So let's start with electrostatics first, then we'll go to the next chapter, and then you will also see capacitors as well. Okay, so only derivations, guys. So I'm expecting everybody has some idea of the basic physical quantities like what is field, what is force, what is potential, what is energy, what is torque, all right, what is dipole. So these are some basic things which you should know, because only then you will be able to understand the derivation. So usually students learn everything, but derivations is the tricky part. So let's get started. Okay, hello Kailash. All right, so the first one is Coulomb's law in vector form. Now I have seen the derivation in even the NCERT. I'll just show it to you over here maybe. All right, so I've seen that over here, and it looks little bit confusing, the manner in which they have put it up over here. So I really did not like the way it has been approached. All right, so I'm going to keep it simple to make you understand how this derivation has to be done. So let's get started. First of all, if this question is asked, what you will do is you will say, according to Coulomb's law, we know that the force is given by magnitude wise 1 by 4 pi epsilon naught charge 1 into charge 2 divided by r square. This is nothing but just the magnitude of the force. But the question is, how do you write it in vector form? So here is what I will suggest you guys to do. Draw the two charges, show the distance between them, also show the forces on both the charges. So when I say F12, it is the force acting on 1 because of 2. On 1 because of 2. When I say F21, it is the force on 2 because of 1. So F12 is force on 1 because of 2, and F21 is force on 2 because of 1. Now by Newton's third law, by the third law of Newton, can I not say F12 and F21 are basically action and reaction pair? Action and reaction pair, equal forces in opposite direction. Welcome Dharun. I'm always for you, bacha. I'm glad Khushi was the replay. Awesome, Ankit Kumar Singh. Congratulations, bacha. You got IIT Roorkee electrical. I'm very happy, bacha, for you. Kudos, bacha. I would love to meet you someday. Come down to Bangalore. Definitely will meet. Hi, Sir. Welcome, bacha. So, can I not say F12 will be nothing but negative of F21? Do you guys agree? So, what is F12? It is nothing but force on 1 by 2. This is nothing but force on 2 by 1. 1 by 2, 2 by 1. Great. Next important thing, once you realize that the forces are equal opposite, this is how you will put the minus sign because they are opposite in direction. We'll come back to the vector equation. See, the vector form of the force, I can write it like this. The force on 2 or the force on 2 because of 1, you can see over here, the force on 2 because of 1 in vector form will be nothing but the magnitude. There will be some magnitude and there will be some unit vector over here. There will be some unit vector over here. Think about it. Anytime you write a vector 5 I cap meters per second or 100 Newton J cap. So there is a magnitude and there is a unit vector to specify the direction. Is that right? Okay. So now think about it. This force on the second charge is in that direction, and I feel there is one more vector which is in that direction. Which one it is? Observe. If I mark the distance between these 2 points, this distance as R21, so R21 is nothing but the position vector of 2 with respect to 1. The position vector of 2 with respect to 1. That means I am starting from here and I am going over here. This is the position vector of 2 with respect to 1. Starting from 1, I am pointing towards 2. This is my position vector. So think about it. What would be the unit vector in that direction? What would be the unit vector in that particular direction? the unit vector in that same direction will be r21 hat. Think about it. If this is the position vector, r21 hat is a unit vector in that particular direction. Everybody agree with this? Come on guys, keep the chat box active and make sure you're saying yes, no, or agreeing or disagreeing with whatever I'm saying. All right. So what is the value of this unit vector? By definition, any unit vector is the vector divided by the magnitude. So if you have a vector, you divide it by its magnitude, you get unit vector. For example, if I have a vector called 5 cap, if I divide it by 5 parts, I get 1 cap. So when I divide this vector r21 with the magnitude which is just r21, I get the unit vector. Great Dharun, very good Shweta, awesome, awesome, awesome. Thank you Dani so much. Yes, I will, I think I did the session on the Newton's, the second session, I'll let you know Khushi whenever I will do it, but not anytime soon, maybe some other chapter for now. Now, let's put the magnitude over here. Let's put the magnitude. The magnitude is nothing but 1 by 4 pi epsilon naught q1 q2 divided by the distance. This distance is nothing but r21. So r21 and unit vector, like you can see right over here, is nothing but r21 I cap. So this is nothing but your force on 2 because of 1. In fact, I can write this as 1 by 4 pi epsilon naught q1 q2 divided, this is square, I'm so sorry, this was a square, so r21 square. This r cap I can write it as r21 divided by r21. This is bar, this is magnitude. So this square into this number will become a cube. So this will become 1 by 4 pi epsilon naught q1 q2 divided by r21 cube, and there will be r21 bar over here. This is the force on 2 because of 1. That's it. That is our final answer. And you will also mention the force on 1 because of 2 will be exactly negative of this. Will be exactly negative of this. So this is also very important to be mentioned. Is that clear? Is that clear, guys? Everybody with me on this? So this is how you're going to prove or you are going to arrive at the vector form of the Coulomb's law of the force equation. So the force on 2 because of 1 is K. This is Coulomb's constant, product of the charges. Cube is there. So a lot of people think, sir, actually it should be square, right? Yes, it should have been square. But remember, there is also a R over here. So this R and this R anyways dimensionally get cancelled. So don't worry, it's perfectly okay. Dimensionally, nothing is wrong. Let's go to the next point. That is the electric field intensity on the axis of a dipole. Electric field on the axis of a dipole. Now again, if you just open it up, okay, this is the next derivation. Anything else before that is just pure definitions. There are no derivations before this. So you will see after probably they talk about flux and all of that, they have given the derivations which is very concise. Hardly anything is there. If somebody who's studying the chapter for the first time looks at it, they will get scared. They will 100% leave these derivations. So that's the reason why I'm going to do this for you. So observe this carefully on the axial line, and then I'm going to also go to the equatorial line as well. So both. So when I have a dipole, this is a positive charge, this is a negative charge. The line joining both the charges is called axis. The line joining both the charge is called as the axis, whereas the line which is perpendicular to the line joining the charges, the perpendicular line, that is called equatorial point. Okay, so we'll start with the axial point first. So the distance between the charges on the dipole is 2a. This is the center of the dipole. R is a point on the axis. Also, there is an assumption over here that this R is much larger than this value of a, meaning if you just think of it like this, this is plus, this is negative charge, you are somewhere over here, this could be 1 centimeter, this could be 200 meters. So that's how far you are as compared to the distance between the charges. That's the meaning of that assumption. Are you able to visualize it? This diagram is not exaggerated right now. This is just to make the values, the geometry, and showing everything else conveniently. That's all. So actually speaking, the charges are very close. The point is very, very far. Okay. Now think about this. Negative charge will apply a field. Positive charge will also apply a field. Negative charge is closer. Positive charge is far away. So whose field will be stronger? Obviously the one which is closer. So that means the negative charge which is there, it will pull with a stronger force or stronger field. So the E negative part will be stronger. The positive charge is far away. So it is also going to apply a force like this, E plus, but that will be definitely smaller. So now think about it. Yes, the derivations are very important high for JEE, especially for JEE mains higher level questions, and JEE advanced so must. For JEE advanced you have to study all the derivations. If you are not, then guarantee you might not get into IIT. You might just probably get a very low rank, but not IIT for sure. I can vouch for that. Okay, so now here is the thing, guys. Here is the thing. See, if I know that the fields are opposite, the net field obviously will be in the direction of the larger force or larger field. So I can say that the net field, this is the net field, will be nothing but the value of E minus, and you will have minus of E plus. One is here, one is there. So subtract both the fields, you will get the resultant field. I hope everybody agrees with this. I hope everybody agrees that the net field at this point will be the subtraction of both of them. Now you just have to substitute the values. So quickly look at this. From the negative charge, how far is this point? If this is R, this is A, this is R, this is A, how much is this distance? R minus A, because this is 2A, so naturally this is A. So this is nothing but R minus A is this distance. Similarly, if you see how far is that point from this charge, the positive one, you can see this is 2A, or rather you can say from this point this is A plus R plus A. So this distance is nothing but R plus A. That's it. I hope this is fine. So now just substitute the values of the field. The field formula is KQ by R square. So K is K, Coulomb's constant. Charge is nothing but Q divided by R. R is nothing but R minus A. So this will be R minus A whole square minus KQ divided by R plus A whole square. I hope everybody is understanding it till here. Very good, Shweta ji. Awesome. Now take some terms common and let's try to solve this. I'm not going to use different colors now. Observe this. So the net field will be K and Q are common, and I can see I can take an LCM over here. So R minus A into R plus A the whole square. I've just taken the LCM. So R minus A square, R plus A square. Here on the top I will have R plus A whole square minus R minus A whole square. See if everybody has understood this particular step. Very, very important. I've just taken the LCM. If you guys have understood this step, please let me know, guys. So R minus A square, R plus A square LCM. So R plus A square goes here, R minus A square goes here. I have to subtract both of them. K and Q are common, so I have just taken it outside the brackets. That's all. Okay. Now observe this. This will become KQ. Well, R plus A whole square will have R square plus A square, R square plus A square plus 2RA. R square, it will have R square plus A square plus 2RA. And here I will have minus R square plus A square minus 2RA. Awesome. And at the bottom, what do I have? A minus B, A plus B. A minus B into A plus B is A square minus B square. Simple identity. So this will be nothing but R square minus A square's whole square. Cool. Next step. Think about it carefully. What is going to happen? You can see R square and R square cancels. A square and A square also cancels. 2RA minus minus plus. So it will become 2RA plus 2RA. So hence it will become 4RA. So this will become KQ into 4 times RA, 4 times of RA divided by R square minus A square. Now R is much larger than A. R is much larger than A. So big number square, 1000 square minus 0.1 square. 1000 square minus 0.1 square. Think of it like that. Is almost 1000 square. So why not neglect it? So can I not say approximately this is nothing but, I'll just rearrange the terms, 2 times of K into I will say it is nothing but Q, alright, Q into 2A into R divided by, there was a square also over here. So R square minus A square, I can approximately write it as just R square, and I have to put a square over here. Wonderful. Now the moment I do this, my blessings are always with all of you, Aisha, and everyone. And all the best, bacha. You will pakka do well. So that's why I'm conducting this session. Observe this. R square is R raised to 4 and charge into 2A. What do you think is charge into 2 times of A? Come on, my warriors, think about this particular term carefully. Charge into the distance between them. That is your dipole moment. So how about just replacing it with dipole moment P? Dipole moment, electrical dipole moment, that's all. And you have R over here and you have R raised to 4. Obviously one of the R's will get cancelled. This will just become 3. So wonderfully, I have proved now that the electric field, I'm just going to put it over here, the electric field on the axial point is 2 times of K. K is nothing but 1 by 4 pi epsilon naught, okay, into P divided by R cube. That's it. That's the final result. But there is one small step over here. Observe carefully. The dipole moment, the electrical dipole moment, which is P, which is charge into 2A, is in this direction. The field is also in the same direction. So on the axis, the field and the dipole both happen to be in the same direction. So if I happen to put a bar over here, I should also put a bar over here without any minus or plus sign because their directions are same. So that becomes my final result, and I'm just going to sit and block this. That's all. So I'm just going to block this because the directions are same. So electric field is parallel to the dipole moment on the axis. That is your last reasoning that you're going to put when you put it up in your board paper. Everybody clear? So there is no negative sign over here. Yes. I hope this is clear. Sir, I've studied only 2 lessons in physics, NCERT in 4 months. Can I ace physics? And Dharun, I feel you should study at least for 7 to 10 hours, including coaching maybe. And I'm pretty sure it is possible in the next 4 months. So maybe in the first attempt, you might get some marks, but in the next attempt, I'm pretty sure you'll improve and you will get a very good score, bacha. So students have done it in the past. In fact, you have more than 4 months, so don't get scared. You can definitely crack it. Okay? Don't worry. Just start studying. Don't sit and think that I have not done this, so what should I do now? I think my life is wasted. No, it's not like that. If you keep thinking about it, you will not take the next step. Next question is electric field on the equator, guys. So let's try to do this. Electric field on the equator. This is relatively simpler as compared to this one. Here you had to use A minus B into A plus B identity. You have to use A square plus B, A plus B whole square, A minus B whole square. So basic identities were involved. Here it is more of components than anything else. Observe this. There is a negative charge here, there is a positive charge here. I hope you can see the plus sign. This is positive, this is your negative charge. The dipole moment is there, and this is your equatorial region or equatorial plane or the equator for this dipole. So whenever you have a dipole, this becomes the axis, this becomes the equator. The field lines go like this and come back. So the field lines go like this and come back. So you can see at the equator, the field is definitely opposite to the dipole moment. So the electric field is opposite. So 100% in the vector form, I'm going to put a minus sign. All right. So for now, let's forget about this. Let's just concentrate on the magnitude. So observe this carefully. Observe this carefully. What I can see over here is this positive charge at this particular point, will create a field in this particular direction. Will create a field in this particular direction, which I have called it as E1. Can you see that? This is the E1 field created by this particular positive charge over here. R is the distance from the center of the dipole, 2a is the length of the dipole, and in fact here they have used L. I will just use the same symbol A and A so that we are consistent. So the length of the dipole is 2a. Similarly, the negative charge which is there over here, is situated at a distance of, again, this hypotenuse of this right angle triangle, and it will also create an attractive field like this because it is negative charge. So that negative charge electric field is E2. See if you are able to observe this. Everybody clear? Everybody clear about this question? Everybody clear about this diagram? The positive charge will repel, the negative charge will attract. This is R, this is 2a. This is a right angle triangle, this is also a right angle triangle. Both the triangles are congruent, both these distances are also same. Why? Because they are congruent triangles. This height is same, 90 degrees, the base is same, all the angles will also be same. In fact, if you would try to mark the angles, this is how it would look like. If this is theta, even this will be theta. And this distance d will be nothing but root of r square plus a square. R square plus a square. Everybody with me on this? If this is theta, even this is theta. Why? These are two parallel lines. If this green line makes some angle with this parallel line also will make the same angle. Not just that, again if you see these two parallel lines, this one and this one, if this angle is theta, naturally this angle will also be theta because they are alternate angles. I hope you can see that. Everybody with me on this? Kailash, per month at least 3 chapters you should study, bacha. 3 to 4 chapters. It depends on the size. If there are big chapters, obviously 3 to 4. If there are small chapters, then it should go till 5 at least. Okay. Now, moving on, the net electric field that you can see over here, this net electric field that you can see over here, I have a feeling it's the vector sum of this and this, but you can see E1's y component and E2's y component will cancel. Look at it carefully, guys. There is a y component of E1, so that is E1 sine theta, and there is also a y component of E2, which is E2 sine theta. These both are definitely going to cancel each other. They are going to cancel each other because the distance is same, charge is same, magnitudes, angles are same, so they are just going to cancel out. But if you look at the cos components, they are going to add each other. So E1's cos theta component will be over here towards your left side, and also E2's cos component, which is also going to be in the horizontal direction. Just check this out. Everybody with me on this? Both the vectors component. I hope you guys can see that. This was the vector over here and there was a vector over here. The y components are cancelling, but the x components are definitely assisting each other. Now, obviously E1 and E2 both are equal. E1 and E2 both are equal. So I might as well say this is 2 times of E1 cos theta. Reason being, since E1 is equal to E2 magnitude wise, because charge is same, magnitude wise, distance is also same. So what is the value of E1, you might say? So the value of E1 is, what is the value of E1? KQ by R square. K is Coulomb's constant, charge is just Q, divided by distance, distance is D square, cos theta. If you look at any triangle, cos theta is adjacent side by hypotenuse. So adjacent side, like you can see, is nothing but A, and hypotenuse is nothing but D. So this is just going to become K into Q into 2A divided by dq. Now you can clearly see charge into 2A just like before. Charge into 2A just like before. What is it? It is your dipole moment. It is your dipole moment, electrical dipole moment. So you can replace that with just P, and rest of the terms will be as it is. D is root of r square plus a square. Root of r square plus a square. So this will be nothing but r square plus a square whole raised to 3 by 2. Whole raised to 3 by 2 because cube and then root. So raised to 3 and also raised to half. So 3 by 2 will be there. But we all know this r is much larger than a value. So obviously r square plus a square can be just written down as k into p divided by just r square. A is very small in comparison with r. If r is like 200-300 meters, a will be 5-6 centimeters. So when you see the comparison, a should be neglected. So only r square will be there, raised to 3 by 2. So when square and you take the half power on the top, you can see square and this half power will just get cancelled. So we'll just have k into p divided by r raised to 3. That is going to be your electric field. That's it. But like I had told you before, the moment you have a dipole, the electric field goes somewhat like this, and we can see that the electric field value is exactly opposite to the dipole moment. If dipole moment is here, electric field is exactly opposite to it. So that's why I should put a negative sign over here if I write it in vector form. So if I write it in vector form, I'm just going to put a negative sign. See if this much is clear. Everybody with me on this? Was this a wonderful derivation? Come on, my warriors, let me know in the chat box. The minus sign has come because electric field is anti-parallel to the dipole moment. That's the derivation. Can we move ahead to the next one? Let me know in the chat box, guys. Okay, let's move on if you guys are done with this particular derivation. Okay, cool, amazing. So let's move on to the next one. This is done, I guess. Yep, this is done. So let's move on to the next one. Application of Gauss's theorem in the calculation of the electric field of a line charge. So whenever you have to apply Gauss's law for a line charge like this, so what will be usually given is lambda, which is your linear charge density, which is expressed in coulombs per meter, how much charge is there per unit length. At this particular line charge will create electric field in all the possible directions, and you will have to choose a Gaussian surface such that your electric field happens to be either parallel or perpendicular to the electric field lines, because then the calculations using Gauss law becomes much more convenient. I hope this is clear. So what I'm going to do, I'm going to take choose a cylindrical surface. I'm going to choose a cylindrical surface, and in that cylindrical surface you will notice those electric field lines will hit the curved surface perpendicular to it. Observe, if I choose a Gaussian surface something like this, if I choose a Gaussian surface which is cylindrical, somewhat like this, okay, and the height of this is, let's say, h, and the radius of this is, let's say, r, at some distance r, you will notice that the electric field which will come out from this, all right, the electric field which will come out from this will be obviously perpendicular to the surface. At any point, you take any point, the electric field will be perpendicular to the curved surface like this. So these are the electric field lines. I'm just showing few of them, not all of them. So I want you to understand it from this particular diagram. Cool. So if the curved surface is perpendicular to the electric field, that simplifies our process using Gauss law. Observe. What is Gauss law? Gauss law says the total flux, that means the electric field into the area vectors integration for the entire surface, is the charge which is inside by epsilon naught. That is nothing but your Gauss's law or Gauss's theorem. Now, if you choose the curved surface, that's where the actual flux is passing through. The flat surfaces, there is no flux. So, don't you see, at every point on the curved surface, field is constant. So, this part, which is the flux on the total surface, the total flux on the surface is only passing through the curved surface. The total flux through the cylinder is only passing through the curved surface, because the field lines will hit only the curved surface. They are not passing through the flat circular faces. So can I not say the total flux is only the flux through the curved surface, is only the flux through the curved surface where electric field is same, where electric field is same. If you come from this point to this point, this point to this point, this point to that point, this point to this point, this point to this point, all the points are at the same distance from the line charge. Think about it. All the points are at the same distance from the line charge. What does it mean? The field strength is the same. So, because the field strength is same, I can shift this field outside. I can shift this field outside the integration. That's the rule of integration. Any constant term, you bring it outside. So cyclic integral, the area is equal to Qn divided by epsilon naught. So just do the math. What is the curved surface area? What is the curved surface area of a cylinder? It is nothing but 2 pi r, which is the circumference, into the height of the cylinder. So 2 pi r is the circumference multiplied by height gives you the curved surface. What is the charge inside? Well, that you can get it easily. If lambda is the charge per unit length, so in this cylinder, the charge will be Qin and the length will be nothing but h. So instead of Qin, why not just put lambda into h? Think about it. If lambda is Qin by h, Qin will be lambda h, because lambda is the charge per unit length, the length is h. That's all. So divide this with epsilon naught, and you can clearly see over here this h and this h just got cancelled. So therefore I will get the electric field to be 1 by 2 pi epsilon naught. 2 pi and epsilon naught come over here. Lambda is there as it is. This r goes over here as it is. That's it. So that is your final result. Okay. So that's the field due to a line charge. Is that understood or clear? Or can we move ahead to the next question? Coming up on your screen, guys. Get ready for this. Now look at this. Find the electric field intensity due to basically a flat surface. That's what the question says. Again, you have to use Gaussian surface. Let's try this out. First of all, it's a flat surface. First of all, it's a flat surface. So what we are going to do is we are going to understand where the field lines are going to come. Based on that, I will choose the surface. So if the field lines are perpendicular, if the field lines are going to come from this sheet outwards like this on both the sides, it makes sense to choose a Gaussian surface which accommodates them such that the field is either perpendicular or parallel. And I feel the best way to take these uniform field lines Gaussian surface is choose a rectangular box, or assume a cylinder like somebody is saying. Correcto. So let's do that. So say for example, the field lines due to this particular flat surface come out like this, okay. So they come out like this. They will also go on the other side. Please keep that in mind. I will choose a Gaussian surface somewhat like this, where maybe you can choose a cylinder, you can choose a you can also choose a cuboid box. All those things will work, and it should also come out from the other side like this. See if you are able to visualize. There is a cylinder over here. Okay, so there is a cylinder over here which has been chosen, which is piercing it. This is your Gaussian cylinder. Gaussian cylinder. This has a surface area of A. So if you look at it sideways, this is your sheet. The field is coming like this. The field is coming like this. The Gaussian cylinder is over here like this. The Gaussian cylinder is over here like this. So now again use the Gauss's law and see what is happening. Cyclic integral electric field into area is the enclosed charge by epsilon naught. Now if you notice, when I have to calculate the total flux, try to see where the flux is actually cutting through. If you notice in this situation, it is not cutting through the curved surface. In fact, it is cutting through the flat surface. In the previous question, you saw the flux was cutting through the curved surface. Here, the field lines are piercing through the flat surface. So, the total flux is the flux through basically the two circular faces. So, the two circular faces, one this side, one that side, here and here, both. And that's all it's going to be. And that's the only flux which is cutting through, nothing else. And I am going to see that on that flat surface, the field here, everywhere is same. And the field is basically same on that particular surface. The moment the field is same, I can bring it outside. So electric field into integration of the area is going to give me enclosed charge by epsilon naught. Now, when I have to add the areas, integrate the areas, I will add only the circular faces area. So this side area is A, that side behind the area is also A. So integration of the areas will nothing but be just 2 times of A. So there are 2 circular faces here and here. So the total area through which the flux is piercing is 2 times of A. This is very, very important. Now, what do we do on the RHS? So here we need another term which is called as sigma. This is called as the surface. This is called as the surface charge density. This surface charge density is often expressed in coulomb per meter square. How many coulombs of charge is there per meter square? How many coulombs of charge is there per meter square? And think about it in this Gaussian surface, because this always says inside charge. In this cylinder, think which is piercing through that flat sheet, how much charge is there? The charge is Q in. And how much area is occupied by that charge which is enclosed? It is nothing but A. Think carefully. Sigma represents how many coulombs of charge is there per unit area. So if you look at only that part which is being pierced, which is inside the cylinder, in that part Q in charge is there. And how much area is there? The same area as that of the faces of the cylinder. So shouldn't I put Q in as sigma into A? Sigma into A is the enclosed charge. So now what happens, guys? Now what happens? Obviously this area and this area will get cancelled, and I will get the field is equal to sigma by 2 times of permittivity of vacuum, or epsilon naught. So that becomes your final formula. Field is charge density or charge per unit area upon 2 times of epsilon naught. And the most important thing is this is uniform field. Why is it called uniform field? Because it does not depend on distance. It does not depend on distance. No matter how far you go, the field lines are parallel. They are not going away or not coming together. So the field is uniform. It is not becoming weak or it is becoming strong. Whereas in the previous question, you can see R was there. R means distance. So it depends how far you are. And accordingly, the field lines will go away and away. So it becomes weaker and weaker as you go away. So that's why I will call this field as uniform. I'm so glad, Kavita, you are able to understand this. You being a 11th standard student. It means a lot. Alright. Mr. Devil, I will make a video on that as well. I'll be putting up a short very soon. Here's the next thing. The electric field intensity due to a charged shell at different points. So there are two major points usually. These are very simple to solve. So you have to again start with Gaussian surface. Electric field dot area vector is enclosed charge by epsilon naught. It's a charged shell. Please understand that. When I say charged shell, that means the charges are only there on the shell or on the periphery or on the outer surface of this circular object. This is your charge. Let's say Q. From the center, at a distance of r, you want to find the field. So what I do, I choose a Gaussian surface. This is a Gaussian surface is always closed surface. There are no openings in it. That's how the law is defined. So Gaussian sphere, I would say. It's a Gaussian sphere. And at all these points, let's assume, symmetrically assume that there is some electric field. But the beauty of this is, when you look at the RHS, what is the charge inside this Gaussian sphere? The charge inside this Gaussian sphere is obviously 0. So hence RHS is 0. So naturally LHS is going to be 0. So area can't be 0. Naturally it has to be nothing else but the electric field. RHS is 0 because there is no charge inside. All the charges are outside. So if you are inside a shell, at any point the field is 0. So very, very crucial result. So field at any point inside a charged shell is going to be 0. Very, very crucial. Good evening, Piyush. Good evening, Abdul Malik. Yep. I hope this is clear. Can I watch Pathfinder and Nurture series for physics need? Definitely, Abdul Malik. That the intention of Pathfinder and Nurture was for every competitive exam, any student who wants to understand the concepts for especially physics, definitely you can understand it. So please watch it for JEE and NEET. It will definitely help you. Hello Prasad Pachila. Welcome, Bacha. So field inside is 0. What about a point outside? So again, choose a Gaussian surface. Choose a Gaussian surface. Again, understand this is a charged shell. This is a charged shell like this. So the charges are on the periphery. You have chosen a point which is outside. Now this is my Gaussian sphere. This is my Gaussian sphere. This is my Gaussian sphere. Let's try this out and see what happens. Let's use Gauss law. Cyclic integral E dA is equal to Q in by epsilon naught. In this case, for this Gaussian sphere, obviously this entire charge is inside that sphere. So there is no doubt that the enclosed charge will just be Q, and here I will have epsilon naught. That's the first thing that you will notice about RHS. Let's worry now about the LHS. So for that, think how will the electric field lines look like? How will the electric field lines look like? So the electric field lines from this charge will look something like this. They will come outwards. There will be no field inside, but definitely there will be field only outside the conductor, outside the shell. And these electric field lines are again perpendicular to the area. They are piercing through the area, and everywhere this total flux is passing through the sphere, which we have assumed, where you will notice electric field is same everywhere. Why is it same? Here, all these are at the same distance from the center. That's why the field is same everywhere. So let's just shift the electric field outside. I'll just have integration of the area is equal to Q by epsilon naught. Integration of area, that means the area's sum of the sphere. So the area of the sphere is nothing but 4 pi r square. 4 pi r square, r is the radius, is the area of the sphere. That's what that integration means. So that's Q by epsilon naught. So hence the electric field will be 1 by 4 pi and epsilon naught come together. Q is there as it is, and r square will come over here. So there you go. That is our final result. This tells me that the field the field outside a charged shell, is exactly like a point charge, very, very important, and it is definitely not equal to 0. You can see that. I hope this is clear. Sismparthi, I'm not taking classes daily, bacha, but I'm taking classes regularly. Once or twice a week at least I'll try to come, and in October you will probably see me a little bit more frequently. But the point is that you have all my lectures which are there. In addition to that, whatever videos are there already on the channel of mine, apart from that I'll be doing extra things which will help you understand the subject better. That's what I'm going to do. Okay, so moving on to the next one, and that is electric potential due to a point charge. This is also a very important derivation. A lot of people generally make some mistakes in these kind of things, especially with the sign. So there is a charge, there is a point, and that point is at a distance r, and the question is what is the potential at any point. So there you have to write down the definition of potential, derive it, etc. So you will get some 3-4 marks easily for that. So first of all, what is the definition of electric potential. Electric potential has been defined as the work which has to be done to bring a unit test positive charge from infinity to that particular point. So work done to bring a unit test positive charge from infinity to that point is called as basically the electric potential. So the way you define it is nothing but the work done to bring a unit test positive charge from infinity to that particular point. So work done per unit test charge, this is my test charge. So work done, actually I should have put per unit test charge, to bring work done per test charge to bring it from infinity to that particular point. Now over here, what is the work done's definition? Work, remember from 11th standard, is force into displacement, but that is only when the force is constant. But when the force changes, obviously when you bring this charge, the force of repulsion will definitely change. You have to use integration. So that's what you should understand, that if I have this particular point at some distance, let's say over here, which is x, and this happens to be your dx, the electric force between this charge capital Q and this charge small q will be obviously in this particular direction. This is the force of electricity. But you have to bring the charge closer. So from infinity you are pushing it like this. So your actual force which is going to do work is going to be this way. This is going to be your external force which is going to bring the charge from infinity to that particular point. So I am going to see that this force is definitely going to change as I come closer and closer, because the force is going to get stronger. So definitely it has to be integration. So it will be integration of the external force dot the displacement dx divided by, or if you don't like the vector form, no problem, put f external dx cos theta and divided by this charge. Now think about it. The magnitude of this external force will be equal to the electric force. So whatever electric force I am experiencing, I am going to exactly apply the same force so that I am able to bring this charge closer and closer. So that's why I can write this as integral the force of electricity into dx. Theta, what is theta? Think about it. It's the angle between your external force and your displacement. Clearly it is pi radian or 180 degrees. It's cos 180, and cos of pi or 180 is nothing but -1. Do you guys understand it? Why it is -1? And that's it. The whole thing divided by Q. Now substitute the value of the electric force. The value of the electric force will be nothing but K capital Q into small q divided by x square. Okay, this q will come over here as it is, and this dx will also come over here as it is. This minus sign I will bring it over here. Okay, next step. This q and this q you can clearly see is getting cancelled out. K capital Q are constant, so I should bring it outside the integral. So I will get, I'll just write it over here maybe. Observe, the voltage or the potential at that point will be minus K capital Q minus K capital Q. X square I will bring it on the top. X square I will bring it on the top as minus 2 power dx. I have to bring it from infinity to that point. That means the value of x will be first infinity and then this x will reduce to r. So the value of x was first infinite, slowly you're bringing it to this point. So that is how the limits will come out to be. Now it's simple integration. So minus kq, x raised to minus 2's integration is x raised to minus 1. Okay, x raised to minus 1 divided by minus 1. So again the limits will be infinity and then r. This minus and this minus cancel. So it will just become kq. Okay, this minus and this minus have cancelled. So it will just become kq, and I will have x raised to minus 1, that means 1 by x. So first infinity and then r. Now substitute. First you substitute as r. So 1 by r minus, then you put infinity. That's it over here. 1 by infinity is 0, guys. So it will become kq into 1 by r minus 0. So it will just become kq divided by r. That is the value of the potential. That's it. So there is no confusion over here. If you open up NCERT and read, I'm pretty sure you will get really confused. It's paid Bacha Abdul Malik. So if you are a part of the pro subscription, you have access to all my micro courses: HC Verma, derivation, numerical problem solving, Euro course solving, any other micro course of any other teacher also, you will get access to it when you are in a part of any kind of pro subscriptions, any kind of. Thank you for all the love from Bangladesh, Tohin Hussain. Thank you so much. Lingeshwaran, I have already made one. Just search for formulas physics Shreyas Sir. There's a beautiful video, more than 1 lakh views. You can see that. Okay, all formulas from all the chapters is there. You can have a look at it. Okay, I hope this is clear. Welcome Raju. Hello, hola, shagun bhati gujar. Okay, so I hope this is understood. So the challenge was here, the directions and the sign. Understanding that the electric force is repulsive, but your external force will be this way. External force and displacement both are basically, this dx are making an angle of pi. So a lot of people choose dx here. No, that's not correct. If x is here, dx will also be in the same direction. So that's why this cos 180 is very important. A lot of people make a mistake generally over here. That's what I have seen. Okay, now let's go to the next point, and that is electric potential due to a dipole. A lot of people do not like this derivation because it's quite lengthy, and if you, I don't know whether I can have it open, maybe over here. If you open it up, maybe in NCERT, you will be like, what have they really done? I didn't understand anything. So guys, I'm not sure where it is gone. I think it is somewhere here only. Okay, so if you try to look at the derivation, right, it is crazy. So I do not want you to have a look at the derivation that way. We are going to see, yeah, look over here. It's some crazy derivation. Nobody will understand anything if you just look over here. So I'm going to explain this to you in detail. It's very important. It's very simple if you understand the steps, and you can definitely get some 4-5 marks in the examination, guaranteed. Okay, now this is a general point. So this is a dipole, this is negative, this is positive charge. Okay, this is a general point making a distance r, and let me just put up some pointers over here. This is, let's say, okay, let's do one thing. Okay, so I'm just going to make this as the positive charge. This was your negative charge, so this is your positive charge. This distance, I hope you can see, this is r1, this is r2, okay, this is r2, and this is just r. I hope you are able to see this. If you're not, maybe I'll have to just make it little bit bigger. Okay, I'll just try this because already there was something written over here. Just erasing that, just give me a second. Yep, so this is nothing but your R1, this is nothing but your this is just R, this is just R, and over here, this is nothing but R2. This is nothing but R2. Okay, fine, everybody with me on this? Okay, keep this in mind. Okay, great. Now, the dipole moment is here from negative to the positive. From the center, you will measure R. At this point, you want the potential. Potential at any point. In fact, if you put theta as 0, that means that point will come on the line joining the charges. So that will be axis. If you put theta as 90 degree, then this line will become equatorial. So I'm trying to find it for a general point, and that is what? That is what is there in the books also. So observe carefully now. So let's try this out. First of all, the potential at that particular point, P will be nothing but the potential due to the positive charge. That means due to this one, the potential due to the positive charge plus the potential due to the negative charge also. The potential due to the negative charge also. Now, the good thing is potential is a scalar quantity. So you don't have to take vectors. So remember, potential is added like scalars. Very, very important. So you don't have to take any kind of component. That's the best part about this. Is that clear? Everybody with me? So you don't worry about, sir, this component, that component. That happens with field, not with potential. Okay. Now, let's see what is the potential due to the positive charge. It will be nothing but K into Q divided by that distance is nothing but R1. Due to negative charge, it will be negative because it's negative charge. So minus KQ divided by R2. So I can see clearly there is this K and Q which is common. And what I have over here is 1 by R1 minus 1 by R2. That's what I can see. The challenge is now to find the potential at that point. I need to know what is R1 and what is R2. I'll do one thing. I'll show you how to find R1. R2 is going to be exactly similar, just with a small sign change. So observe carefully. In this particular triangle, okay, this is theta, this distance is A, this distance is R, this distance is R1, this is particular point P. So if you use something called as the cosine rule, it's a rule in triangles. It says if you know two sides and one angle, you can find the third side. So the side which is opposite the angle, turns out to be like this. So R1 square will be the adjacent sides A square and R square. So adjacent sides to theta. So it will be nothing but A square plus R square minus 2 times AR cos theta. This is your cosine rule. How many of you remember it? Do you remember cosine rule? It's there in maths. If you're a bio or only NEET student, then maybe you won't know about it. But this is a rule. What is it? Opposite side to the angle square is adjacent side square minus 2 into this adjacent side into that adjacent side into cos theta. That's why it's called cosine rule. Yes, Abdul Malik, I always start from basics. So it will be more than enough for the derivations part. Definitely. Or if I'm conducting any other class, it will be enough for anything else also. Now, I can say I want 1 by R1. So I'll do one thing. I'll take R square common. And I also know one more thing, guys. This R, right, is much larger than A. That is the standard assumption. You are very far. So maybe I will just take R square common. Observe what will happen. I will get this as A square by R square plus 1 minus 2A by R into cos theta. See if you are able to understand this. If you multiply by R square inside, this will become A square, this will become R square, and this R with this R square, 1 R will come on the top. Now we all know A by R will be a very small number. A is very small as compared to R. So don't you see this is going to be negligible? It is going to be negligible, small number by a very large number square. It's like 1 by 1000 square. It's going to be very small. You will be like, sir, then this is also negligible. No, that is not so negligible, because if you neglect that, then there is nothing. Then you will just get it as R. So then there is no point only. So why were we doing all this? So I would have said the same thing first only. R1 is equal to R. The whole challenge is that R1 and R2 are differing by a small amount. That's what I want to find out. So this is little bit negligible. So I can write it as R square into 1 minus 2A by R into cos theta. Great. So this is nothing but your R1 square. Now flip it below. Okay, so this will become 1 by R1 square is equal to 1 by R square. Instead of bringing it down, I'll just write it as 1 minus 2A by R cos theta raised to minus 1. Is that fine? Is that fine? Everybody with me on this? That's it, as simple as that. Great. Now take roots, square root on both sides. Observe what I am trying to do. Take square roots on both the sides. What will you get? You will get 1 by R1 is equal to 1 by R. Square root of this will be nothing but 1 minus 2A by R cos theta whole raised to minus 1 by 2. Great. Now you will be like, okay sir, what next? Should I now use this over here? Not yet. There is one small thing which we need to do before we go ahead. I don't like this power, get rid of it, and that's nothing but binomial. 1 plus x raised to n. Use binomial theorem, guys. Use binomial theorem. 1 plus x. This is 1, this is x, or raised to n is approximately 1 plus nx. If this x is small, and it is, why not? A is small than R, so this is a small number, so I can definitely use this particular concept. So let's use the binomial approximation and see what do I get. So 1 by R1 will be 1 by R into 1 plus nx. N is nothing but minus 1 by 2, and x is nothing but this negative term, so minus 2a by r into cos theta. So that's what it is. Minus minus cancels, 2 also cancels. So 1 by r1 will be 1 by r into 1 plus a cos theta divided by r. Just check this out. This is what I got, 1 by r1. Very good, Purvika. Hello, Dilip. Welcome, bacha. Everybody clear? So cosine rule is there and binomial is also there. This can come like a big question in your board examination. Now, similarly, this is just nothing but your R2. This is your R1. This is nothing but your R. This is nothing but your plus Q. Okay, all of this. So similarly, can I not say, can I not say 1 by R2? Just think about it, guys. If 1 by R1 was this, 1 by R2, I can directly write as 1 by R into, instead of 1 plus a cos theta by R, it will be 1 minus, that's all. That's the only difference. So it will be 1 minus a cos theta divided by R. See if this is okay. See if this is okay. Everybody with me on this? Clearo? Understoodo? Now come back to our original problem, which was potential. So let's go back to potential, guys. So V will be equal to K into, what was it? K into Q. So K into Q, 1 by R1 minus 1 by R2. So substitute everything over here now. So let's try to do this. So I'm just going to use 1 by R1 over here first. So let me put over here. 1 by R1 is nothing but 1 by R into 1 plus a cos theta divided by R. And then you will have minus 1 by R2. That means 1 by R into 1 minus a cos theta divided by R. So that is going to complete this. So I can see 1 by R is common. So I'm just going to take out few common terms over here. So KQ by R. And what is going to be there inside the bracket? Observe carefully. This one and this one will cancel. This one and this one will cancel. This one, this term which is there over here, so which is a cos theta divided by r, and this term minus minus will become plus. Again, a cos theta divided by r will obviously add together. So again I can take r common outside, so it will become kq divided by r square. A cos theta plus a cos theta is 2a cos theta. I might as well write it as k into, okay, I can see right now over here what is happening. This q into 2a is nothing but your dipole moment. This is your dipole moment. So I can just put it as k into p, and this cos theta comes over here as it is, and over here I have r square. So that's it, that's the final answer. Potential is k into p into cos theta divided by r square. That is your final result. That is your final result. See if this is okay, understood or clear. Okay, so very nice question. You don't have to do the second part. The first part you find r1. Once you find r1, r2 you can just write, instead of this plus sign there will be a minus sign. That's the only difference. Is that clear? So cosine rule, binomial, and obviously you have to use your basic algebra. If you're loving this derivation, I hope you are smashing the like button as well. If you're not, then you're not doing justice to the channel, guys. So make sure you're doing that as well. Okay, so let's move on to the next question and next derivation actually, that is on the torque and the energy. These kind of questions also come. Obviously in the exam they ask you find the torque or find the energy derivation for a dipole placed in an electric field. So first of all, let's see where is our dipole. This is negative charge, this is positive charge. So you can clearly see this is our dipole P. Great. Then if you see, the electric field is in this particular direction. The electric field is in this particular direction. So this is the direction of the electric field, and the electric field makes an angle theta, with the dipole moment. This electric field will apply some electric force obviously. So the electric forces will look something like this. On the positive charge, it will be this way. It will be Q into E this way. On the negative charge, the force of electric field will be Q into E this way. Now, this force on the positive, this force on the negative will cancel. So definitely net force on the dipole will be 0. But net torque is not 0. Why? That force and this force will try to rotate it like this. That's why you see a torque being generated. So how do you find the torque? Well, that's simple. First of all, this dipole's length is 2a. So why not just assume this as a. This is a, and this is also going to be a only. Now to find the torque, here is the catch. See, from the center, right? From the center, this distance is a, but the force which is being acted is in this direction, QE. But this force will not create torque. A component of that force will create torque. Remember, always take the sine theta value if the force is making an angle. You can see this is the angle made, which is theta. So what will be the torque because of this force? It will be RF sine theta. RF sine theta between them. I hope you see, if this is theta, even this is theta. This is basically your R, or your position vector. So same way, I can say this charge also creates another torque in the opposite direction, in this direction. This torque and that torque will not cancel. In fact, they are in the same direction, you can see. So they will definitely add. Hello Yadvinder, hello Ravan, welcome. Yes, so can I not say the net torque will be torque on the positive plus torque on the negative? In fact, I can say 2 times the torque on the positive, because they are in the same direction. They are in the same direction. I hope you guys can see it. They're definitely in the same direction. Everybody with me on this? Clear-o? Understood-o? Amazing-o? Can we move ahead-o? Everybody with me on this? Alright, observe now next. What is the torque on the positive charge? The torque on the positive charge will be nothing but the R is nothing but A over here, into force, which is nothing but QE over here, into the sine of theta. So that will be nothing but sine of the angle between the force and the R vector, which is sine of theta, as simple as that. Okay, interesting. Now I can just rearrange this a little bit to adjust into some known terms like this. So I'll write it as Q into 2A into E into sine theta. Observe carefully, this part again is your dipole moment. This is your dipole moment. So why not just put it as PE sine theta? That's your torque magnitude wise, but vector wise it will be P cross E. That's it. So that becomes your derivation for the torque. Very, very crucial. Understood? Very good, Bharati. Amazing. So this is how you're going to derive the torque on a dipole which is placed in some electric field. That's the diagram. That you should start with diagram. Always show the terms. Start with the assumptions. See what are the forces. See if there are some resolutions or you have to take some angles, and go by the definition, you will get it. Next one is the energy. Let's move on to that. So again, let's show the electric field. Electric field is over here. This is the electric field. It makes some angle theta with the electrical dipole. The dipole moment is over here, which is charged into 2A. Great. Question is, what is the energy at any angle theta? So first things first, you should know the reference energy. If you do not know the reference energy, you will make a mistake. It is assumed that when the dipole is exactly perpendicular to the electric field, then the potential energy is assumed to be zero. This is called as your reference or zero reference potential energy. Whenever you talk about potential energy now, you always take something as zero. So here, when the dipole is perpendicular to the field, that's what has been assumed as zero. Cool. Anything else will be measured with respect to this. So now, when I have rotated it by some angle, okay, so I want to know what is the energy stored at any particular point. So here is my logic, guys. If this is theta, think about it, if this is theta, obviously when I try to slightly even rotate it this way, this angle like this clockwise will be d theta. So d theta is clockwise, please understand that. If this is theta, then d theta is in the direction of theta. Always theta is measured not from 90 degrees, always with respect to the field. Theta is always measured with respect to the field. So d theta is always again in the same direction of theta. Cool. So let's try to write down the potential energy now. So the potential energy of the dipole will come from the work which has to be done, by the external torque, all right, in storing it. Or remember, there was one standard formula for potential energy. If you remember, it was nothing but a minus of the work done by the conservative force, or the negative of the work done by the conservative force. So that is also one way of looking at it. But if you get confused with the negative sign, then just keep it simple. The change in the potential energy of the dipole, has come from the work done by the external torque in rotating it. So if I write it as potential energy at particular theta minus potential energy at 90 degrees. Or you can say or think of it this way. Earlier it was at 90 degrees. Now I have brought it to theta. So from this to this position, how much energy has changed? That will come. If you are changing the energy, it has to come from somebody's work. Earlier it was at 90, now I have to bring it at theta. It has to come by somebody's work. Keep this in mind. This will be equal to the work done by the external torque. So this will be integration of, instead of force with displacement, it will be torque d theta. It will be torque integration with d theta. So u theta is u theta only. U 90 degrees is 0 as per the given condition or assumption. Whenever it is at 90 degrees, remember the energy is assumed to be 0. The torque is nothing but P E sine theta. That's the standard thing. Integration with respect to d theta. Now, once you put this up, very important, put the limits. First, it is at 90 degrees. Then it has been brought to theta. Then it has been brought to theta. So now just integrate this and see what do you get. U theta is equal to P and E are constants. Sine theta's integration is nothing but cos theta. So this will be cos theta. And first put theta and then put cos of 90 degrees. Now cos 90 is basically 0. So therefore it will be P E cos theta. Like I can see there is something missing over here. Like I can see there is something missing over here. So you will be like, what is missing, sir? Yes, there is a negative sign missing. So whenever you do this, you will often see you might get confused. Sir, I didn't even realize that, oh my God, I missed the negative sign. Those of you who know the final formula, know that the final formula has a negative sign over here. So how do you get that negative sign? So where have we missed the negative sign? I think we have missed the negative sign right over here, somewhere over here. Observe, this is the work done by the external torque. This torque is the torque by the field. This torque is the torque by the field. The actual torque, think about it. While you bring it from 90 to theta, will be exactly opposite it. Will be exactly opposite it. Like this. The external torque will be like this. But you are moving it from 90 to this angle. You are moving it from 90 to this angle. So your displacement is exactly opposite to the torque. The external torque will be this way. Your displacement is like this from 90 degrees to theta. So hence the work done must be negative. Hence I should definitely put a minus sign over here so that it is consistent. So a lot of people miss that minus sign. Is that clear? Everybody? So hence the final answer will be minus P vector dot E vector. The dot product, because electric field and dipole moment both are vector quantities. And P E cos theta, it can be also written down as the dot product of P and E vector. Ruchi, I hope it is clear. Is that understood? No problem, Heba. I'm pretty sure it will help you for the final board exam. Remember, midterm is not the only game. Heba, see me, है ना? Final aim is your final board exam, which is going to happen in the next few months. Hello, Sunek Skula, Parvati. Oh my God, you have a little bit difficult name, bacha. I hope I pronounced it fine. All right, so this is how you're going to get the potential energy of a dipole. Moving on to the next one. Last few derivations, guys. Let's move on to this. Capacitance of a parallel plate capacitor, standard thing. There is a negative charge, positive charge on the plates. The capacitor has a area of the plates as A, and the distance between the two plates is basically D. Okay, so there is a negative charge over here and there is a positive charge here. Now the question is, find the capacitance, find the field inside, and all those sorts of derivations could be asked. So my logic for this is very simple, guys. Observe, this is your negative charge, this side is your positive charge. Okay, so the negative charge will create an attractive field like this, will create an attractive field like this, and the positive charge which is over here, this positive charge will create a repulsive field like that. It will come outwards like this from that positive charge. Observe this. Now if you observe this diagram carefully, you will realize that in this region and in this region, observe carefully, look at the arrow marks also, look at the arrow marks. In this region and this region, that is outside the capacitor. So this region is outside, this is also outside, this is inside. These two fields cancel each other. Do you see that? Everybody is able to see it. The fields will cancel. Even here the fields will cancel. So I can clearly say that outside the fields cancel each other, because of which the net field outside will be just zero. Outside the capacitor there is no electric field, but inside there will be field. So let's talk about inside. If you look at the arrow marks again carefully, this green arrow mark is here, this green arrow mark is here. Both the fields are helping each other in the same direction. So can I not say the fields add and support each other? So hence the net field inside will be the field due to the positive charge, which will be sigma by 2 epsilon naught, plus the field due to the negative charge also in the same direction, so sigma by 2 epsilon naught. So hence I can say that the field inside is nothing but sigma by epsilon naught. This is a very important formula for the field inside and the field outside of a capacitor. Sigma is the charge density, it is charge per unit area. Okay, fine, Santoshi. All right, fine, welcome. Hi, Pawan, Pampana, welcome, good evening, bacha. This is the field inside. If this is done, let's go to the capacitance formula. Now, what you need to do is, for showing capacitance or finding capacitance, remember Q, the charge on the capacitor, is capacitance times voltage. Somehow show the charge is some number into voltage, that number becomes the capacitance. How do I do that? Well, I have a logic for this. Go ahead with this particular derivation only. So the field inside will be sigma. Sigma is charge by A. Charge by A is sigma into epsilon naught. We also know one more thing. That is, there is some voltage difference between these two plates. There is some potential difference between these two plates, V, and I think the field and potential difference are related. If you recollect, field is rate of change of potential with distance, magnitude wise. So can I not say also the field is nothing but the potential difference divided by the distance that you have traveled, rate of change of potential, dV by dr. So just substitute, what is the voltage difference? It is V. Distance is nothing but given over here, that is d. Interesting. Substitute the value of E over here. So Q by A epsilon naught. So rearrange the terms. So Q will be equal to epsilon naught A. This D is as it is and this V is as it is over here on the top. The reason why I wrote it in this form is because we know, but charge on a capacitor is C into V. So comparing, what are you going to get? Comparing very clearly, the capacitance of a parallel plate capacitor is epsilon naught A divided by D. So that's the capacitance of a beautiful parallel plate capacitor. So field is done, capacitance is also done. Hello Vinay Singhagar. 2022 student, Sankey Choral Music Academy got ISER TVM. I'm so proud. Oh my god, I'm so happy guys. You guys are coming back. One student just came sometime back before. He's like, sir, I got into IIT Roorkee Electrical Engineering, our VN Light student, and now we have Sankey Choral Music Academy. I'm not sure what's your exact name. I'm guessing it's something related to Sankey. Got into ISER. I'm very proud, bacha. I am really happy for all of you, and I'm so glad we were associated at least for some time in this journey on YouTube. Kudos and do well. All the best to all the students who are coming and telling their ranks and telling their achievements. I'm pretty sure the juniors as well will get motivated and inspired from your achievements. Okay, so capacitance is done. Okay, great. So equivalent capacitance in series and parallel. This is the next thing that we need to do. Oh my God, you're going to take physics. All the best, Gacha. Rohit, I'll be making a video on it when the expected dates are. Okay, let's go to series and parallel. These are the last few simple things that we need to do. So let's talk with series first and then we'll go to parallel. So for series, okay, for series, what happens is, if this is a capacitance C1, this is a capacitance C2. If I choose this as my system, this becomes an isolated system. Notice why it is isolated. There is a gap here, there is a gap here. There is nothing that can come from outside or inside physically. So whatever charge is there should be zero. So therefore the net charge on such a thing should be zero. That means if I assume that there is a negative Q charge here, obviously there should be a positive Q charge over here. If this is negative, this should be positive, so that the total charge is zero. And what do we know about a capacitor? The plates which are facing opposite each other, they have exactly equal but opposite charge. So if this is negative Q, this is plus Q. If this is positive Q, this is negative Q. This implies the charges on capacitors, in series is going to be same. Very important. This is a proof of why the charges are same for capacitors in series. It's just based on the charge conservation on an isolated system. I hope this is clear. Now the next important thing, voltages. Voltages won't be same, obviously. This will have some voltage, this will have some voltage. I want to convert this into one single capacitor CS. Obviously the charges are same for capacitors in series. The equivalent capacitor will also have the same charge. If I talk about the voltage on that equivalent capacitance, the voltage on that equivalent capacitance will be also the voltage on the capacitors as a whole, but each one has different capacitance. So because of which they have different voltages. So the total voltage will be voltage across this plus voltage across this. So if this has voltage V1, this has voltage V2, V1 plus V2 is the total voltage. So V will be equal to V1 plus V2. So the potential differences, the sum of it will be the potential difference across the series combination. Is that understood, guys? Come on, guys. I'm taking a lot of pain and a lot of effort for all of you just to do these derivations. I know many teachers, many institutions will skip these derivations or just do it like, okay, see, is there in NCERT this. Half the students don't understand. Students keep messaging, sir, do the derivations. So I'm doing this exclusively for you. So make sure you're showing your full support. Make sure you smash the like button. And also, if you're not a member of this channel, make sure you hit the subscribe button as well. Okay. So what is V? I know this. Q is CV. Q is C into V. So V is Q by C. So why not write this as charge by C? Q by C. This is also Q by C1. This is Q by C2. Q gets cancelled. Do you see that? Q gets cancelled. So I can see that 1 by C is equal to 1 by C1 plus 1 by C2. This can be extended for multiple capacitors as well. Okay, so that was your series. Now let's move on to parallel. Let's go on to parallel. So let me just draw one capacitor here and another capacitor here. Okay, so this is C1, this is C2. In this situation, you can easily notice that whatever voltage difference is there, the potential difference is same for all capacitors in parallel. This capacitance and this capacitance, they have the same potential difference. I hope you guys can see that. Cool? Amazing. So their equivalent combination, so when you combine it into one single capacitor of the parallel circuit, that will also have the same voltage difference. But what will not be same is the charge. So if this has some plus Q1, this has some plus Q2, this is minus Q1, this is minus Q2. If I combine them, you can see Q1 and Q2 will combine, minus Q1 and minus Q2 will combine. This charge Q and minus Q, this Q will be equal to Q1 plus Q2. The charges will add. So charges on all capacitors, the sum of it in parallel is equal to the total charge, on its equivalent capacitor. That is the logic for solving this. Now Q is equal to CV, so capacitance is C, voltage is V. This is again C1 into V, and this is also C2 into V. Voltages are same, so V gets cancelled. So naturally you will get C is equal to C1 plus C2. Exactly what you were expecting. Yes, exactly, Ruchi. Just like you know, in resistors current is same, here in capacitors charges is same when it is in series. In resistors, when in parallel, the voltage is same, here also the voltage is same. That's all. Okay, so will I take problem solving sessions? I'm already doing some problem solving sessions weekly basis. So whenever I'm coming per week, I'm picking up a chapter, and you will see in October the sessions frequency will probably be a little bit higher. So you will see problem solving sessions. Yes, but you need to come and show in full support that you guys are interested in problem solving, not just theory. Come on guys, I'm expecting you guys to see the Pathfinder and Nurture series, okay, which I've done last year. There's nothing different that I can teach. I cannot, again, when I teach series, I'm going to say the same thing, okay? It's not going to be different. Yeah, but the problems, the approaches, tricks, concepts could be different things, which when combined together will give rise to new approaches, new way of thinking, out of the box thinking, and that will help you build your confidence in the exam. Okay, so that's what I want you to do. Okay, yeah, I'm going now to the next one, and that is energy stored in a capacitor. Oh, I think somebody was asking, sir, give a note on the dielectric susceptibility and dielectric constant. So let me probably put it, oh, luckily I have an empty space here, so maybe I can put it here. So I can just say it over here like this. If I have a capacitor, okay, I'm just going to remove this diagram. I don't need this. Just 1 second. Just give me a second. Okay. Yeah. Hold on. I'm just explaining, but just 1 second. So imagine this is a capacitor with nothing in it. So this is the positive plate, that's the negative plate. So let's say this is plus sigma density, this is minus sigma density, because of which there will be some electric field. Now the moment you add some dielectric material, what happens? There will be induced charges in it. So apart from this plus sigma and minus sigma, the moment you add some dielectric medium inside of this is basically your dielectric medium. This dielectric medium will try to reduce the field. What does it do? It tries to reduce the field. So it tries to reduce the field, because of which the capacitance also gets affected. So observe this carefully. How does it reduce the field? By creating opposite direction field. If the external field is here, it creates opposite field. So if plus and negative charges create a field this way, you will see there will be a negative charge induced over here, minus sigma I, and here there will be plus sigma I. These are basically your nothing but induced charges which basically oppose the field. So the actual charges, these are nothing but your actual charges. So the actual charges create a field like this. The induced charges create a field like this. This is because of the induced, and because of which you will see that the net electric field will be in this direction. This is your net electric field, which is basically reduced form. I hope this is clear. Everybody with me on this? Yes, Vinay, I'm trying to explain this only. Okay, the induced charges are opposing the external field. Okay, very cool. Now, if you notice, what is the actual charge on the capacitor now? What is the actual charge on the capacitor now? If you just quickly take a look at what is there on the left plate or on the right plate, what is there on the left plate or on the right plate, you will notice there is actually sigma minus sigma I over here. There is plus sigma minus sigma I over here, and there is minus sigma minus sigma I on the other plate. Check this out. Minus minus becomes plus. So plus sigma minus sigma I minus sigma minus sigma I. That is the new, I would say that is the new equivalent charge. The new equivalent charge on the capacitor. Charge density actually. Charge density. I'll just put it over here. Charge density on the capacitor. If everybody understands this till here, I will go ahead. Everybody has understood, give me a thumbs up. So plus sigma minus sigma is the actual charge density. Plus sigma I minus sigma is the induced charge densities, which are exactly opposite, which opposes the actual field. So the net field is reduced because of the dielectric medium. So the new charge will be sigma minus sigma I on the plates. Dhanush, you have to join the Telegram channel. That's where you will be getting the PDF. Now, here is what I will say. The field which is there, the new field which is there, remember just now I told you the field is nothing but sigma by epsilon naught. It was sigma by epsilon naught. So over here, the only difference will be, the field will be no longer sigma by epsilon naught, it will be sigma minus sigma I by epsilon naught. Everybody with me on this? It will be sigma minus sigma I by epsilon naught. And also I know field is nothing but, just like I did it over here, field is nothing but potential difference by distance. So this E is also potential difference divided by the distance is nothing but equal to 1 by epsilon naught into sigma minus sigma I. Now what do I do with this sigma minus sigma I? The sigma minus sigma I is going to be the new charge, and there is a basic definition, guys. This equivalent new charge of the capacitor, okay, this equivalent new charge of the capacitor is always the old charge or the actual charge divided by K. This K is the dielectric constant of the medium. This is the actual charge density. Here also I should use the word density only. So that is how K has been defined. If originally there was 10 coulombs, 10 by 2, that means 5, will be the new charge. The 2 is a factor which is the reduction factor. How many times has it reduced? If there was 10 coulombs initially, if I divide it by 2, I will get 5. If 10 divided by 4, that means 2.5 coulombs will be the new charge. That 4 is the dielectric constant. Is that clear? Everyone with me on this? So can I not write this sigma minus sigma I as the actual charge density divided by K over here? Just check this out. Sigma by K over here. So that's it. Now you just have to solve the question, okay, as it is. So this will be nothing but 1 by epsilon naught. This K is as it is. This sigma, I can just write it as as nothing but Q divided by A. So rearrange, you will get Q is equal to epsilon naught K into A divided by D, and this is V. So this is Q is equal to CV form. So obviously this whole thing is going to be the capacitance. Capacitance is epsilon naught K A by D. You can also write it as epsilon A by D, where epsilon is the permittivity of the medium, which is permittivity of vacuum into the dielectric constant. This is how you get the derivation for the dielectric medium, which is placed inside the capacitor. The new capacitance is given by this formula. Is that understood, guys? It's a beautiful conceptual thing, and I'm pretty sure you are seeing this also when you are looking at the derivations. Your concepts are definitely becoming stronger. Don't think, sir, this is confusing. No, it's not about being confusing. Your concepts are becoming so strong after looking at these derivations. Okay, I think we can move on to the next one. I think we can move on to the next one. Last two derivations, very quickly we'll go through it. Energy stored in a capacitor. Obviously there is electric field. That electric field will store electric energy. So you have to move the charge slowly. And you will see there is slow energy development in the capacitor as the charges get stored. So when a charge dq is added on a capacitor, okay, across a voltage V, this V will be equal to obviously Q by C, where Q is the charge on it at that time. Then the increase in the potential energy stored is basically the work done in moving the charge dq across the voltage V. So the increase in the potential energy stored is the work done in moving the charge across the voltage V. So the increase in the potential energy, I can just write it as du. The work done in moving the charge dq across voltage is charge into voltage. So the total potential energy stored is integral of du. That means it is integral of dq into V. But wait a minute, the value of the voltage is Q by C. So just put Q by C over here. So moving ahead, U will be equal to, just bring that 1 by C outside. It is integration of Q dq from 0 to the final charge. It's integration. Why? Because I have to add up all the energies. Every time in bringing dq charge from here to here, I'm doing dw work and potential energy increases by du. So slowly I keep on adding the charges. So the final energy stored will be the integration or addition of all of these things. So 1 by C, Q's integration will be Q square by 2. So it will be Q square by 2 minus 0 square by 2 after substituting the limits. So it is half Q square by C. You can also write it as or half CV square also by substituting Q is equal to CV. So one and the same thing. So that gives me the potential energy stored inside a capacitor. I hope this is clear. Hello Bilal. Okay, Roshan Das, can I play the last slide? Roshan, you will be able to get the last slide again, this one as a replay also. Even in a live session you can move it behind, don't worry, and you will also get it in the Telegram. Okay, so don't worry about it. Okay, so one last derivation, guys. Energy density, ready for this? Yeah, you can also write Aarti Kadam as half QV also. If you want, you want to write it as half QV, no problem. You can write it as half QV also. Again, just use Q is equal to CV. So all these things are the same. You just can substitute one with the other. That's all. Okay, cool. So last derivation, that is the energy density. Energy density means the energy stored in the capacitor per unit volume. That is the meaning of energy density. The symbol for that usually is rho u or just u, just like density symbol rho, but this is energy stored per unit volume, so usually it is joules per meter cube. In 1 meter cube, how much energy is stored inside the capacitor? So because remember, capacitor stores energy inside the field inside of it, so how much energy is stored per unit volume, that's what we are trying to find out. So it will be U by volume. Energy stored, I can write it as half Q square by C. I just got this, right? Half Q square by C. Okay, so volume, I can just write it's the area of the plate into the distance. So the area of the plate into the distance will give me the volume between them. So it is area into D. Wait a minute. Now capacitance over here, observe this carefully. This capacitance is nothing but epsilon naught A by D. Epsilon naught A by D, and this A and D will just go over here as it is. Now you can clearly see this D and this D will get cancelled. So the next expression will be Q square by 2 epsilon naught A square. Okay, so why not maybe just write this as Q by A whole square, and then I have just 1 by 2 epsilon naught. What is the advantage? Maybe I'll get sigma. Okay, from sigma can I do something? Okay, I want to get oh yes, I can write it as like this, guys. Observe, this will be Q by A is nothing but sigma, so sigma square by 2 epsilon naught. But we all know field is sigma by epsilon. We just did it some time back. Field inside a capacitor. In case you forgot it, just go back over here. Field is sigma by epsilon naught inside. So why not use that? So therefore sigma will be E into epsilon naught. So I'll just put this as E into epsilon naught whole square by 2 epsilon naught. So this will become half E square epsilon naught square, and this epsilon naught will be here. 1 epsilon will get cancelled, so it will be half epsilon naught electric field square. So that is your energy density, and that's your final formula. That's it. Done. Check this out. See if this is clear. Okay, let's get started then. Now, the first thing is electric field and current. If you remember correctly, in electrostatics, I have clearly told that there cannot be any field inside a conductor. But in current electricity, you will see that there is some kind of a field inside the conductor. The reason for that is that the charges are not static. The charges are moving. That's the reason why there is electric field. You can say that it is not zero. In fact, because of the field, the charges move. Because the charges move, that's why there is current. So if I show that there is an electric field in this direction, remember always electric field flows from high voltage to your low voltage. Then if these are the electrons, free electrons, right? These are nothing but your free electrons. The force on those free electrons won't be this way, it will be this way. Think about it. Why the force will be this way? Because it is a negative charge. It's a negative charge. So the force will be in this direction, because of which the motion of the electrons will be in this direction. But since the charges which are negative are moving towards the left side, where will the current be? The current will be exactly opposite. In fact, in the direction of field only. So you're going to see the current will flow in this direction, because current is assumed to be the net flow of the positive charges, the rate of flow of the net positive charges, right? Yes, Varsha, definitely you can, bacha. Hi, Ritikavadi, Sanjay, welcome, bacha. Is this diagram clear? The field goes from high voltage to low voltage. The force on a negative charge acts exactly opposite. So since the negative charges go here, it's as good as saying the positive charges or the current is flowing in that particular direction. Now, How are these things related? Let me just give you a quick intro over here. Remember, resistance is given by, proportional to the length by area, and that constant of proportionality is rho, which is just called as resistivity of that particular conductor, the resistivity of that particular conductor, correct? And as per our Ohm's law, we know the voltage difference. Remember, this is high voltage, this is low voltage. Obviously, there is some kind of a voltage difference. This voltage difference is current into resistance. So I know I can put the value of resistance from here. So just import this value. It will be rho L divided by A. Is that clear, everybody, till this point? Everybody with me? Very good. Good evening, Creations, Ananya. Yep. Welcome. Yes, NDA aspirants too can watch it. This is for all competitive exams. JEE, NEET, NDA, doesn't matter. Olympiads, everything. Bring this L below. Bring this length below. So V by L is equal to, what is current by area? If you remember the definition of current density, you will recollect that current density is how much current flows per unit cross section. So strictly speaking, I can just put this value of I and A together, and this resistivity also I can do one thing. I can write it as 1 by conductivity. Remember, resistivity is inversely related to conductivity. More resistance, less conductance. Less resistance, more conductance. So this sigma is nothing but called as the conductivity. This is called as the conductivity, right? Now what is V by L? The voltage by the length is dV by dr. The rate of change of voltage with respect to distance is nothing but the electric field. So this is nothing but your field. This is nothing but your current density, and this sigma is right over here. So rearranging the terms, bring this sigma over here, you will get J is equal to E times of sigma. This is a very important relationship. It tells you what is the current density in terms of the field and the conductivity, or even the resistivity. You can bring sigma on the other side. Sigma on the other side, it will become resistivity. So you can also write this same expression as E is equal to rho J. It's one and the same thing, guys. It doesn't matter, because if you bring sigma over here, 1 by sigma will become the resistivity. Is this clear? Everybody with me on this? Everybody has followed through this derivation? Give me a thumbs up, then I will go on to the next derivation. So what are the key steps of this derivation? 2 steps are there. First, resistance. Second, Ohm's law. Once you get through Ohm's law, rest is just simple manipulation. Current by area is current density. V by L is nothing but the field. So this J, remember, is your current density. Current per unit area. Current density. Okay, this is what I have written this I by A as. Fair enough? Awesome. Let's move on to the next one, and that is the expression for the drift velocity. Some of you might know certain derivations, some of you might have forgotten, some of you are completely unaware. So guys, doesn't matter, watch the session, it will be definitely helpful. And yes, you need to go through the other theory parts, because the theory parts I have covered it in the Pathfinder series. Please watch that, okay? There you will get the other theories. Here I'm exclusively focusing only on derivations, okay? Because I'm expecting you guys to know the other terms. Now, in case of drift velocity, so here is what we are going to do. These electrons collide randomly, they go here and there, and slowly they start moving from one side to the other. They slowly start drifting from one side to the other. So that speed with which they slowly move, because of the electric field, because of the voltage difference, that is called as the drift velocity. So just imagine this. Just imagine this. You have a conductor over here. You have a conductor over here. There are lots and lots of charges in it. There are lots of electrons, charges, whatever you want to call them. There are these electrons, charges. Slowly they are drifting with some velocity like this. Okay. After some time, all these electrons will get flushed out. Just imagine, after some time, all these electrons will get flushed out and new set of electrons will come in. Visualize this scenario. So I'm just going to show a time snapshot when all these electrons would have just come out. All these electrons would have just probably come out over here, something maybe like this. That's it. And the new set of electrons would have come inside. The new set would have come inside. This happens in a time interval of, let's say, delta t. So right from here till here, this happens in a time interval of delta t. And these electrons, if they have got flushed out, obviously they have traveled the length of the conductor. The electrons have definitely traveled the length of the conductor. Everybody agrees with this? Hello, draw and roll. Nice to see you back, bacha. Everybody following this? If these electrons come out, if the length of the conductor is L, these electrons would have traveled L distance. With what speed? Vd speed, which is the drift speed. Okay, Meenakshi, delta t is the time for the charges to cross the conductor, to cross that particular conductor. This conductor, to cross them, how much time interval they have taken. I hope, Meenakshi, that is fine. Varsha, right now we have started with hybrid in 1 or 2 cities, that's it. And maybe in the years or months to come we will start more, but right now we are completely online, bacha. Okay, so next thing that you need to realize is that current is nothing but how much charge flows upon how much time does it take. Current is how much charge flows upon how much time does it take. Also, the drift velocity, the speed with which they move, is how much distance they travel, that is L, in how much time interval that they take, that is also delta t. So I know, now I have got some nice idea, maybe I can divide both of them. The moment I divide, I know delta t and delta t will cancel. So let's just divide both of them. So I'll get current by the drift velocity will be the charge divided by the length. Is everybody clear about this? Awesome. Now, moving this drift velocity over there, what I will get? I will get this as charge into the drift velocity, the whole thing divided by length. But I'm not so happy about this equation yet, because this charge is something which I do not know. I need to do something about it. So here is what I'm going to do. How much charge was there in it? How much charge was exactly there inside of this? So that I can easily calculate. The charge inside of this will be nothing but the charge per unit volume. If I know the charge per unit volume, maybe I can multiply it by volume to get the total charge. But I don't even know the charge per unit volume. There is something else which is generally given or can be easily found out, and that is how many charges are there per unit volume. Not the charge, but the number of charges. So just imagine if I write the number of charges, how many ever charges are there, into the value of each charge. Each one is E charge, which is 1.6 10 to the power minus 19 coulombs. So if I multiply by E, I will get the total charge. I'll get the total charge. All right. But remember, I can also write this total number of charges as the number of charges per unit volume into the volume itself multiplied by E. Just check this out. If I divide by volume, I have to multiply by volume also. And this is a number which is generally known to you. That is nothing but small n. Volume is nothing but area into length. And this is nothing but E. That is nothing but your charge. N is the number of charges which are there per unit volume. Maybe 100 charges per meter cube. Volume is obviously volume, area into length, and electron charge. So how about substituting that over here? I will get this as N A L into E, rest of the things as it is, drift velocity as it is, length as it is. You can clearly see that the value of length from here and here just gets cancelled out. So I'm just left with current is equal to N. I have Vd also, I have electron charge also, and area also. That's it, guys. That's the value of your drift velocity in terms of current. If you know the current, if you know the charge, obviously you know it. Area, if you know it, you know the number of charges per unit area, per unit volume, you can find the drift speed, or if you know the drift speed, you can find the current. Very important relationship. Current is NVIDIA. It's the name of a graphics card company, NVIDIA. So you can remember it. Current is NVIDIA, the graphics card company. I hope this is clear. Hi Rajeshwari. Yep. So Ghost, I'll help you bacha in some strategy sessions that I'm going to come up in the next few days, few weeks. Don't worry, just stay tuned on the channel. Alright, Ghost Gaming? Cool. So this was another important derivation. If you have noted it down, if you have followed it through, maybe it's time that we move for the next one. Now the next one is conductivity and relaxation time. Okay, this is also very important, tricky kind of derivation. Many people skip or they do not really understand. That's why they end up skipping or just losing marks. So what happens is, whenever these electrons move, they do not move with uniform velocity. They get propelled or accelerated because of the field or the potential difference, but then they collide and then they again lose the velocity and again accelerate, again collide, lose the velocity, again start. So this keeps on happening. So just imagine this. Just imagine an electron which is there. I'm just worried about the motion in the direction of the current. The other part of the motion I'm not really bothered. Just think of it this way. An electron just after collision might have some velocity u, and then what happens is it gets accelerated, and after some time maybe it gets some new velocity, let's say v. Maybe it gets some new velocity v, and then again what happens is, again over here it collides, and again the same electron starts with a new velocity and again it gets accelerated and again it collides, and this process continues. This process continues. Collides, loses the velocity, again accelerates, again collides, again this same thing is going to continue. Now, can I find the acceleration? I think so. We can easily find the acceleration. So acceleration is nothing but the electric force upon the mass. The electric force is nothing but the charge into the electric field, mass of the electron. I will assume it as m. Now this time from one collision to next collision, so here also maybe a collision would have occurred. Let's assume that time as small t. This is the time between collision, the time between your collision. Everybody following till here? Hello Ashrita, I am from right now in Bangalore. Okay, yes. So Senthil Thorsarella, yes bacha, tomorrow I'm going to have a session for strategy for JEE 2023. Yes, at 7 o'clock. Okay, all right. Now here is what we are going to do. We are going to use kinematic equation, right? I think kinematic equations are applicable. Acceleration is there, so let's use kinematic equation. So as per the kinematic equation, so using our kinematic equation, can I not say V is equal to initial velocity is nothing but u plus acceleration. Acceleration is nothing but E by m. All right. Oh, but wait a minute. This charge is actually negative. The electron charge is negative. So, I think I should put a minus sign when I put a vector symbol over here. Okay. So I should put a minus sign only because I know the charge is negative. Magnitude wise, it is nothing but E by m. I hope this is clear. And into, I'm just going to put T over here. Now this is basically an equation for any electron between your collisions. Between your collision. Now, if I take the average, what will happen? If I take the average, like for example, if this is for, let's say, the first electron, this will be V1 is U1 plus EE by M into T1. For second, it will be V2 is equal to U2 minus EE by M into T2. So like that, for every electron, there will be some velocity, initial velocity, and there will be some time from one collision to other collision. What if I take the average of them? What if I take the average of them? Varsha, Ashita, concentrate bacha over here. If I average them, now if I'm averaging, now the symbol for averaging, I don't know whether you know this, is basically this triangular brackets. So whenever I put a triangular brackets, it means it's average. So if I put F and the triangular brackets, it means the average of the force. If I put P and this symbol, it's average momentum. So if I put that, average velocity is equal to, final velocity is equal to average initial velocity, and this E by M is a constant, so it will not come in the average. The average of a constant is a constant, so don't even bother showing that. And over here, I think I'll just have probably this average of time. I'll tell you what, this average velocity with which it goes is in fact nothing but your drift velocity. Think about it. The average velocity with which it goes from one side to the other side is nothing but your drift velocity. So I'm just going to put this as your VD. That's it, is equal to, okay, the average velocity with which it moves finally after getting accelerated is your drift velocity. Now here is the thing, U is nothing but the velocity after the collision. After every collision, the particle, the electron might go in random directions. So when you think carefully, for all the electrons, one electron might go here, one electron might go here, one electron might go here, another electron might go here. So all the electrons are going in different directions. That means the average velocity, not speed. Speed will be something, but velocity will be 0. So just after the collision, I would say the average velocity will be 0, guys. Just check this out. Just check this out. Everybody agreeing with this? Because after the collision, each velocity of that electron might be in different directions. So that's the reason why the average will be 0. Okay. Now this over here, minus E by M, the average interval from one time to next time, that has been called as the nothing but the relaxation time. So this is having a new symbol. This is called as nothing but your relaxation time. How much time it takes on an average to it relaxes between two successive collisions. It collides and then it collides again. Between those two collisions, on an average, how much time it relaxes. That is nothing but your relaxation time. So hence, I will basically get your drift speed magnitude as nothing but E by M into the time period. This is another formula for your drift velocity, guys. Very crucial. I hope you guys understood this. Instead of red color, we please use green color. Okay, fine, Dhanya. Sure. Definitely. Okay. Is this clear, bacha? Is this clear, bacha lo? All right. Everybody with me? Okay. So here to here is the critical part. Yes, creations or units. This velocity on an average. One electron gets this speed, one electron gets this speed, one electron gets this speed. On an average, it will tell me with what average velocity they are moving. That is how quickly they are drifting from one side to the other. That's why the average of this is drift velocity. Average of this velocity after collision. After every collision, each electron might move in all random directions. So when you have random probability, randomness, the average will be 0. Because each direction is equally probable. Remember, this is vector, so vector's average will be 0. And the times average from one collision to the next collision. It collides, then it is relaxing. Okay, now again it collides, and again it relaxes, again it collides. So that average interval is basically called as the relaxation time. I hope this is clear. All right, everybody. Now here is one important thing that I'm going to do. Just hold on, guys. There's one important thing as well we need to do over here. I'm going to use this equation with this equation. So from here, look what VD is, but from before, observe carefully, but from your previous slide, look over here, VD is current by NEA. VD is current by NEA. So let's use that. VD is current by NEA. And this is also equal to this entire thing. So it is nothing but EE by M into your relaxation time. So now let's play around with this. Let's see if something gets cancelled. No, nothing is getting cancelled. But current by area is remaining over here. Let me just keep it as it is. This small e into this small e is E square. And I will also have N over here. This capital E is also there. Okay, this tau is also there. And this M is also there. Okay, and area has just been kept over here. E into E, E square. N as it is. E as it is, tau as it is. Current by area is nothing but your current density. Then this E I will just keep it over here. And then this will just become N E square tau by M. Now I'll tell you what. Look at this equation and compare it with this one. Compare it with this one. J is sigma E. J is sigma E. So look over here. J is sigma E. So what should this value be? So comparing, guys. Comparing with what? Comparing with current density is sigma, which is conductivity into E. What will I get? The conductivity of any material is nothing but N E square tau by M, which is also 1 by your resistivity. So this is also a very important formula. Very important formula. In fact, think carefully what we have done, because I said that over here, this part is just like your conductivity. I have in fact proved this equation, and this equation actually came from Ohm's law. So if you go reverse, actually you prove Ohm's law. I will repeat. I did all of this without even knowing Ohm's law. Nothing, okay? Without even knowing Ohm's law. This was using basic kinematics and mechanics, forces, Newton's laws. So here I got current density is sigma into E, or current density is something into E. So this is the exact same thing which I got over here. This is the exact same thing which I got over here. So if I go reverse, what will I be able to get? Ohm's law. So this is actually then the proof of your Ohm's law. I hope this is clear. Everybody with me? Everybody understood? These are important equations. This will come in mains, this will come in NEET, this will come in boards. If you get this derivation, please do this. Guarantee marks, rather than trying something very new question which you do not know, or maybe some case study. Okay, so let's move on to the next one. So conductivity and relaxation time done. Now let's move on to mobility. Mobility has been defined as how easy it is to move these charges for an applied electric field. So the ease of the charge carriers, ease of the motion of the charge carriers, for a given electric field. Now the symbol of mobility is nothing but mu. It is nothing but how mobile it is, that means drift speed divided by the electric field. So mobility has been defined as the drift velocity by E. Now you can also do one thing, drift speed, I just got it over here as EET by M, So just put it over here, EE relaxation time by M. This E as it is, EE cancels. So I'll get this as E tau by M is nothing but mobility. So this is also a formula which is there in your NCERT. Just check that out. Yes, this will be useful for EMSAT. Definitely, bacha. All CETs, all need exam, all NDA exams, whatever exam you are preparing for, it is going to be useful. All these formulas are going to be there. And trust me, and you can also probably vouch for this, when you know the derivations, it's easier to remember the formula because it's there in your head. And not just seeing the derivation once, if you know it in and out, trust me, you will easily remember the formula. You don't have to make too many efforts, or you don't have to struggle for watching videos how to remember formulas. You won't struggle so much. Agree or disagree? Okay, so I hope this is clear. So let's move on to the next one, and that is electrical power. Yep. Very good. Let's move on. How many marks, sir, for this? This, if mobility comes, I think it will be for hardly 2 marks. Yeah, but if this comes, this one, this will come for 4 to 5 marks at least. 4 to 5 marks. Okay? Quite possibly 5 marks only. Okay, if the derivation comes, prove Ohm's law or show that current density is related to the field in terms of relaxation time and all of that, then obviously it will be for 5 marks. Okay, so now let's move on to electrical power, guys. So imagine that we have a conductor and the charges are moving from one side to the other. There is a potential difference. This is your potential difference. There is a potential difference. So when a charge Q moves from one side to the other side across a potential difference, what happens is the potential energy gets converted into the kinetic energy. Obviously a charge is accelerated. So what happens when you accelerate a charge? It will obviously change its potential energy. And that change in the potential energy is converted into kinetic energy. So can I not say, in fact, that because the charged particle gains kinetic energy, can I not say the loss in the potential energy goes into the gain of the kinetic energy, which in turn goes as your heat loss, because it is your thermal energy. These electrons, kinetic energy will knock something that will start shaking, vibrating, motion, rotation, and that comes as your thermal energy. That means your heat energy. Agree? Disagree? Yes? Oh my God, Dhanya, for this question I got 5 marks in the examination. Very good, very good. So I'm pretty sure these 5 marks are in your pocket, guarantee bacha. So how much is the loss in the potential energy? The loss in the potential energy is the charge into potential difference. I hope you know this formula from electrostatics. It is nothing but how much charge you move multiplied by your potential difference. So charge that has been moved is Q, potential difference is V, the heat energy developed is nothing but H. Okay, now can I not write charge as current into the time? So can I not write charge as current multiplied by time? So into V is equal to H. Now bring that time over there. So H by T will be voltage difference into current. The heat developed per unit time is nothing but the energy loss per unit time, which is power. The rate of energy is power. So this is power is equal to voltage into current. Not just this, guys, observe carefully. Because power is voltage into current, I can use Ohm's law, and instead of current, I can use V by R as well, because V is IR, so I is V by R. So I'll get this as V square by R. Or you can even do this. Power is equal to voltage is current into resistance into the current. So it is also equal to I squared R. So hence, in general, I will get power is voltage into current, which is also I squared R, which is also V squared by R. So this is the derivation of the power loss or heat loss formula. V into I squared R, V squared by R. Concept is clear. When I do sums is difficult, Abdul Malik, that means you need to start with easy problems. You need to do H.C. Verma, short answers, then objective one. You need to check solved examples and then watch some teachers solving these examples. Could be any book, doesn't matter. And then you slowly start with easy and then go to medium, then go to previous year mains, then go to some other things. Or if you are preparing for NEET, start with easy, then medium, then go to your NEET exam level paper. Okay. Smiley Queen, I'm not sure, bacha, but this chapter for sure is very important for all the exams, be it NEET, be it JEE. In every exam, this question, this chapter 100% comes. Not just one question, most likely 2 questions. Okay? Chalo, let's move to now series and parallel. This is a slightly easier derivation. So resistors in series, resistors in parallel. Let's do this quickly, guys. So when you have 2 resistors, basically in series combination, what happens is that the current through both of them is same. Agree, disagree? Current through both of them is same. This is R1, this is R2. So you can also see that the voltages won't be same because the resistances could be different. But the total voltage will be voltage across 1 plus voltage across 2. And V1 is current into that resistance. The current into that resistance. And V2 is the current into that particular resistance. The total voltage which is there, I can say, is the total current, which is I, into the equivalent resistance, which is Rs. I cancels. So resistance in series is nothing but R1 plus R2. This is the proof of this. Proof of your series part, guys. Okay, so for series, Rs is R1 plus R2. It comes because the total voltage is individual voltages addition and current is same. Moving on for the next one. Let's do this one. So here, the current obviously gets divided as I1 and I2. But what is same across both is the voltage difference. So here, I would say the current is I1 plus I2. Now, if you look I1, here, this voltage, the voltage across this resistor is current into that resistance. The voltage across this resistor is current into that resistance. So I can say I1 is V by R1, I2 is V by R2. Also, if I combine them as one single resistor, I can also say the total voltage is current, the total current, not I1, I2, into the equivalent resistance. So I can write current as V by nothing but RP. V cancel, so 1 by RP is 1 by R1 plus 1 by R2. You can see the derivations are very much similar, except for the fact that what is being added. Here in series, voltages add. Here in parallel, the currents add up to give you the total current. That's it, as simple as that. Abdul Malik, MTG physics for NEET? Well, kind of enough, but you also need to do previous year questions. Okay, just doing MTG will not be enough. You have to do lots and lots of previous year questions. Okay. Hello Srijit, welcome bacha. Okay. So how about this? The cells in series and cells in parallel. You might have seen this in your NCERT books. How about this? Shall we do this also? Okay, let's try to do this question. So here, what do we have? Many cells in series. So maybe you can just take 2 cells for now and we can prove it. And there is some current flowing, there is some external load. The question generally happens to be like, what is the equivalent EMF or equivalent resistance, or you use that to simplify the circuit. So just imagine you have a battery with some internal resistance R1 over here, and again over here you have another battery with some internal resistance over here. I can say that across this battery there is some voltage V1, across this battery there is some voltage V2. Combine them, both of them together, you will get the total EMF, and I can say it becomes your equivalent battery's EMF and equivalent battery's internal resistance. These two together give you one single battery which has equivalent EMF ES and equivalent resistance RS. How do I combine both of them together? Observe carefully now. Observe carefully now. Can I not say the total voltage across both of them? Okay, so just 1 second. If I say that across this one the total voltage is V, can I not say it is nothing but V1 plus V2? The total voltage is nothing but the voltage across this EMF. Yes or no? Oh, that's more than enough, Abdul Malik. Ruchi, the temperature dependence of resistance is not exactly a proof, it's just a phenomena, it's just like a conceptual question, give reason type. So that will come like a give reason. Okay, if the temperature increases, then what happens? The collisions are more frequent. The collisions are more frequent because the thermal energy increases, and because of which the resistance increases. So that's a logical explanation, not a derivation as such. Okay, Ruchi Bacha? Okay, so here I'm more interested in the derivations, not in the the questions, give reasons, because then that becomes limitless. You can do so many things like that. Okay, so now the total voltage is the sum of these individual voltages. Now what is this voltage equal to, and what is this V1 and V2 equal to? Well, V1 I think is nothing but if there is some kind of a current inside of this, if there is some kind of current which is flowing inside this, we know the terminal voltage, recollect, terminal voltage across a battery is nothing but the EMF minus the current multiplied by the internal resistance. Internal resistance, you might have seen this always, EMF minus IR when it is getting discharged. So how about using the same thing over here? V1 will be E1 minus IR1, that's V1, and V2 will be E2 minus IR2. Okay, and this V will be nothing but ES minus IRS. So this will now become E1 and E2, I can bring it together. So it will become E1 plus E2 minus current, I can take it common, and I will have R1 plus R2 over here. And over here I have ES minus IRS. Now that's the end of story. You just have to compare now. You just have to compare now. Hello Anu Akash. Just look at this. Just compare this term with this term. This term with this term. Look at this. E minus IR, E minus IR. Very, very similar. So from this clearly it is seen the equivalent EMF in series is just the addition of the EMF E1, E2, E3, and the internal resistance of the equivalent cell is just like in series R1 plus R2 plus R3. That's it. That's the formula, guys, for your equivalent EMF in series. Is that clear? Can we move ahead to the next derivation, bachalo? Okay, let's move then. Okay. Now obviously you should expect we will do parallel now. Let's do this parallel part as well. It's not that difficult. So again, over here we have this battery E1. Maybe there is some kind of internal resistance R1. This battery is E2. Maybe some internal resistance, let's say R2. Okay. But in parallel, what will happen? The currents won't be same. Currents will get distributed. This will have some current I1. This will have some current I2. If you combine them into one single cell, that single cell will look like this. RP is the equivalent resistance, EP is the equivalent EMF, and the total voltage is the same. But the current, very, very important, guys, very crucial. This current I is going to behave as if both the currents are together. So can I not say I is equal to I1 plus I2? Just simple Kirchhoff's current law, the currents merge at that junction. Pupti sir, yes, you are very late, bacha. Captain नाम मार्वल से इंस्पिरेशन मिला क्या पता नहीं यार हो गया I don't even remember how I got the name the captain. It just happened. I didn't think of it, I didn't plan, it just happened. I think I used to talk about aeroplanes or ships and all of that, and slowly people started calling me captain, so I thought okay, fine. So for JEE and MSAT, NCERT and HC Verma is more than enough. JEE and MSAT, HC Verma, NCERT, no, it's not more than enough. You need to do PYQs, bacha. Yeah, for JEE, and it depends. You're talking about JEE means, yeah. JEE Advanced, no. Okay. Now, what can I write current as? Just use the same definition like before. Yeah, I can do something over here. Observe now what I'm going to do. All right. In general, your terminal voltage is E minus IR. So I can say V, or rather E minus V is equal to IR. I is equal to E minus V by R. Interesting. I can write current as E minus V by R. So let's use that over here and see what do we get. So I1 will be E1 minus V by R1. That's I1. And I2 will be E2 minus V by R2. Great. I'll take E1 by R1 and E2 by R2 together. So E1 by R1 plus E2 by R2, I'll take it together. Minus V is common. And I have 1 by R1 plus 1 by R2. Great. So that is equal to the current. Bring these people over here. Or I can just say, okay, and bring I over there. Cool. So this will become V into 1 by R1 plus 1 by R2 is equal to E1 by R1 plus E2 by R2 minus I. Divide it over here. So V will be equal to E1 by R1 plus E2 by R2 whole thing upon 1 by R1 plus 1 by R2 minus this current divided by this whole thing over here again. So 1 by R1 plus 1 by R2. Now I'll be like, okay sir, why did you do it like this? Why did you do it like this? I'll tell you why. See over here, compare this equation with this equation. This equation with this equation. V is E minus IR. E minus IR. So if you compare them, you will understand that this term is similar to this term. So from this I will get the equivalent EMF in parallel is E1 by R1 plus E2 by R2 by 1 by R1 plus 1 by R2. So that is one of the formulas. That is one of the formulas. Also notice one more thing. This R is 1 upon this. 1 upon this. This R is 1 upon this. Everybody agrees? Just compare. So let's see what do I get then. So I will get basically, over here R is equal to 1 upon R1 plus 1 upon R2. Just flip it guys, or just take this here and bring this over here. You will see this is 1 by R1 plus 1 by R2 is equal to 1 by R. Oh, that means the equivalent resistance in parallel is just like your parallel circuits, 1 by R1 plus 1 by R2. So that brings you to the final formula. That's it. So that's what I have done, guys. Is that clear, guys? So I have compared this with this over here. Just compare. Harshad, happens. Many students have told me this, and it's not just with me. I'm pretty sure it would happen with any teacher whom you're following at a 2x or 3x. And I'm so happy that you are able to understand my lectures at 2x. That's good. That's good. Great. Usually students are like, not to me, but in general, sir, please slow sir, I'm not able to understand sir, you are very fast sir, my brain is thinking at half the speed you are talking sir. But it's good that you are watching it at 2x speed. No problem. Okay. Okay, great. Even Juhi agrees, sir, 2x is good. Okay guys, but I'm not going to talk very fast, because then some students will be like, sir, I watched your lecture at 0.25x or 0.5x speed, sir, because you're talking so fast, I couldn't understand anything. So I'm just maintaining the averages, law of averages, guys, always. All right. All teachers we are seeing in 2x. Okay, no problem. It always saves your time. But yeah, live lectures, the fun is only different. And it's sometimes good to watch the live lectures also. You know? Okay, let's come to Wheatstone's bridge now. Yeah. Wheatstone's bridge, what say? Let's go to the Wheatstone's bridge. Okay. So in Wheatstone's bridge, what happens is that your current gets distributed, but it does not flow through this middle thing. This G is Gadha, donkey, it could be anything, monkey, donkey, anything. This device will not allow any kind of current. So whatever current comes in over here will get divided as I1 and I2, this will have no current. So the same current just goes as it is, and this current goes as it is as I2, and this galvanometer, that's it, no current, no current. Okay, so I can say that when Wheatstone's bridge is balanced, then I can say that there is no current in your galvanometer. So there is a peculiar ratio. We can do that now very easily using your Kirchhoff's laws, voltage law. So let's say I start from here, go like this and come back over here, use KVL, use Kirchhoff's voltage law for what parts? R, G, P. From R you go to galvanometer and then you come to P. Okay, so this is what I've done. R, G and P. So here there is a voltage drop of minus I2R, and galvanometer there is no current, so no voltage drop at all. And here I'm going against the current, so I should put a plus sign. It will be I1 into P is equal to 0. Bring these people over there, so it will become I1P is equal to I2R. So dividing, I'll get I1 by I2. I1 by I2 is R by P. Now I can also say similarly, using Kirchhoff's voltage law, for this part, that means from X to Q to your galvanometer and back, you will see a similar relationship, but here I1 by I2, I think it will be Q by, it will be nothing but Q, sorry, it will not be Q, it will be basically X by, it will be nothing but X by your Q, X by Q, that's what it's going to be. Now from these two, from this equation 1 and from 2, so from 1 and 2, what you're going to get, because I1 by I2 same, you're going to get R by P is equal to X by Q. That's it. This is the condition to balance. This is the condition to balance a Wheatstone's bridge. Is this topic Wheatstone's bridge important for any competitive exam? In JEE, there have been many instances they ask questions on this particular part. They give you a complicated circuit and you will see that it is actually balanced. So many resistances just get eliminated. Then it becomes simple series and parallel combination which you can solve easily. I'm not saying it will come, but it has come many times. That's what I will say, creations of anonymous. Okay, so I'm not doing this part again because it's exact repeat, but you will get this, okay, when you solve. In fact, you will see meter bridge is also based on exactly the same concept of Wheatstone's bridge. This Wheatstone's concept, how is it used over here? Observe, there is a known resistance. I'm just going to call this as the known resistance. This one over there is basically your unknown resistance. This is your unknown resistance. Then you have a meter bridge. Meter bridge means obviously the whole length is 1 meter or 100 centimeters. And then you have some length called as the balancing length. You have some length L as the balancing length, usually called as balancing length, where you get null deflection. Null deflection means no current will flow through the galvanometer. This circuit is exactly similar to this circuit, except for the fact that instead of seeing those resistors physically, what you have is this wire which is having a lot of resistance. This part over here is like this resistance, and this part over here is like this resistance over here. So these two resistances are actually combined together over here as this potentiometer wire. So you will see, using your balancing condition, this R divided by your X comes out to be this resistance by this resistance of that L part upon resistance of that 100 minus L part. And since we know resistance is directly proportional to your length, you will see that this is also equal to length by 100 minus L. So this is how you get that, R divided by X. From this you can find the unknown resistance. From this you can find the unknown resistance. Is that clear? Yes, Tanish, bacha, it is definitely useful for JEE. If you know derivations, you can get really amazing marks and you will not forget the formulas and you will understand the concepts deeply. So if you want 70, 90 percentile, then don't watch this lecture. If you want 90 percentile, 95 percentile, 99 percentile, slowly you want to push yourself towards higher percentiles, then only watch this video. Okay. Okay. Harshad Jagtap, delta star method of solving questions is not needed. So I have seen so many teachers, so many coaching institutes teaching students of 11th and 12th standard poor things, you know, teaching delta star transformation. I remember I learned delta star when I went to, I think, first year, second semester. And they're like, oh, nice, this is cool. I could have solved one problem, you know, from JEE. Then I realized that there was no question in the history of JEE Mains or even JEE Advanced which should be solved using delta star, or basically, you know, the problem becomes very simple using delta star in the history of JEE Mains or even JEE Advanced. So they know what is the limit of the syllabus. They won't give you stuff which is there in engineering. They have saved it peacefully. Those same IIT professors will ask you the questions when you go into electrical or mechanical or whatever engineering you have taken in first, second year. In JEE, they will not ask you. They will test you on what you know. They'll ask you simple question on Ohm's law only, conceptual question on maybe Kirchhoff's law. There only you will get stuck. So don't fall into these traps of learning delta star and so many other transformations which are not asked, not important, not even needed, and not even there in the syllabus. All right? I hope this is clear. Okay. Chalo. Let's move on to now magnetism. So we are now going on slowly to this chapter, chapter 4. Chapter 4. All right. Chalo. Let's move on. So, oops, yes, there we go. So the first derivation is usually in the force on a current carrying wire. Okay, how much force is basically there on it. So for that I have taken a simple wire which is carrying some current and it is placed in a magnetic field. If you take the zoomed in version, if you magnify it under the microscope or if you just see it under the lens, it will look something like this. There is this small element of the wire which has some current. The length of the wire may be DL, L, whatever you want to call it. The electrons or the charges are moving with VD, drift velocity. There is magnetic field also over there. If a charged particle experiences magnetic force while in motion, even current carrying wire has moving charges, so hence that should also experience force. I hope this is clear. So here is the thing. A moving charge experiences a force like this, Q into V cross B. So same way, if this charge is nothing but your electron, this velocity will become your drift speed. This velocity will become your drift speed and this force will become the force on the wire. So hence the force on that particular wire will be E into drift velocity into B. Okay, cross. Great. Now here is what I'm going to do. I think I know the formula. I know the formula of the drift velocity. So I'm going to use that. But also there is one catch. This Q is not just E, guys. It should be the total charge. It should be the total charge. Because if I just put E, then it shows me the force on any one charge. But there could be so many charges inside it. So I need to be little bit careful over here. So maybe it is not just E over here. I need to put something else. What will that something else be? Think about it. How much charge will be actually there inside of this? The amount of charge that will be actually there inside of this will be number of charges, the number of charges per unit volume, number of charges per unit volume into into each charge, which is E, into volume itself, Think about it. Number of charges by volume anyways get cancelled. So number of charges into E will give me the total charge which is there inside of this. Everybody agrees? Nandani, galvanometer to voltmeter, ammeter, that is not exactly a derivation, bacha, but still, okay, if you want to understand the concept, okay, I'll tell you what you can do. Just 1 second. In this channel itself, so what you do, okay, I'll tell you what you should do to understand the concept. Just search for voltmeter or something like that. Okay, so you see this galvanometer, ammeter and voltmeter. Okay, so just watch this class so that you understand the concept behind it. It's not a formula. In fact, even in this lecture, right, I have told my students, don't by heart any formula. Lot of students just try to by heart some formula for voltmeter and ammeter, and that's why they are not able to solve. You try to fit in those terms because every time the question might come in a slightly different manner. So please do not by heart that galvanometer, ammeter, voltmeter conversion formulas. Okay, watch this class. Trust me, you will be very conversant with that particular chapter. Okay, I hope that is clear. Okay, only that particular topic. Okay, it's not a derivation. Alright, Pupsari, you have basically my class, rotational motion. Pupsari, just go to nurture series, it's there in the playlist, entire system of particles. But start from center of mass, don't directly jump to rotation. Start with center of mass, then go to momentum and then go to rotation. It will help you. Okay, watch that and then also watch my one shot. Trust me, you will get a good level of understanding in rotational system of particles and all of that. Okay, bacha? Cool. Sari, is that right? Okay, little bit difficult for me to pronounce. Yeah, thank you. Okay, I'll probably come to that creations of Anonia towards the end. Okay, maybe let's go with the derivation now, right now. So what will this be equal to? Number of charge carriers per unit volume is small n, electron charge is E, volume is nothing but area into the length of it. So that is nothing but your charge. So maybe I can put that over here. So that is nothing but N, E, A and L. So it should not be E, it should be the total charge in it. So I'm just going to put N, then E, then A, then L, and then VD is also there over here, and then B. Oh, I remember this. N, VD, N, VD, and this is L and this is B. What is this? Current is NVIDIA. So this is going to be I and this is L and this is B. That's it. If you want to put the vectors, it is cross. So that's the force acting on a current carrying wire. You should know this. Okay, everybody with me on this? Cool? Excellent. So this I have done because since current is NVIDIA, that's all. So this is another important formulas derivation. Moving on now to the next derivation. Wow, we have the velocity selector. Now some of you will be like, sir, what about that formula that R is equal to mv by qb or time period 2 pi m by qb? I don't think you should think of it like a derivation. It's very easy. First of all, circular motion concept, mv square by R is equal to qvb. It's simple, number one. Number two, I think I have done that in my regular classes also many times. So I don't feel the need to do it over here, but still if you feel like watching that part, which is there like a small paragraph, you can definitely watch the helical motion and circular motion concept in my Pathfinder series. Okay, so I'm just avoiding that because I don't think it is so important. Although application wise or formula wise, it is very crucial for solving problems, which I have already done in my Pathfinder. So let's look at velocity selector. So in this velocity selector, what happens is you throw those charged particles. With different states under the influence of electric and magnetic field, and certain particles with certain low speed go one way, with high speed go the other way. A particular speed exactly goes undeflected onto the other side. If you have a small hole on the other side, then those particles with a particular range or a particular velocity only will come out because there is a hole. all other particles might just go on to the other sides. That is the reason why it is called as a velocity selector. Now I know you guys are thinking, sir, why would lower speeds go one way, higher speeds go the other way? We'll talk about it. Okay, Joes, it's okay, you can still watch it right now. Now, observe this. If there is electric field on this charged particle, obviously there will be a force on this charged particle, and that force will be nothing but this way. So the electric force will be this way in the direction of the field. Velocity is here, magnetic field is inside, so I'm pretty sure there will be a magnetic force also. And if you do V cross B, you will see the thumb coming upwards. So the force due to the magnetic field will be in this particular direction. There you go. If it goes undeflected, if it goes basically undeflected, what does it mean? What does it mean if it goes undeflected? Both these forces are definitely going to be equal. So the force by the magnetic field should be equal to the force by the electric field. Force by the electric field is Q into E, charge into the field. Force by the magnetic field is QV into B. You can clearly see the charge value just gets cancelled, and I just have my velocity as electric field by my magnetic field. Now this is a very special velocity, which is the ratio of electric and magnetic fields. Only those charged particles which have this velocity will go undeflected through this. Any other particle which has less or more will either go that way or that way, because either magnetic force will be more or electric force will be more. Everybody clear? Thumb rule फिर से. See, velocity is here, magnetic field is inside. So stand like this. I am behaving as if I am a student. So you will hold your right hand like this. V cross B, thumb will come up. So that's the direction of the magnetic field force. I hope this is clear. Okay, so these particles exactly have V is equal to E by B. These particles definitely don't have the velocity as E by B. So that's why it is called as a velocity selector. Cool? Okay. Thank you, Rishabh Shukla. I'm so glad that you guys are learning a lot through these quick, short, and meaningful sessions. Okay, and so many chapters, so many concepts done at once, guys. I'm pretty sure in your school this would have taken a lot of classes out there. Not this derivation, I'm saying in general these two chapters. But watching these concise videos will help you grasp everything in one go. It will help you not just for boards but also JEE, NEET, NDA, everything. Okay, moving on to another question, another derivation. Okay, so I'm not doing Biot-Savart's law and all of that, because Biot-Savart's law cannot be proved. It's like a fundamental thing. It's like asking somebody to prove Newton's law of gravity. So that cannot be proved. So that's more fundamental. So using your Biot-Savart's law, there are some derivations which are based on it, like a loop, and then you have Ampere's law on which you have the wire and all of that. So let's start with a loop. So there is a current carrying loop. Current goes in like this and goes around like that. And this is the axis of the loop. The radius of the wire, you can call it as, the radius of the loop, you can call it as R. On the axis, you are at a distance. You are at some distance, let's say I call it as X. So this is basically your X. This is a distance at which you are from the axis. Okay, this is theta. This is theta. Now what is that theta? I will come to it in a bit. Hold on. Now, first of all, every element on this wire will create a magnetic field at this point, and the total vector sum of this is what I need to find. Very visualizing problem, very nice concept is there in this. Observe carefully or you will get lost. Okay, pay attention. I want to find the total net magnetic field because of all the elements at that point. Now take any one element over here, that is dl. So if you look at it sideways, it will look something like this. It's like the loop is over here. Okay, the loop is over here. The current is coming towards you. The current goes like this and goes in. So here the current goes inside. This is the current coming towards you. This is the current coming inside, towards you and inside. I hope you are able to visualize when you see it from here. Okay, goes in and comes out and goes in like that. And your axis is basically this one. This is your axis. I hope you can see that. This is the direction in which there is a small element which is carrying current, and I want to find the magnetic field there. From here, if I look over here, this becomes my position vector, the position where I want to find the field at this particular point. The current is coming towards you. I'm trying to find the field over there. Everybody able to visualize this? I'm so happy for you, Hepsi. Good evening and all the best wishes for you. Thank you, Amarnath. Okay. Now use your right hand. Okay, maybe you will have to turn a little bit, but it is okay. Maybe you might have to face away from the screen or whatever. Length is towards you. The position vector where you want to find the field is there. So if you do length cross B, length cross B, just try it out. Right now I know you're watching me. So you just turn around a little bit and do length cross B. You will see the thumb going there. That's exactly the direction of the magnetic field shown over here. This is exactly the direction of the magnetic field shown over here. Just try this out. Yes, Imran, Esa, there is repeaters batch, bacha. You can leave a comment, bacha. I'll definitely ping you the link for joining the repeaters batch. Because this is a small element coming here, the field also is basically dB. The field also is basically dB because it's because of a small element on the top, dl. Now, if you call this as theta, obviously this is 90 minus theta. Obviously, the complementary of that, then this will be theta. Just check this out. This will be theta. And then again, this will be nothing but your 90 minus theta. Just check this out. This will be 90 minus theta. Everybody with me? Everybody with me on this? Great. If this is 90 minus theta, then again, this will be theta. So this is how I'm marking all the angles which are very, very crucial. Theta 90 minus theta, theta 90 minus theta, theta, because this angle is 90 degrees. Okay, now this magnetic field will have two components. This magnetic field will have two components, bachas. Okay, one component is actually over here. Okay, this will be your dB sine theta, and the other component will be here. That will be dB cos theta over here. Now think carefully. Think carefully. Just like this element caused this magnetic field and two components, just like this magnetic field caused two components, one component here and one component here, can't you think that this element which is there here, which is going inside, will also cause two magnetic components, magnetic field components, one component here and the other component here, exactly opposite. Just like the field is here, the other side the field will be downwards and there will be again two components. Just like this wire causes these two components, this wire which is going in will cause a field here which will have two more components. Now think carefully. Out of these components which are caused by diametrically opposite elements, which magnetic fields are cancelling, which magnetic fields are adding? Which magnetic fields are cancelling, which magnetic fields are cancelling, which are adding? Come on, think about it. This sine component or cos component, I want the answer in the chat box. I want the answer in the chat box. Isn't it obvious that these are basically the red ones? That is the reason why I put it in red. They are basically cancelling out. The green ones are basically adding. They are nothing but adding. Yep, the sine components are cancelling, the cos are getting added up. So that's it. So now I know that one thing is for sure, the small magnetic field using Biot-Savart's law is mu naught by 4 pi I into dl cross r. Remember, dl was here, this element like this, r was there. I'm looking at that point on the axis there. So dl cross r, the angle between dl and r is 90 degrees. So I dl r sine 90, very important, divided by r cube. This is using your 𝐕𝐞𝐝𝐵's law. 𝐕𝐞𝐝𝐵's law. You can see RR gets cancelled, so dB will be mu naught by 4 pi I dl by r square. Now I don't want dB, I want only the dB cos, because that is what is going to give me the net field. The net field will be integration of dB cos theta. So integration of dB is mu naught by 4 pi. I have r square, and I have dl. Cos theta, you can see cos theta. What is cos theta? From here only you can see this is basically your radius adjacent by hypotenuse. So adjacent by hypotenuse. So this should be r by small r. Many people are constants, just throw them outside the integral. So mu naught by 4 pi, current is a constant, r square into r is r cube, and even r is going to just come out, and I'll just have integration of dl. Integration of dl is only going to remain, and that's it guys, nothing else. So think about it. If I add all the add all the elements, dl everywhere through the loop, I'll get the total circumference, nothing else. So this is just going to be, maybe I'll just put it up over here, then I'll go on that side. So this will be mu naught I r by 4 pi r cube. Okay, I'll do something with r cube also. Integral of dl is nothing but 2 pi the radius. Great, you can clearly see this 2 pi cancels with this 4 pi, it becomes 2. Also notice this small r over here, is nothing but the hypotenuse. So it is root of r square plus x square, or r square plus x square raised to half. So in the next step, what I'm going to write is the magnetic field is mu naught I r divided by 2 r cube, that means r square plus x square raised to half raised to 3, that means raised to 3 by 2. That's all. R is r square plus x square raised to half, so raised to 3, so that's why 3 by 2. I think that should be the final outcome. Yep. And you can substitute x is equal to 0. If you put x equals to 0 in this, what will happen? If x equals to 0, then you will try to find the B field, magnetic field, at the center of that particular loop. At the center of that particular loop. So if you put x as 0, what will you get? You will get this as B is equal to mu naught IR divided by 2 is also there. X is 0 because when x is 0, you are at the center of this loop. So it will become r square plus x square. X is 0, gone. So r square raised to 3 by 2. 2 cancels. R cube will remain. So it will become mu naught IR divided by 2r cube. That's it. One of the r will get cancelled, right? So just check this out if everything is clear. Yes. Wait a minute guys, I think while writing this I missed one r. I just realized this r and this r should become r square. I'm so sorry guys, I missed the r square term over here. So this r into this r, I missed one square, so this should have an r square. So this should be r square, this will also be r square. Now it's fine. So this will be nothing but B is equal to mu naught I by 2r. Yes, this is exactly the field at the center of the coil. Just check this out. Yep. Oh, a lot of people make a silly mistake here. They write dl as 2 pi small r. No, it's not 2 pi small r, it is 2 pi capital R, the radius of the loop. Okay, that's also a common mistake. Okay, I hope this is clear. Moving on. Yeah, let's move on to the next derivation maybe. Okay, so what's the next derivation? Yeah, Ampere's law, yeah, we have to use and find out the magnetic field due to a long wire. Very straightforward. Let's use Ampere's law. So Ampere's law says that integration of magnetic field with the line integral is mu naught into the current which is there inside of it or enclosed. So this is a long wire. It produces a magnetic field. Question is, find the magnetic field at any distance. So what you do is take any loop, any path which you call it as the Amperian path. This is your Amperian loop, and again take the radius to be r, and at any point on that loop you will notice that the magnetic field is always along that element dl. No matter where you take that element, dl, that element and that magnetic field are always parallel to each other. That means B dot dl, when you do that B dot dl, it will become B dl cos 0. Current inside this loop is only I, so it will just become mu naught into I. Cos 0 is 1, magnetic field is same, so bring it outside. So cyclic integral just dl is mu naught into I. Now this dl's addition, dl, if you add it, you will get the complete circumference of this Amperian loop. So it will be B into 2 pi radius, it is equal to mu naught I. Therefore the magnetic field will be mu naught by 2 pi r, and there is current over here. That's the magnetic field due to a current carrying wire. And that's what I have done using Ampere's loop law. Ryan, this is English channel, that's why I'm talking in English, but you have a Hindi channel where I teach, that's called Neat Made Easy. You can watch me over there also. Yeah, boards have a soft corner for loop derivation, maybe. All right. Now there is one more peculiar derivation. It's not there, in your regular, white pages. It's there as maybe an example or in one dark page. Okay, slightly hidden from your normal view inside your NCERT, and that is for magnetic field inside a wire. Very crucial. Magnetic field inside a wire. So when you go inside, also there is magnetic field, and how do you find that? Observe this. So inside, let's assume that the magnetic field at any distance from the center, this is basically your R, is B, and you again choose an Amperian loop. You choose an Amperian loop over here, and this is your wire basically. I hope you can see this. This is your wire. And the radius of the wire is r. You're trying to find the field anywhere inside of that. Again, start with Ampere's loop law. Cyclic integral B dot dl is equal to mu naught into I, which is there inside. Now again, the dot product will become B dl cos 0, because magnetic field and the length are always parallel. So bring that B outside. I'll just be left with dl's integration. So again it will become basically 2 pi small r. This is what it will become. But the problem is with the RHS. The RHS is not just mu naught into I. Reason being, observe carefully, you have to choose only that current which is inside this part. Only which is inside this part, not the entire thing. Observe carefully. If you take the cross-sectional view, there is current flowing in this entire thing, but you only want the current which is flowing in this much part. How do you do that? Because only I need the enclosed current. The logic is the current which is there per unit area is the same. So if total current was I, it would be flowing in an area of pi r square, pi capital R square. But in this part, the current which is going to flow, I don't know whether it is seen, so maybe I'll use a different color. Okay, the current which is going to flow will be only distributed in small pi r square. This is the transformation you need to do. I hope this is clear. Okay, now pi gets cancelled. pi gets cancelled. So what is the current inside going to be? It is going to be I into small r square by capital R square. So just substitute that over here. I small r square by capital R square. So mu naught I small r square by capital R square. Mu naught I small r square by capital R square. Now it's just a matter of cancelling things. This r and this r will get cancelled. So I think you will get the magnetic field as mu naught I, and you will have small r over here, and you will have 2 pi and this capital R square. So this is the formula when you are inside. The main difference is that when you are outside, then the magnetic field is inversely proportional to R when you are outside. R is below, and when you are inside, then the magnetic field is directly proportional to R. That is the change. That's all. Exactly. So this transformation is very, very crucial, guys, whatever I did over here. Okay, if you do not know this transformation, you will make a lot of mistakes. Here the current per unit area is the same. That's all you need to do. Okay, moving on to the next derivation, and that is solenoid. And for solenoid and toroid, it is very simple. The solenoid, what happens is inside you will see that this B is nothing but uniform. There is uniform magnetic field inside, but outside there is negligible magnetic field because the field lines just distribute everywhere. So there is negligible magnetic field. So usually the Amperian loop that you take looks somewhat like this. Looks somewhat like this. You go here, then you go here, then you go here, and then you go here. And when you apply your Ampere's law, which is B dot dl is mu naught into I inside, this integration, which is the complete loop integration, you can break it into parts. You can break it into parts. Let's say this is first part, this is second part, this is third part, this is fourth part. So I can say integral B dl for the first part plus integral B dl for the second part plus integral B dl for the third part plus integral B dl for the fourth part is equal to mu naught into I enclosed. Now what happens is, only in the first part you will see magnetic field and my length are in the same direction. So basically what happens is, because they are in the same direction, only in the first part I will say it is integration B dl cos 0. Now whether it is here or here or here, 3 does not even have field. Remember, outside there is no field. So basically the third term just becomes 0. The second and the fourth term, the magnetic field and the length are both perpendicular. So when you take the dot product, it will anyways become 0. When you take the dot product, magnetic field is like this, length is here or here, so they are perpendicular. So dot product of perpendicular vectors is 0. That's it. So this is mu naught into the enclosed or inside current. Great. Now B is constant, so just bring that outside. Remember, this B is uniform, so bring this outside, and I'll just have integration of dl is mu naught into the current which is trapped inside. Okay, now here is the catch. Observe this carefully. There are some windings over here. There are some windings. Each winding will carry some current. Each winding will carry some current. So how much current is inside? How much current is inside? It's basically the number of your windings, which are there, into each winding will carry I amount of current. How many windings are there? Into the current of each winding. How many windings are there? How do I know? Simple. If I know number of loops per unit length, if I multiply it with the length of this part, I get the total number of windings. I know per unit length how many windings are there, how many loops are there per unit length. Into the length will give me the total number of windings into the current. Now this quantity is called as small n, this is L and this is I. So this is the current which is going to be there inside. So just put N times L times of I as it is over here. Now I know when I add these lengths for only the first part, from here to here, dl plus dl plus dl will give me the length of this first part, which is L, and this right hand side will be as it is, mu naught N L I. Clearly L cancels, so I'm just left with B is equal to mu naught number of turns per unit length into the current. This is the formula, guys. Check this out. Everybody with me on this? Okay, so this is how you derive it for the solenoid. You should know what transformation I have done over here. So the total current was total windings into current. Here the windings will be how many windings are there per unit length into the length. That's it. So this quantity is called small n, length is L, I is I, L anyways gets cancelled. Now for toroid you don't need to do special derivation. If you take a solenoid and bend it and connect the ends, it becomes a toroid. So whatever formula is there for solenoid is also applicable for toroid. So even for toroid, the magnetic field is mu naught, okay, small n into I. As simple as that. This n is how many turns are there per unit length. How many turns are there per unit length? So you can write this n as total turns into the total length of this tube, which is nothing but 2 pi into r, where r is basically this radius. How many turns are there per unit length? So this is how it is. So if you take a solenoid and just connect the ends, it becomes a toroid. So the formula will not change, it's the same, just that this n can be written down as total turns into the length of the tube. As simple as that. Okay, last few derivations coming up on your screen, guys. Let's do this. Okay, come on, do not lose your josh, do not lose your energy. Last few derivations. Are you guys ready? Show some energy, guys. Yes, negative marks definitely matters, Ghost Gaming. Yeah, solenoid made into a ring is a toroid. Very true. Yes, Joey. Okay, now force between two parallel wires which carry current. How do we do this? Well, each wire will produce a magnetic field. The field will apply a force on the other wire. So let's say I calculate what is the field by wire 1 on 2. That will be B1. It will be mu naught I1, because field by wire 1, by 2 pi into the distance between them. Let's say I'm just saying the distance between them is d. So it will be 2 pi into r. Here r is nothing but d. This is the field which is created by any wire at some point. Now because this field is cutting through this wire, it will apply a force on it. So the force on 2 due to the field of 1 will be given by current into length into your magnetic field of the 1. I L cross B. I just gave you that formula some time back. So just substitute it over here. So mu naught I1 by 2 pi d, and over here as it is you will have I2 into length. Bring this length below. So this will become force per unit length is mu naught I1 I2 divided by 2 pi d. Now this is also very crucial formula. Very crucial formula. The force of interaction between two parallel wires is mu naught I1 I2 by 2 pi d, but this is force per unit length. Please bear that in mind. This is the force which acts per unit length of the wire. In fact, this is how the unit of ampere has been defined, because you know the unit of force, you know the unit of length. So length is also known. Mu naught by 2 pi is nothing but 10 to the power, mu naught by 4 pi is 10 to the power minus 7. From this, that current has been defined as 1 ampere. Okay, so that's how it is. Cool. So very straightforward derivation. One thing you should know over here is that if the wires are basically parallel, that means in the same direction, then they will not repel, then they will basically attract each other. Then they attract each other. Whereas if you have one wire here and the other wire here, opposites here will basically repel each other. That's something which you should know. Moving on now to the torque experienced. Let's go to this. Torque experienced by a loop which is placed in a magnetic field. Very, very straightforward, guys. Again, observe this carefully. There is a coil over here. Let's say the side length over here is, let's say, A. This side length is, let's say, L. There is some current which is flowing in this, which I call it as I, placed in some external field, which is like this B. So if you look at it from this point or this angle, if you look at it from this point, okay, so what you want to see is this loop is just flat over here, okay, and there is this external field this way, okay, and there is current flowing like in this way, like this, like this, like this, like this. So its current is going like this, like this, like this, and like this. So what kind of forces will be there? Let's try to identify. First of all, whenever you want to calculate the force, remember the force due to the external field is I, L cross B. Length is this way, magnetic field is this way. Just try this out. Length is inside, magnetic field is here. If you do L cross B, you will see the force acting downwards. So I think on this side, the force will be here. You can try it out. If the current goes like this, like this, like this, like this, force will be over here. Just try it out. Length is inside, magnetic field is towards your right side, the thumb will point down. Same thing if you do it over here. Length and magnetic field both are parallel, so there will be no force. Length and magnetic field are parallel, no force. On this wire, because the current is coming this way, the force on this side will be over here. Obviously, if the current goes here, the force is down. If the current comes like this, the force will be up. And on this part, there will be no force because length vector and magnetic field vector both are anti-parallel. So there should be no force on it. When sine 0 or sine 180 is calculated, it comes out to be 0. So if you look at it sideways, it basically looks something like this. One force here and the other force is over here. So clearly there is a torque. And if this is the pivot or this is the center, you can easily find out the torque by the magnetic force. This torque will be, please bear in mind, this total length is A. So hence, each of this will be A by 2 and A by 2. So this force will give a torque of R, which is nothing but A by 2 into F, A by 2 into F this way. Even this force will give the torque in the same direction, it will not cancel. If this force is rotating it anti-clockwise, this force will also rotate it anti-clockwise. So this will be also A by 2 into F. So this will obviously become A into F. But wait a minute, what will be the force on this wire? It will be ILB. I is I, length is L, and B is B. This is the torque on that particular loop. This is the torque on the loop. What if there are n turns? Think about it. So for n number of turns, each turn will experience the same torque. So can I not say the total torque will be number of turns into tau 1? That means it will be nothing but NAIL. Wow, nailed it. Nail B. Interesting. Now I'll do one thing, guys. A into L is nothing but the area of that loop. So why not write it as N into I. A into L is nothing but the area into B. Observe this. Now this term NIA, here A is nothing but your area. Then this NIA is defined as a new term called as the magnetic magnetic moment. Magnetic moment. So I can just write it as just M and this is B. So this is how you get torque as MB. But in general, it turns out to be torque is equal to M cross B, the vector product. Just like in electricity, it is electric dipole moment into electric field. Here it is magnetic dipole moment into magnetic field. As simple as that. Cool, guys? Everybody with me? So this is the torque on a loop which carries some kind of current. M cross B, this is how magnetic moment has been defined. Awesome. Cool. Now last, I think, few derivations. This is also very crucial. Sometimes it got deleted also, but maybe it might be there in your syllabus. So how do you convert a loop into a dipole? See, when I see a loop which carries current, you might have seen that some places or some books or some teachers would have told you there is a north pole and south pole. How do you know that it is a north pole, south pole? How do you know it behaves like a dipole? That is the proof for this. Observe carefully. So imagine this is a loop which carries current. So what is this? This is nothing but a loop carrying current. This is a loop carrying your current. This current is basically going like this. You take some random point on the loop. At some distance x from the axis. I know that there will be some kind of a magnetic field, and I think I just derived that for you. The magnetic field on the axis of a loop is just given by mu naught I r square divided by 2 times r square plus x square. Cool? This is the formula which I just derived some time back. What if that point is really far away? Let's make some approximations and I want you to compare this, that's all. If P is really far from the center, that means the value of x is much larger than the radius of the loop. That means the value of x is much larger than the radius of the loop. So if you look at it over here, r square plus x square can be approximately said, because x is very large, this will be insignificant in front of this guy. Remember, this is like 1000 square, this is like 1 square. Obviously 1 square will be neglected in front of 1000 square. So this will be approximately x square. Everybody with me on this? Very good. Now let's substitute. Oh, sorry, I forgot that 3 by 2. My bad. So sorry, guys. This was 3 by 2. My bad. That 3 by 2 was there. Now let's use that over here and see what do we get. So therefore, magnetic field will be mu naught I into r square. The whole thing divided by 2. R square plus x square is nothing but nearly x square. The whole thing raised to 3 by 2. Interesting. 2 will cancel. Yeah, the powers. So this will end up being mu naught I r square, the whole thing divided by 2x cube. Okay, I'm still not happy with this. I've just, simplified this expression. Nothing else has been done. Now I got some idea. Maybe I can divide it with pi and also multiply with pi. And in fact, divide with 2 and also multiply with 2. So basically, what I'm trying to do over here is multiply by 2 pi and also divide by 2 pi. What will happen because of that? Well, let's find out. Therefore, let's see if I have one more slide. Yeah, luckily I have one more slide. Okay, so B is equal to mu naught as it is. 2 into 2 pi is nothing but 4 pi. Interesting. This 2 as it is. And what I can do, pi r square into I, or rather I into pi r square. Just check this out. I pi r square and this 2 as it is. The whole thing divided by x cube. Okay, I'll go to the next slide and make you see it now. Therefore, the magnetic field will be mu naught by 4 pi. 2 as it is. X cube also as it is. Do you see what this I into pi r square is? Do you see what this term over here is actually, it's current into area. If you noticed, current into area, here the number of loops is 1, is nothing but the magnetic moment. So strictly speaking, this is nothing but your magnetic moment, guys. This is nothing but your magnetic moment, as simple as that. I into, no, yeah, it's not current density, no, that's completely different. This is I into pi r square, that's the, area of that coil. So that's your magnetic moment, so might as well put it over here. Now this formula looks very familiar to me. I'll tell you what, if you remember dipoles, electric dipoles, the formula was also very similar for finding the field on the axis. It was 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, 2 times of electric dipole moment by the distance cube. Here it is magnetic and it is mu naught by 4 pi, and instead of electric dipole you have magnetic dipole. Crazy, guys. So imagine this, if you had a bar magnet instead of this, which had its own magnetic moment m, then on the axis I would exactly get the same magnetic dipole moment. On the axis I will get the exactly same, I will exactly get the same magnetic field. So this proves that a coil carrying current, is exactly similar to a magnet, and this is nothing but a permanent magnet dipole. That's the proof of it. Thank you, Dinesh. I'm so glad you enjoyed it. Yes, for NEET also derivation is necessary. In fact, from board's point of view, Hannah Jones, number 1, number 2, when you do derivations, you will understand the concepts deeply. So a lot of NEET students often complain, sir, I'm not able to solve problems, I don't understand it properly. So the reason is you just know the formulas and you just do the questions. So if you want good marks and if you want to understand things and then do it, then please go ahead with the derivations. Or if you are the kind of person who are like, sir, I can do without the derivations also, I'm able to solve the problems, then it's fine for NEET. I won't say that for JEE or any other exam or Olympiads. Okay, I hope this is clear. Hi Leah, Madison. Okay, so that is the proof of this. Last one is the magnetic moment of an electron which is revolving. So this is very simple. It is basically the gyromagnetic ratio. See guys, if you have a charged particle which is revolving, okay, it also produces current because it's charge moving in a loop. So a charge revolving in a loop is exactly like a current loop. That means it will have its own magnetic moment. So the moment you see any charge like electron revolving in some orbit of Bohr's model or any atom, it's like a small current, teeny mini current. Yes, there is no physical wire, but it is like a wire which carries some current, and because a current carrying loop produces its own field and behaves like a small teeny mini magnet which has its own magnetic moment, so even a charged particle in a loop also has its own magnetic moment, and we can find that very easily. Okay, let's try this out. First of all, what is the current because of this? Current is nothing but how much charge which flows in particular one time period. In one time period, the charge which flows is Q, and the time period is nothing but 2 pi r by V. This is standard. Time is distance by speed. How much distance it travels with what speed is nothing but the time. Cool. Now comes the magnetic moment. The magnetic moment, this is the magnetic moment, guys. The magnetic moment is number of turns here is 1, current is I into area. Current is nothing but QV by 2 pi r. Current is QV by 2 pi r. Area is nothing but pi r square. Pi just goes, one of the r also goes. Therefore, magnetic moment comes out to be QV r by 2. Just check this out. Okay, now I think I got one idea what I can do. I can just preserve the equality by multiplying by m and dividing by m. Preserve the equality by multiplying and dividing by m. So what happens is, because of this, I will get q. I will write this as mRV, and this is 2 and this is m. I know what is this. I know what is this. mRV. What is that, guys? That is nothing but your angular momentum. Angular momentum. If you remember from your 11th grade, R cross MV, R cross momentum, MRV is nothing but angular momentum. So bring these people down here. So it will look like this. Magnetic moment by angular momentum is Q by 2m. This is a very famous value. This is called as gyromagnetic ratio. So for any charged body which is rotating, the magnetic moment by angular momentum is the charge by twice the mass. Very, very standard value. How the loop corresponds to the poles? Sharon, let me tell you, there is nothing like poles. Remember, North Pole and South Pole is just a hypothetical thing. You cannot ever figure out where the pole is, because the moment you break the magnet, it produces two new poles. So North Pole is that part of a body from where you see the field lines actually coming. But remember, field lines are not actually starting from north, because even inside the magnet, the field lines continue as closed loops. So there is something called as the north side and south side. Pole is just a concept which is introduced to make it look like electricity. Otherwise, there are no magnetic monopoles. Now, in electromagnetic waves, what are the important things that you need to study? First is the source of the electromagnetic wave. Second is the equations and the characteristics and the nature of the electromagnetic wave. The third thing is the electromagnetic spectrum, the different kinds, its applications, the sources and the wavelengths. So I have made a beautiful mind map for all of you. So in the source of electromagnetic wave, what and all you should know? Yes, Adityas, you can let me know. Okay, so field created by Maxwell and wave propagation by Hertz. These are the two main concepts. Even if you open up NCERT, right, you will see the same thing right over here. So I don't know whether I have it open. Let me just see. Looks like I have closed it. Okay, anyways. So the idea over here is that Maxwell gave the theoretical approach, right? He talked more about the theory about electromagnetic waves. Hertz was the guy who made experiments, who conducted experiments and found out that light is actually an electromagnetic wave. Maxwell told that electric fields can create magnetic fields can create electric fields. So he gave the relationship between the electric and the magnetic fields. He also told about the moving charge, the concept of moving charge, which creates electric field as well as magnetic field around it. Very important concept. So a normal charge which is at rest creates electric field, but the moment you move the charge, it also produces magnetic field. So if you oscillate a charge, you will notice that you will eventually end up creating an electromagnetic wave. This was the conceptual part, but that actual part experimentally was given by Hertz. That's one thing. Now, the next thing, yes, that's the Maxwell's equation. This mind map is going to be very useful. You can take a printout or you can draw it the way I have shown, and then you can add more formulas. Don't worry, you'll get the entire PDF in the Telegram channel. If you have not joined it, please join it right now. Okay, now the next thing, this session will be for at least 2 hours, I guess. The next thing that you should know over here, let me just get my pen. All right. Okay. So talking about electric and magnetic field waves, these electric and magnetic fields are basically perpendicular to each other. Like you can see, they are perpendicular, and the direction in which they move is also perpendicular to the electric and the magnetic fields. So going back, E and B fields are perpendicular. Not just that, E cross B is parallel to the speed of light. So if electric field is this way, magnetic field is that way, E cross B, using your right hand thumb rule will give you the direction of light. So there could be questions based on this. They will give you direction of E, they'll give you direction of B, and they'll ask you where is C. Example, just think about it. Say electric field is in I cap direction, magnetic field is in J cap direction. I cross J is going to give you K hat. So the light will go in the Z axis. That's what. I hope this is clear, everybody. All right. So let's move to the next part. Oh, somebody's saying I missed UV rays. Thank you very much for pointing it out. So let me add UV rays. Thank you guys. Yeah. So I don't know how it got missed, but yeah, let me put it over here. UV rays as well. This is also there. Okay. Now going ahead, there is relationship between electric field, magnetic field and the wave speed. That is something which you should talk about, and let's write it down. And how is speed and frequency related? Very important formulas. Observe this carefully. Speed of light is electric field by magnetic field. It is also electric field amplitude by magnetic field amplitude. It is also 1 by root of permittivity into permeability and permeability of the medium. This is also frequency into wavelength. This is also omega by k, which is angular frequency by angular wave number. So this formula sheet is very important. You don't know what might be given, what has to be found. You can use these formulas whenever required. So this is basically your amplitude of the electric field and magnetic field. This is basically your property of the medium, the medium's electric permittivity and magnetic permeability. This is frequency, this is wavelength standard. Omega is 2 pi f angular frequency. K is your angular wave number, so it is 2 pi divided by lambda. Standard values. E and B are the instantaneous values. If you notice, this value of E is nothing but E naught sine or cosine, whatever you want to use, kx plus minus omega t. Same way, the value of B is B naught sine or cos, whatever you want to use, kx plus minus omega t. One doubt I have, let's see, one question rather. Is it mandatory to put kx first? Can I put omega t first and write omega t plus minus kx? Think about it. Thank you, Vityashar Bose. Ida oru bro nenga. Oh my god. Is it mandatory? Anything can come. How many marks will derivation come for board exams? For major marks, at least 10 to 15 marks minimum. I'm telling, minimum 10 to 15 marks. Derivations or derivation related questions. Okay, so this is something which you should know. Also, you should know one simple logic, and that logic is the medium decides the wave speed. The source that is generating it decides the frequency. These together decide the wavelength. So wavelength is decided in the end. Source decides frequency. The medium decides the speed, and together using this relationship F lambda is equal to C, you will decide the wavelength. Last thing is the energy of the wave. Energy of that wave is divided equally into electric and magnetic fields. It's equally divided. Both the fields carry equal amounts of energy. So whenever the total energy is asked, it is just the sum of the electrical and the magnetic fields energies. You do not have formulas for the CBSE board exam, so let's not worry about that. Yes, lens maker derivation can come, and I'm going to derive it today. Okay, now let's go on to these points. Radio waves, micro, infra, visible, UV, X-rays, gamma rays. So you should know application for each and every one of them. Let us see what do you know about UV rays. Whatever you know, write it down in the chat box. I want to see how many of you remember randomly, out of the blue. UV rays, what is the wavelength range? In what range does it lie? What is the wavelength above or below? And what are the applications, phenomena? Are there some problems with that? Okay, Yes, phase difference is k into delta x. Okay, so sorry, 2 pi by lambda, yeah, which is k into delta x. Okay, used to kill germs. Yes, UV rays are very harmful. They can damage your skin, can cause cancer, skin burns, and the UV rays are protected. I mean, you get yourself protected from UV rays by applying some lotion or through the ozone layer. So the ozone layer becomes small, then the UV rays from the sun will definitely damage you. Now the range of UV rays, well, you can see it's above the visible rays, so it's going to the higher frequency. It is more energetic than visible rays. It's higher than violet. Violet has a wavelength of 400 nanometer, so the wavelength is lesser for UV rays, so it is less than 400 nanometers. The ultraviolet radiation lies in between 400 nanometers and angstroms, reason being X-rays, the wavelength is in Armstrong. Recollect, X-rays, Armstrong. How do I remember it? X-rays is used in diffraction. It's used to study solids, and the crystal structure undergoes diffraction when X-rays are passed through it. So you will see that diffraction occurs only when the wavelength is comparable to the intermolecular gaps, or the spacing between them, and the spacing is usually in Armstrong. So now I know that X-rays are in Armstrong. So that's how you are supposed to remember, through examples, through some stories, through some applications. Gamma rays used for treating cancer, microwaves in your microwave oven, infrared, it's created from your body, greenhouse effect, all these things should come in your mind. Visible rays comes from 400 nanometers to 700 nanometers. 400 is violet, 700 is red. Red is longer, blue, violet is shorter. Radio waves is used for long distance communication, satellites, radio, your TV, your all these long distance communication. Radar happens through radio waves. Okay, so I have put up a table, uses, range, type of radio wave that we are talking about, type of electromagnetic wave. I put this, but you have extensive paragraphs, and guys, in the Telegram channel, if you have not seen, please see that I have put up underlined NCERT. I have only underlined and given it to you. What more you want? It can't be, I mean, simpler than this. The entire PDF of NCERT with underlined pointers for each, not just here, but the entire chapters, for all the chapters of term 2, it is there. So please check it out. So this is the most important graph, most important diagram which you should know. Obviously, please don't carry color pencils and say, sir, do we need to carry 7 color crayons in the exam? No, you just have to make a chart, just mark, okay, gamma rays, X-rays, ultraviolet, violet, yellow, red, infrared, microwave, short radio wave, long radio wave. You should know it. No problem, Bhargav, always for you. Sir, radar system is for microwave. Now, sir, you said radio waves. Radar comes in between. Radar comes somewhere in between. You'll see in between radio waves and microwaves. So it's on the higher end of microwaves. It's on the lower end of the radio waves, short radio waves. Okay, whatever the major derivations are travel with Afzal, I'm going to do it. So should we remember the wavelength in terms of 10 powers, or like nanometers is better? And who is that? Anabalgam Anbu, because remembering in the powers of 10 is more difficult, no? So you can remember some in Armstrong, like X-ray in Armstrong, visible light in nanometers. Radio waves are very long, so in kilometers, meters, so it's easier that way. Okay, okay. I left AM waiver. Oh my god, guys. Yeah, oh no, guys. In radio wave, one of it is AM, one of it is FM. So AM is not a special kind of wavelength. Please don't get it wrong. Like microwave, radio waves, X-rays, AM is not a wave, a separate wave. AM is a type of process on that wave which makes it amplitude modulated. So you will see that in communication systems. It is frequency modulated and amplitude modulated. AM is not a separate kind of wave. AM is an application. The velocity of all the waves is same. Basmati, all the light waves travel at the same speed. Yes, we'll be doing VIT-EEE also. Which ray is used for satellite detection? These radio waves, this range. Questions are based on frequency also. See, Hari Harsan, simple. If you know the wavelength, you can find frequency. If you know frequency, you can find wavelength, because f into lambda is c. C value is simple, 3 into 10 to the power 8. So if you know the wavelength, you can easily find the range of frequency. So only remember one of them. If you try to remember both, good chance you might just forget it in the exam. No need to memorize critical. That's why I told wavelength is easier to memorize. I feel so. For you guys, is it easier to memorize frequency or wavelength? You guys only tell me. Kritika, you only tell me, is it easier to memorize wavelength or frequency? I feel wavelength is easier. Acha, Anirudh remembers both for electromagnetic. Good, if you remember both, you have excellent memory skills. My memory is not that great, guys. Okay, wavelength. We know the velocity is lambda by t. Velocity is lambda by, lambda into f. So if lambda is different for different radiations, how come we say velocity is same? Frequency is also different, Bhargav. That t is different. So what did I tell you just some time back? Look at this. Medium decides speed, not wavelength or frequency. Source decides frequency, wavelength is decided in the end. That's the reason. Understood, bacha? I'm very good. Sriji. Nice to see you back again. 𝐸𝑟 like I told you, use the tricks. Okay? Radio wave long, meters, kilometers. Long radio waves, kilometers. Short radio waves in meters, millimeters. Then you get micro. Micro is in milli to micro. Infrared is in just above that 700 nanometer mark. 400 to 700 is a very important data point range. Above that, you get your ultra. Then X-rays is in Armstrong. Gamma is obtained from nuclear reaction. So nuclear means, see, in nucleus, what is the size? 10 to the power minus 15. So it will be very small, 10 to the power minus 12, 10 to the power minus 14, 10 to the power minus 15. So it's in that range. Keep that in mind. Okay, bacha? Where do we find our NCERT underline notes? Samyukta Kannan. Go to the description box, Telegram channel link, click open Telegram. If you have not downloaded Telegram app, download it. In that app, just scroll up. I have just put it up just yesterday. Next. Now this is the difficult part. Relation between E and B, derivation, no, don't expect it. It will not be there. In fact, Janaya studies, I doubt they will ask any tough questions on E and B relationship also. So don't worry. Bohr's energy level derivation can come, Anisha. I will be doing that. This is for class 12th passing out batch. Prem Kumar, in a live class, let me just see if 2x speed is available. I'll have to move like this. I'll have to do like this. I'll have to write like this. If this is 2x speed. So you press 2x speed, I will write like this, okay? This is live class, bacha. Sorry, 2x speed is not available. In the recorded version, it is available. Alright? Okay. Come on. Let's start with the derivations first. Reflection laws using Huygens principle. Can I teach derivatives? Swati, derivatives is not there. 11th standard. Okay. No voice? What are you saying? There should be voice, Sandeep. Refresh. Huygens principle, reflection laws. Let's start. First draw a mirror. Obviously reflection means mirror only, row. So first draw what? Mirror. Next, what will you draw? Incident rays. So draw incident rays. Incident rays. Can you wait a minute after writing, Angel? I want to keep it fast because there are so many things, but Angel, I'll tell you, whatever I write now, whatever I write will be available to you in the PDF. I will post the PDF immediately. You don't even have to wait 1 second. You can make fast hand notes. Show incident rays. These are your incident rays. Show this AB. AB is called, AB will be now your incident wavefront. It's your incident wavefront. Now, when the wavefront reaches the mirror, this point starts creating secondary waves in this direction, opposite, because it's a reflector. Meanwhile, B will reach here, reach this point. So by the time this point reaches here, this point creates waves in this direction, and that's how the wave reflects. So you will see this will be the reflected waves. Probably this will be the reflected wavefront. I will call this CD. So CD is your reflected wavefront. Now observe this. Let's start drawing the angles. Obviously, to draw the angles, you should draw the normal. So let us draw the normal. Fair enough. Next thing, mark the angles of incidence. This is the angle of incidence. Normal, incident ray, angle of incidence. If this is angle of incidence, think about it carefully. This angle will be 90 minus I. Perpendicular, na? Complementary angles I, 90 minus I, complementary. Understood, guys? Sandeep, PDF will come after I write it. Guys, you don't understand the concept of time, kya? Only after I write the PDF will come. Before writing, how will the PDF come? Hold on, na? Let the lecture get over. PDF will come on Telegram channel. Okay, next. This is I. Why is this I? Come on, this is 90 degree. This is 90 minus I, this is I. Obviously, got it. This is 90 minus I, this is I. Fair enough. This is one side. Next thing, over here for the reflected rays. Why am I showing you all this? So that you revise. Even if you know this, even if you feel that this is simple, still revise. Don't be overconfident. You will suddenly get confused in the exam. So over here, this is the reflected angle. If this is the reflected angle, this entire thing is 90 minus R, because this is 90 degree, the blue lines. So this is R, this is complementary angle. Now, if you look at these two yellow lines, these are totally 90 degrees. The angle is 90. So if this is 90 minus R, this is R. Fair enough. Now, what will I say is that in the time point B reaches C, that distance BC, which is speed into time, that distance BC is basically BC, speed is speed of light, time is t. You will notice the wavefront generated at A will reach D. By the time B reaches C, point A will generate a wavefront which will reach point D. So the wavefront generated at A reaches D. So therefore distance is speed into time, speed is c into t. CT same, hence I can clearly say BC is equal to AD. Now this is a very important relationship, because if BC is equal to AD, these are two right angle triangles, notice 90 degree, 90 degree, into right angle triangles, one side is common, and I also said the other two sides are also congruent. Obviously, the triangle ADC is congruent to triangle CAB. These two triangles are congruent. Now the moment, yes, SAS congruency test. Now the moment they are congruent, that's it, their angle should be equal. So which angle will be equal to what angle? This angle of this triangle should be equal to this angle of this triangle. So hence I will be equal to R. So that's what you get. That's all. That's the end of the proof of law of reflection. Very good. Unfortunately, we cannot post it on the description box, Bhuwana. Just download the app, Telegram app, Bhuna. It is very simple, easy, low weight app, very light app. Just download it. It is going to be very useful for you, trust me. Telegram is a very good app, better than WhatsApp. Very secure, very safe also. Okay, okay. His interference of thin film is not present, bacha. Don't worry about it. Next derivation, guys. Let's move on. So we have to be very quick. We have to be, very focused today, because it's just 2 days before the exam. Okay. So number one. Number two, if you feel that something you did not understand, please ask. I will see if I can answer. I'll try to answer. But you can watch the replay later on. You can definitely understand it. Let me tell you that. Okay. So here in refraction proof, you need two mediums. This is medium 1, this is medium 2, refractive index. Here the speed is v1, so v1 will be c by mu1. Here the speed is v2, so it is c by mu2. Speed of light is different in different medium, and that constant is called as the refractive index. So the amount by which, or the factor by which, your speed decreases, that is the refractive index of that medium. If I tell you the refractive index of the medium is 2, that means the speed will become half. If I tell you it is 1.5, then the speed will become 1.5 times less as compared to in vacuum. Okay, let's start drawing the incident. This is the incident rays. This is the incident wavefront. So this is A, B. Obviously this is perpendicular. This is how the rays are coming. All right. Now let's also draw the normal. Let's draw the normal right over here. Okay, fair enough. And then next will be obviously showing it little bit bent like this. It bends. This is your refracted angle. This is your refracted wavefront. This point I'm just going to call it as D. If this is R, this is also R. And over here, if this is I, this is also I. Okay, as simple as that. Incident angle, refracted angle. Now again, you should start your derivation by saying AB is your incident wavefront. Then your D, oh, did I not mark that point? Let me call this DC. Okay, so DC is your refracted wavefront. Also, I will say that when the wavefront reaches this interface, the boundary of the two mediums, then you will see when the wavefront has reached here, this point will still travel with this speed. Point B reaches C. Point B reaches C with speed V1, and in the same time, you will notice that this point generates new wavefronts in the newer medium, this medium, and you will notice those wavefronts will reach this point. So by the time B reaches C, you will notice these wavefronts reach over here. So you will see the wavefronts created at A reaches point D but with a different speed V2. Now think about it. Distance is speed into time. Speed into time. So AD will be V2 into T, whereas over here distance BC is nothing but speed into time again. But that speed is different because medium is different. It will work the insane. Just replace the T without instead of T use telegram.me. It will work. Young's double slit experiment also I will take, Thalapati, definitely. What is WF? Oh, that's wavefront, guys. I wrote short form. I thought you will understand. Okay. So anyways, WF Jania studies is wavefront. Wavefront. Will they ask these two derivations? They can, definitely. Kalyani, if we have enough Marathi crowd, I would love to take the classes in Marathi. एकदम मजा येईल मराठीत. एकदम आता माझी सटकेल, मस्त मजा येईल. Okay, but I'm not sure how many people would love to learn in Marathi. If we have, why not? I would love to teach in Marathi too. तुम्ही पण महाराष्ट्राचे आहात का? हो, मी महाराष्ट्राचाच आहे, पुण्याचा आहे मी, धर्मेश. अच्छा, चलो. Let's see the next one. Now, once you get this right, the next concept is somehow proving Snell's law. And Snell's law has sine, so sine of the angles. So sine of the angles. So let's see how do we do that. Let's figure this out. This is I. Naturally, this is 90 minus I. If this is 90 minus I, this is I. Okay. Complementary is the same angle. Similarly over here, this is R. This is 90 minus R. Naturally, this is R. R, 90 minus R. Complementary is the angle back again. I am tired, but Yogita, your exams are there. So if I rest, then it will not be good for you. So I am working hard only for you guys. Let me tell you that. So now what we'll do is we'll try to find out sine of I and sine of R and see what it is. So sine of I by sine of R. Sine I is opposite by adjacent. Opposite is BC. Adjacent is, sorry, not adjacent, my bad. Hypotenuse. Opposite by hypotenuse. Hypotenuse is AC. So AC comes over here. For sine R, opposite is AD. Opposite is AD Hypotenuse is again AC, like you can see, AC cancels. So I get BC by AD. But wait a minute, BC by AD. BC is V1T, AD is V2T, TT cancels, so it will be V1 by V2. But wait a minute, V1 and V2 is written right over here. So this shall be C by mu1 by C by mu2. CC cancels, mu2 goes on the top and mu1 comes below. Now cross multiply. So mu1 sine I is equal to mu2 sine R, which is your Snell's law. Done, done, done. Understood, guys? Clear? Everybody understood? Sir, is V1 in air equal to C? Yes, V1 in air, Ishwar, will be equal to C. Definitely Kalyani. Okay, hence proved. Yes, Indrani. Hence proved is very important. Hence proved. You feel so happy when you write that hence proved. Okay. Next, interference and intensity. Wow, we have gone to wave optics interference part. Can we use pen for diagrams? I doubt. Please don't use pens, use pencils only. This is from rare to dense. But for dense to rare also, what will change? Tell me. What will change? Tell me what will change in the entire derivation. Nothing. Only the diagram will change. Here it is bent like this, there you will bend it like that. I don't know why NCERT did it. They have drawn two diagrams, 2 times they have derived. I think they were short of some words. They wanted to just fill that textbook. Their head would have told, you have to write compulsorily 10 pages for this chapter. So not derivation for rare to denser, dense to rare. So random it is to confuse you. Okay, clear? No problem. Achha, they didn't derive, but they told it. Achha, they have not derived. Thank God they didn't derive it. But I remember seeing 2 paragraphs. One was for rare to dense and dense to rare. Okay, optical instruments, telescope, everything is coming, guys. Hold on, everything will come. Let's start with this. Many of you might not know these derivations. Let's do this first. First, we have 2 waves combined together which are in phase. That means they are in sync. If they are in phase, what you get is a big wave, constructive interference. The amplitude is A1 plus A2. This is called as constructive interference. Similarly, if you have one wave and another wave exactly opposite, that is called out of phase, then combining them together, you get a smaller wave whose amplitude is A1 minus A2. Such a phenomena is called as destructive interference. Next thing, if you take any wave, you will see the intensity of that wave is proportional to the amplitudes. Which power? Half, 1, minus 1, 3, 2, what is it? I'm going to go derivations chapter wise, but Mariam, let me tell you, derivations are only there in waves, atomic structure and ray optics, that's all. Yes, very good, square, excellent all yours. That's the answer. But now, what if you have a wave like this and the other wave is not in line with it, it's slightly ahead of it. There is something called as the path difference. So the delta x is there. Now this path difference means they are neither in phase, they are neither out of phase. It's something else. So what you get, the outcome, is a new wave. This is your resultant wave and some new amplitude. I don't know, I'm just going to figure that out. And you will see this is neither constructive nor destructive. It is called as intermediate interference. It is called intermediate interference. Dual nature, little bit here and there. Little bit. Small things are there. Okay. Now this path difference creates something called as the phase difference. In phase, out of phase. Crest, trough, in phase. Crest, trough, crest, out of phase. Crest, nah. Trough, nah, nothing. So it's something else. So it is definitely going to have some phase difference. I can also call it delta phi, and delta phi everybody knows is 2 pi by lambda into delta x, standard formula. Now, after you see this, there is one more thing which you need to know. That is, if you open up NCERT also and keep it side by side, you will see one derivation for two waves of same amplitude being added, and you have to find the resultant amplitude and intensity. So there is one important derivation for two identical waves added with phase difference. So there is one important derivation, you can check it out. So basically the resultant wave, R stands for the resultant wave, is given by wave 1 plus wave 2. Wave 1, let's say it is A, you can, in books they have used cos, if I'm not wrong, cos omega t plus A cos omega t plus phi. This is the values of the two waves. These are the two waves which you want to add. Now, if you want to add these two, just realize that you are basically wanting to add, taking A common, cos C plus cos D. Cos C plus cos D is 2 cos C plus D by 2 into cos of C minus D divided by 2. So just do that. So it is 2 times cos of omega t plus phi whole thing divided by 2 into cos of this minus this omega t plus phi minus omega t, the whole thing divided by 2. Okay. Now when you do the math, what you will get? 2 times of A. This will be omega t plus omega t is 2 omega t divided by 2. The 2 cancels. So cos of omega t plus phi by 2. And here omega t cancels off. Only phi by 2 remains. So cos of phi by 2. Rearrange it further. So it will become 2a cos phi by 2 into cos of omega t plus phi by 2. Now this is your resultant wave. This is what is given in your books. You should know this. 2 is a constant, A is a constant, phi is also a constant, t is a variable. So whatever you see over here, this is your amplitude of the resultant wave. Twice A cos phi by 2. Hi Sandeep, welcome back. So Prem Kumar, which part you did not understand? Okay? So this is one wave, this is another wave. You can see this wave, amplitude is A, frequency is omega. This also same frequency, same amplitude, but phase difference. When you add two terms, cos C plus cos D, the formula you should know. What is the formula? I think I should put it somewhere. Cos, I'll put it here. Cos C plus cos D is 2 cos C plus D by 2 into cos C minus D by 2. You can do cos D plus cos C also, it's the same thing. Important questions, Jagdivan Singh, kal karaunga. Yes, ray optics is not done yet. Krishna, don't worry. Even if it was done, you can always go back. That's all. Oh wow. Hello Harshvardhan. Nice to see you from the JEE Fusion batch. Hope it's all going great. Now the moment you get this, there is one last relationship which you should know. That's for intensity. And the idea is like this. When the amplitude is A, let's say, then the intensity is I0. When the amplitude is A for each wave, the intensity is I0. If the amplitude is 2A cos phi by 2, then what is that intensity? Remember, intensity is directly proportional to the square of the amplitude. We can use sine also. Yes, sine also can be used, but in your books cos is given. So I would prefer doing it for cos. Reason being, the model answers might contain cos expressions. The examiner might see sine. He will feel that you have done wrong. See, that is the problem with boards. I don't have any faith with the person checking your board paper. Who do you know who he is or who she is? Do you know whether they will understand? Do you know whether they have that patience to check it? Do you know what kind of problems they have at home? I don't know. Maybe that person checking is very frustrated. He or she has to check some 500 papers in 1 week. So they will do it fast. He will see sine, cos. Oh, he has done wrong. Gone. So let's not take risk. Yeah, so this will be square proportional. So square proportional, guys, square it. So if you square A, basically you will understand that A square is proportional to I naught. So 2 square A square cos square phi by 2 is proportional to the final intensity. Out of that, A square is just your original intensity. So this will come out to be 4 I naught cos square phi by 2. That is your final intensity. That's all. Sugita, I'm not making you feel afraid, but this is how board toppers are basically. I mean, if you want to get 98, 99%, that's how it is. Okay? Because they write ditto. And that's what you see. Sometimes many JEE toppers are not board toppers because JEE people, NEET people, what do we do? I know you're doing this, I can get it. Why do I want to hold like this? I will hold it like this only. So they go by shortest way, easy way, multiple ways. So we are more into logical thinking. We are not into that, memory based things. So don't worry. You might lose just half a mark, 1 mark. It's not like the teacher will give you 0. No, that will not happen. You might just lose a half mark or 1 mark. That's all. Devi Nandana can probably agree with me. Devi Nandana, don't you write everything, whatever is there in the book as it is. Niteshwar, please start studying now. Don't ask that question, sir, what to do? Start now. Can you use sign? Yes, bacha, you can use sign, but I am skeptical about it. If they have given cos, use cos. If they mention in the question, for sine you derive it, then use sine. Mr. Zerg, proportionality. Look at this, intensity proportional to square amplitude. So I naught was proportional to A square. So final thing will be proportional to this square. When you square this, what will happen? A square will come, but A square is I naught, so put I naught. That's all. Is that okay? Is that okay, bacha? Let's move on. Pranav Rai, this is in English. नीट में डीजी में वो हिंदी में था, इसलिए सेम सेशन दोबारा. ओके, लेट्स डू दैट. Even if I do d minus c by 2, how does it matter, Someshwar? Okay, guys, trigonometry. Tell me one thing. Cos of d minus c, isn't it cos of c minus d? Yes or no? Come on. Cos of c minus d, isn't it cos of d minus c? Yes or no? Someshwar and others. So does it matter? No. So trigonometry, you should know that. So I have done it conveniently because I know it will be easier. Moving on to the next one, guys. Okay. No problem. It's okay. You ask that out because these things will come in your exam and then you will get confused. Oh, why am I getting minus sign? In the Shreyas Sir's derivation, in book derivation, minus sign was not there. Now you know how to tackle that. Thank you, James Burke. Now, oh, this is done. I just did it, maximum, minimum. Now, part difference in a Young's double slit experiment. Now, again, if I did it for JEE, I will do it within 3-4 lines. But for boards, the derivation is completely based on algebra, Pythagoras theorem. It's not based on trigonometry. Please keep that in mind. Okay. Now, what you need to do is, first of all, there are 2 sources. Understand the process, how you have to derive. Show the 2 sources, the slits basically. This is the main source illuminating the 2 slits. D, small d is the distance between the slits. This complete thing is capital D, which is more than small d. And this is your screen. At some random point, these 2 waves meet, but they do not arrive simultaneously. There is some path difference. Only that path difference can give rise to other formulas. So the aim is to find out what is the path difference at P. Since S1 reaches earlier, S2 reaches later, so the path difference will be S2P, bigger one minus the smaller one. That's something which you should realize. Now, what is done in the derivation is that they try to find out S2P separately, S1P separately by using Pythagoras and then use basic algebraic identities like a plus b whole square, a square minus b square, a minus b whole square. These are the basic identities used. So let's do it one by one. So S2P square minus S1P square is equal to, let's try to figure this out, guys. Maybe I can write it slightly left side. I will need a lot of space. So S2P square I'll try to find, and then also minus S1P square. Let's try to figure this out. First of all, S2P. S2P is this line. So what you do is draw a triangle and look at this triangle over here. Now you'll notice that the base is nothing but D. S2P is the hypotenuse. Height is y plus this distance. This distance is half of the width between the slits. So it is D by 2. So this is nothing but D by 2. So Pythagoras, hypotenuse square is base square plus height square. So it will be nothing but base is D square plus height, which is y plus D by 2 whole square. Cool, everyone? Okay, this is first term, minus. Next term, S1P. Look at where S1P is. S1P is this one. Cool? Draw the base. Draw the height. The base is still D only. Height, this much is y minus this much. This much is this much. This is half of D. So this is nothing but D by 2. So from y, you take away D by 2, you get the height. So that shall be D square plus y minus D by 2 whole square. Now just expand and see what happens. The first term will be D square plus A plus B whole square is A square plus B square plus 2 into A into B. Next term, okay, let me just put it in the brackets, minus, look at this one. This is D square plus A minus B, oh, I forgot that square. A minus B whole square is Y square plus D square by 4 minus 2 into Y into D by 2. That's the second term. Everybody fine? Oh, yes, I'm the best biology, sir. Thank God. Oh my God. What are you guys saying, man? Concentrate. Now, this one. If you notice, many terms are going to get cancelled. Believe me. D square, D square. Y square, Y square. D square by 4, D square by 4. This and this, no. Minus minus becomes plus. Be careful about it. So this will become 2y. Acha, the 2 also gets cancelled. So yd will come from here. Minus minus becomes plus. Here also you will get yd. So you will basically get 2 times of yd. Everybody fine till this point? Okay. Now the last thing is over here. S2p square minus S1p square. A square minus B square is A minus B into A plus B. Everybody knows this? So why you put S2p square? That's what you will understand, Mr. Zerg. Why is it square? Look at this. This term on the LHS, is actually S2p minus S1p into S2p plus S1p. This is the LHS, and RHS I just figured it out. It is 2yd. Got it? Now why did I write it as square? Because this part is just delta x. This part is just delta x. This part is very easy to find. I'll tell you why. If you concentrate on this arrangement, you will realize both the sources are so close. The point P is somewhere here. This is D. This is capital D. This is your point. Be it S1P or be it S2P, roughly their lengths are D only at that point. Do you agree? Why is that? Because D is much larger than D. They are very close. So they are very close to each other. The lines are almost parallel. This line, this line, this line. It's almost the same thing. You can see that. Does that make sense? God is love. I'll be making the superhero series for all the chapters. I have told this again and again. Please keep in touch with the community posts I keep making. So now this is nothing but D plus D. This is 2yd. So D plus D is 2. So 2 times delta x into D is equal to 2yd. 2 cancels. So delta x is equal to y small d by capital D. That's it. That's the answer. That's your part difference. Got it, everyone? Trigonometry 1 is so much cooler and better, na? Yes, not line by line, important. All the important ones. Every line is not important, obviously. Coming, Sanjit, now to fringe. Fringe width. See, you asked it, it came. Evangeline, you will not need anything else apart from my marathon sessions and the assignments I gave you, the mock tests, the questions I gave you, and whatever strategy video I asked you, whatever I asked you in the strategy video. Do NCERT back exercise, NCERT underline, previous year papers, solve some school papers, and then write the derivations, practice. Whatever things I have told you, just follow that. You will not need anything else to score beyond 30 marks. Trust me on that. Selva Karthik, this is the CBSE derivation. If I do it for JEE, see, I'm a JEE teacher, NEET teacher, so I will do it very differently. Okay. Now, going to the fringe width part, the first thing you need to know is, okay, first of all, let me call this as Y. Okay. At any point, how do you know, or how do you locate a point which has constructive or destructive interference? That's the first thing to start with for finding the fringe width. So let's say I want to find a point which undergoes constructive interference. So what do we know about constructive interference? For constructive interference, that is basically a maxima. That is basically for a bright region, bright fringe. We know that the path difference should be how much? What is the value of the path difference? It should be any multiple of lambda, the wavelength. So it should be n times of lambda. Do you remember it? Very good, Anirudh. Yep. No, not n lambda by 2. It is n lambda. Correct. Now I know the value of delta x. So go back. Delta x is yd by d. Okay. So delta x is y small d by capital D. This is equal to n lambda. So solving it over here, y shall come out to be n times lambda capital D by small d. Done. This is the location of any bright region. By the way, similarly, you can also do it for a dark region. I'm not solving it. You can do it right now or later on. So y will come out to be n plus half times lambda d by d for a dark region. You can do it. Try it out on your own. Okay. Now, having said that, let's try to figure out what is the fringe width. So it's very easy. So let's say this is your nth fringe, nth bright fringe, and this is your n plus 1th bright fringe. This will have some coordinate yn, and that will have a coordinate yn plus 1. This is third fringe, this is fourth, this is fifth, this is sixth. n plus 1th. So what is the meaning of a fringe width? Fringe width means from one bright to one bright, or from one dark to one dark. You find any two distances, it is the same thing. So this is beta, which is your fringe width. So fringe width beta shall be yn plus 1 minus yn. Obviously, this is this minus this. From this, if you take away this much will be remaining, which is your fringe width. So substitute now. N plus 1 will be n plus 1 into lambda d by d. This n, if you substitute, it will be n times lambda d by d. Okay, this is equal to beta. So therefore, beta will be equal to, you can see, n lambda d by d plus lambda d by d minus n lambda d by d. These two cancels. So you will be left with lambda d by small d. That is your beta. Sorted. Mistake at the constructive. Why? What is the mistake, bacha? Everything is fine. Prem. Any crash course available for me, for Vedantu, only for physics? Only for physics is not available. It's physics, chemistry, maths. I would, physics, chemistry, biology. You take it up for all the subjects. Don't think that I have to only attend physics. You never know how you will use the other three subjects, other two subjects. And plus the mock tests is very important, which you can give at your convenient time and do the analysis. All right. Independent of the nth value. Yes, all the, you should know the difference between Young's double slit experiments interference pattern and the single slit diffraction pattern. Over here, the intensities are decreasing, same or increasing as you go from one maxima to other maxima. 2n plus 1 by 2 because n starts from 0 usually. Hari. Selva, I would not prefer to solve it by a method. It all depends on the examiner. Why take risk is my question. I lost marks in board exam because I was preparing for JEE. Yes, Sondera, correct. Very good, Kaushik. It is same. Intensity is same. In single slit diffraction, the intensity reduces. If they ask fringe width, should we prove it from YDAC? Abhinaya, it depends on the marks. So let's say, for example, it comes for 2 marks. If it comes for 2 marks, you will start by saying, we know that delta x for bright fringe is this and y is given by this. Hence, beta is this minus this. Solving, you get this for 2 marks. If it is for more marks, 4, 3, like that, then you have to probably start from here. See the marks and then solve the question. Okay, cool. Angular width is similar, guys. I mean, you can just do this part like this. If you take any fringe right over here, any fringe, it will subtend some angle. Let's say this is delta theta. This is the fringe width. This length, you can roughly take it as d. This is like your arc. This is like your radius. This is like your angle. And we know what's the relationship between length of the arc, radius and angle. Obviously, just use that. So beta will be radius into theta. So you can find the angular width. Is that understood? As simple as that. It's very easy. Okay. Cool. Let's move on. Yes, obviously, Shravana, if you are deriving it using trigonometry, if you don't mark theta, then how will the examiner know? Come on. See, always think that you are deriving it for a 9th or 10th standard student, your younger classmate. Just, one of my student told me that whenever he used to derive, he used to think that he's deriving it for his crush. He had a crush on some 10th standard girl. Imagine this. So he used to always think, I'm deriving it for her. So nice statements he used to write. Very nice, explaining body, very neatly labeled diagrams. So he used to think of his crush and write the exam paper. So cool, right? Motivation. He did not go out with his crush, but that's a different story, but he got good marks. Okay. Now, please don't say, sir, I don't have a crush. Whom do I crush? Sir, and what is a crush? Okay, let's go on. Now, okay, let's do this. Next part, this is the slit width, A. Reoptics derivation tonight, everything, Prithvi, whatever is going to happen, the entire party is tonight. The whole party is going to be tonight, okay? Now, screen. Alright, this is center. Now, what do you get is that when light goes through a slit, it bends, it spreads, and it creates an interference pattern just like YDAC, except for the fact that the widths will be different and also the intensities keeps on reducing. Now, talking about the fringes again, let's say this is a bright fringe. This is a bright fringe. Again, this is a bright fringe somewhere here. Again, a bright fringe over here. Wow, so cool. Okay, these are all bright fringes. Now, in between there will be dark fringes. This is your dark fringe. If you want to locate the theta for a dark fringe, then the formula is theta is equal to lambda by A. This is for a dark or a minima. For a minima, this is what it is. Okay. Apart from whatever derivations I am doing, nothing else will come, AR Devi. Okay. These are the most things. Prem Kumar, my crush is physics. That's very good. And your name is also Prem. Very nice. Now, the next thing, theta for maximas. This theta for a maxima. To locate it, this theta, you will put n plus half lambda by a, and this is your dark this is your bright fringe. These are the formulas which you should know. There is no derivation in this. Be thankful about it. The derivations are crazy for this. Okay. Now, having said this, you can also find the width of the central maxima if you would like. So, if somebody asks you to find the width of the central maxima, this is also there in your books. So, what you should realize is for a central fringe, for your central fringe, it is exactly in between the first dark fringe on the top side and also the first dark fringe below. So, in order to figure out that angle, this complete angle delta theta, the angular fringe width of single slit diffraction pattern, you should realize that what you actually need to do is just draw a horizontal line, divide it into two equal parts, and each one of them is the angle for minima. This is theta and this is also theta. This is theta, this is also theta. So basically your delta theta will be nothing but 2 times of theta, and each of the theta will be oh, I forgot that n over here. So sorry guys, my bad. Any nth fringe. So that n has to be there. If I don't put n, it is only the first dark fringe. So it will be nothing but 1 into lambda by a. So it is basically 2 lambda by a. So this is the angular fringe width of the central maxima. Oh, no, Anirudh, A is not the distance between the slits. Read it. Single slit. It's only one slit. It's the width of the slit. Be careful. This is the slit width, not the distance between the slits. Got it? We are going to come to that, Sarvari Srinivas. Is it necessary to mention that theta if you are using this kind of derivation? Yes, you should. Show it. You should learn all the diagrams, Nada. Nada, come on, bacha. Already you are learning only the term 2. Imagine last year or next year students are going to learn the entire 12th standard physics. Plus in the term 2 also you are seeing only 70% syllabus. 30% is already cut. Now in that also you want important means. Yeah, in some formulas they mention n minus half because for them Ashwin, the n starts from 1. If n starts from 0, it is n plus half. So if it is 0, lower number, you add it. If it starts from natural numbers, not whole numbers, then you put minus. That's all. Yeah. Width of central maxima and angular width. Yeah. Width of central maxima is different. Angular width is different. Width means the actual distance. So once you know delta theta, you can find the width. The actual width. So that width will be this d into delta theta. Width is in meters, millimeters, nanometers, whatever. Angular width is in radians or degrees. Can we use 2n minus 1 instead of n plus? Yeah, you can use. So why twice in Vedantu? Sandeep, that was done in Hindi. This is an English medium channel. That's the reason. Okay. Obviously, I'm not a fool to do it twice. So this is for all the English medium students. That is for all the Hindi medium students. Yes, you should. Okay. Let's do the next derivation. Okay. Now, let's start this. First of all, this is one of the most important and lengthiest derivation. All other derivations are smaller than this. This is a derivation for a curved surface refraction formula. What's the formula? If you remember it, please put it up in the chat box. Mu2 by V, remember? Mu2 by V minus mu1 by u is equal to mu2 minus mu1 by r. So that is the formula which you need to use, which you need to derive. Now how are you going to derive it? Let's figure it out. See, the whole idea is that the angles are going to be small, and when the angles are going to be small, we can use small angle approximation, which looks something like this. Sin theta is roughly theta, which is roughly tan theta. This is something which should be there in your mind. Since the rays are getting refracted, that's why I'm thinking about sin I by sin r and all of that. And I think I'll be also using tan formula somewhere or the other for trigonometry perspective. What should come in your diagram? Observe. Show a curved surface. Show one side is rare, one side is dense, whatever. Assume the refractive index n1, n2. Then show the ray coming from object. Draw a normal. Wherever that normal intersects the axis, that becomes your center of curvature. This becomes your radius of curvature. Cool? Next. What is the next thing? You will mark all the base angles. This side, and this side. All the three base angles should be marked. All the three base angles should be marked. Need not be alpha, beta, gamma. You can use your own symbols also. That is okay. Okay? Don't have to mark in the same order. You can mark this as beta, this as gamma, this as alpha. It's okay. Okay. Now, this is object distance, this is radius, this is image distance. That's something which you realize by now. And the next thing you should do is find the tan of alpha, gamma and beta. This is the first thing you are going to do. So let's start with it. First of all, for tan of alpha, look at this triangle. You will realize that tan alpha is nothing but opposite, which is NP, divided by this one, which is OP. Now, tan of small angles, these angles are very small. So small angles tan is angle itself. So this will be alpha. Similarly, let's try to look at gamma. So for gamma, look at this triangle. You will notice that gamma, which is roughly tan gamma, tan gamma is roughly equal to opposite NP by adjacent PC. NP divided by PC. Next is this big triangle over here. Okay, that's beta. So beta is roughly tan beta, which is nothing but NP by PI. So it will be NP divided by PI. Fair enough, guys? Normal and center of curvature, no. Normal is perpendicular. The normal will pass through the center of curvature, and the line which is the normal which passes through the center of curvature will also include the radius, because radius of any arc or circle is along the normal only. Okay, next thing. What you should do is, I think we'll have to use some exterior angle properties and all of that. So let's write it on the next slide maybe. So exterior angle properties for which triangles? Observe. First is this triangle. In this triangle, this is exterior, these two are internal. We know the exterior angle property. So exterior angle is the sum of interior angles. So exterior angle is I is equal to alpha plus gamma. Not just that, there is one more triangle which I want you to see, and that is this one. For this triangle, this plus this is gamma. So R plus beta is gamma. So therefore R is nothing but gamma minus beta. Now why did I do this? Because I and R are incident and refracted angles, and I can make use of sin I, sin R and all of that, and also approximate angles. So using Snell's law now. So now let's use Snell's law and see what do we get. So Snell's law. So sine of I by sine of R is equal to sine of alpha plus gamma by sine of gamma minus beta. But sine of angle is the angle itself when the angle is small. So this will be alpha. So this will be nothing but alpha plus gamma divided by gamma minus beta. And what is sin I by sin R? That is nothing but your mu2 by mu1, of course. Mu2 by mu1, or you can call it n2 by n1, because mu1 sin I is mu2 sin R. That's the formula. Is that clear? Now, It's simple. I'll tell you what you need to do. Just multiply it. So mu1 into alpha plus gamma is equal to mu2 into gamma minus beta. Now substitute all the values from before. So start substituting mu1. Alpha, see from before. What is alpha? NP by OP. So NP by OP. Just substitute it. It is nothing but NP by OP. Then check what gamma is. Check what gamma is. Gamma is NP by PC. Gamma is NP by PC. So it is NP by PC. So this is mu2. Again, this is NP by PC. Last thing, beta. What is beta? Beta is nothing but NP by PI. So this is NP by PI. You will notice from everywhere NP will cancel. And what is remaining over here is just the object distance, image distance and the radius. That's all. Trust me on that. So let's figure that out. What is object distance over here? U is technically minus OP because this is negative side, this is positive side. Light rays are going this way. R is technically plus PC and image distance is technically plus PI. So substitute it over here, and that's it. You will get the answer. Okay? What you're going to do next is just substitute. So mu1 by 1 by OP. Instead of OP, you are going to put minus U plus 1 by PC. PC is nothing but R is equal to mu2 into 1 by PC, which is R minus PI. PI is nothing but V. So 1 by V. And from there, you will get your answer, which is mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. Done. Okay. Sir, how to plot alpha, beta, gamma? What do you mean by alpha, beta, gamma? You can choose anything, whatever you want. You can choose this as alpha, this as beta, this as gamma. Alpha, beta, gamma are the base angles of all the rays: incident, refracted, and the normal ray. These are the three angles. With sign convention, yes, you have to substitute with sign convention. If you put plus OP, you will get a wrong answer. You will get something else, and then you will start wondering. So be careful with the signs. Okay, cool. Now let's make our formula. Should we draw all the three diagrams? No, I don't think so. I'll show you what and all diagrams you need to draw. So first thing is for lens maker. Lens maker as in you want to find the focal length. So if you want to find the focal length, obviously the object is going to be at infinity. So the rays will come from an object at infinity, of course. And I want you to treat a lens like two surfaces, curved surfaces. Surface here and there. Surface 1 and surface 2. So this happens to be your first surface, which will probably have some radius of curvature. I'll just call it R1. And you will also have this curved surface, and this is your second surface. This will probably have some radius R2. Okay, R1 and R2. So it's basically 2 times you have to apply that formula, nothing else is there. So let's apply this one by one, and we are interested in finding out the focal length. So this is your focal length. This is your focal point. This is your focal length. So let's do this one by one, starting with the first surface. Using mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. What is mu2? Mu2 is the refractive index where the refracted light enters. This is the incident medium. It enters inside the glass. Just look at this ray which is inside. We are talking about this ray. It's inside glass. So mu2 will be mu. V, I do not know where is V, because after it gets refracted, I don't know where it forms an image. Should we write the assumptions? Yes, write the assumptions. Okay, so if you observe carefully, this ray over here is inside glass. Actually, it would have gone and met somewhere over here. This point which I have shown over here is technically your image from first surface. This image from the first surface technically becomes the object for second surface. Keep this in mind. The ray bends, it wants to meet here, but that image becomes the object for the next surface. Okay. So now let's start writing things down. V is V1, I don't know where it is formed, minus mu1 is incident medium's refractive index. U, object distance, rays are coming from infinity, so do not forget to put infinity. Mu2 minus mu1, so mu minus 1 divided by R. R is nothing but R1. Okay, this is your first statement. So mu by V1 minus 1 by infinity is 0, so is equal to mu minus 1 by R1. Now do the same thing for the next surface. So for the second surface, do write the same thing. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. Now for the second surface, second medium is air. So mu2 will be 1. V is where the final image is formed. That means the final ray meets at the focus. So this should be focal length minus mu1 by U. Mu1. Okay, mu1 is this glass medium because this is the incident ray for this second surface. So this should be mu. Object distance. Remember, the object for the second surface is the image from the first surface. Image. So it will be just V1 is equal to mu2 minus mu1, that means 1 minus mu divided by the second surface. Now what you're going to do is just take this and this and just add them. Just simply add. That's it. That's all you need to do. This is the derivation method A.R. Devinanda. They have substituted infinity in the end. That's the only difference. What I have done, I have substituted infinity before only. If you open up NCERT also, you will notice they have first written general formulas before and after, and then what they have done is they have substituted infinity, and then they have substituted image distance and all of that. This is fine. It's okay. There is no problem in this derivation. You will get marks. Let me tell you that. Yes, you have to write for the first and second surface. And lastly, they have substituted V as F. See the derivation, you will see. Yeah. So add them, now you will get the answer. That's it. So 1 by F minus mu by V1 plus mu by V1 is equal to mu minus 1 by R1 plus 1 minus mu by R2. And therefore these two people cancel, so 1 by F is equal to, take mu minus 1 common, so it will become 1 by R1 minus 1 by R2. That's it. That's the Lenzmacher formula. We don't need to use sign convention because I have not substituted the value of R1. R1 is just left untouched. If I put R1 as something like minus ON minus I don't know, PC, something like that, then I have to put plus or minus. R is a variable whose value needs to be substituted with sign. So I don't need to put plus or minus R1. No, that's why yes, I'm not substituting minus R2 and plus R2. Getting it? No need of minus. That is why don't use that complete derivation of NCERT. It is very confusing if you see that. Yes, I know in NCERT, what was the use of sign? You tell me that. Because while using this formula, what they have done, I'll tell you what they have done. They have put some numbers or some alphabets, AP or PI or something like that. Okay, they did all this. Here also they have put the radius of curvature is some alphabets, AB or CD or something. Again in the end, they wrote that AB, CD, PI, whatever back into R1, R2. So they put and again took it back. No use. Over there we needed it. Over here we needed it because, say, over here, all the trigonometric formulas, whatever I wrote, where is that trigonometry? Trigonometric formulas they had some variables like PC, OM, distances were there. So in order to convert the distance into the optical terms, U, V, R, that's why I substituted with sign convention. Yeah. So That's why CBSE students face a lot of problems. More problems, you know who face? NEET and JEE students. Why? Because JEE students, NEET students, they study in such a simple manner. You open NCERT and then you're like, oh my god, what is this? Okay, now I'll tell you what. See, this exact same derivation, whatever I taught you now, the same, not this one, sorry. This one. The same derivation works for lens formula. V1 is not F, V1 is the intermediate image. V1 is the image by first surface. So first image is formed somewhere else. The next image is formed at the focus. 2 times refraction happens. Keep this in mind, 3G. First refraction is not going to give the answer. Second V is the F. Okay. Now the same derivation works. I'll tell you why. Because instead of assuming the object at infinity, you assume the object somewhere. You assume the object is somewhere and the image is not formed at focus, the image is formed at some V. It's the exact same derivation. That's all. You will see now. HK, R1 and R2. What is R1, R2? R1 and R2 are the radii of curvature of the surface. Wherever the light hits first, that becomes your first surface. The other one becomes your second surface. If you draw that line, draw that curve, you will see it's a circle. Center will be here. So this is the radius of curvature. So this is R1. R2 is the radius of this curve. So this is R2. So for the first surface, when I use this formula, I put R1 because for this surface, I have to use this R1. For the second surface, this is the radius. So that's why I used R2. Is that making sense? Does R2 always negative? No, R2 is not negative always, Prem Kumar, because if you take a concave lens, what will happen? R2 will be positive, R1 will be negative. Got it? So don't by heart like that. Yes, before starting the derivation, just mention in brief and start the derivation. Key. This is focal length, this is the distance, this is object distance. So mention all that. Yeah, mention all that. Thank you, Anisha. Yeah, underlined PDF will be, Jania, it is already uploaded. NCERT is already uploaded. Only this will be uploaded after the class. I hope all your doubts are clear. Okay. Now, for lens formula, I don't know. Shanti, you just see my method. It is so simple. The same method. Now, if you guys understood this part, you will understand this part also. It's so easy. Trust me on this. What you need to do, assume that the object is here. Assume the object is here. This is your object distance, U. Okay. This is your first surface. This is your first surface. The rays from the object will come here. Then inside, they will obviously refract. They will refract. And again, they will come out. So maybe some other color. Okay. Like this. This is where the final image is formed. And this distance is V. And this surface is your second surface for refraction. Observe this carefully. It's the same thing. This is for the first surface. For first surface, if you write mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. Mu2 for this surface is this medium, glass medium. It's entered inside glass. So mu2 is glass refractive index. V, I do not know. See, the ray after going inside, I don't know where it wants to go. This is your V1. This is your V1. This is that intermediate image. So basically this is your V1. Next, minus mu1. mu1 is incident rays in air. So put 1. Object distance is U. So just put U. mu2 minus mu1, U minus 1. R will be this surface's radius. First surface radius is R1. Now, for the next surface, for the second surface, what you do, use the same formula. Again, mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. Check one by one. Mu2, second medium, this medium, air medium. It has come outside, so 1. V is the final image distance, which is V itself. Minus mu1 is the glass. It's inside the glass first, so 1. u is the object distance. Keep this in mind. This image becomes the object for the next surface. This image becomes the object for the next surface. I will do that, Thalapati Vijay. Is that clear? Is that making sense? Yes, for semiconductors also it is there. Okay, so basically this u will be V1. This is the most important part. The image of the first becomes the object for the second. That's all. This image becomes the object for the next surface. That's it. Now this will be, oh sorry, what the hell did I do? mu2 minus mu1. This is supposed to be mu. Oh, sorry, my bad. mu1 is whatever is there is inside. This will become 1 minus mu divided by radius. Radius is nothing but r2. That's it. Radius is r2 because this is the second surface. Done, done, done. Now just again add it. Nothing else is there. Just add the two. Adding. Just add the two and see what do you get. Mu by v1 minus 1 by u plus 1 by v minus mu by v1 is equal to mu minus 1 by r1 plus 1 minus mu by r2. This is what you get. Now solving, you will get the final answer. Mu by v1 will get cancelled. So 1 by v minus 1 by u is equal to, this is nothing but mu minus 1 is common, 1 by r1 minus 1 by r2. Now what is this? This is focal length. So this is 1 by f using lens maker formula. So that's it. That's your lens formula. Sir, V1 will be before the final image because the second surface ray will go away. Matlab that's okay. This is just for your understanding. Kaushik, don't worry about it so much. Sir, for atoms lesson, will they give atomic number in the question? For simple elements like hydrogen, helium, lithium, don't expect. For some other elements, yes, they will. Yes, U1 will become U in the second surface. Yes. Refracted ray not parallel to the principal axis. No. It's just, I've shown it random diagram, so don't take it to heart. Ki, sir, is it really parallel? No, it is not parallel, guys. It's some random ray. Okay. Yes, this is exactly the proof for lens maker also, no? See, what was there? First surface, second surface, add, you got it. In this case, first surface, second surface, add, you get it. Same derivation is there. Only difference is in lens formula, object is randomly placed, image is randomly placed. In lens maker, object is at infinity, image is at focus. That's all the differences. See if you guys got it. Can we move ahead? Okay. Some basic formulas over here for magnification. Let's see this. Magnification. It's image height by object height, which is just V by U. You should know this formula, of course. If M is positive, it means it is obviously erect, and if M is negative, then it is inverted. And magnitude of magnification, if it is more than 1, it is enlarged. It is enlarged. And if magnitude of the magnification is less than 1, it is diminished. That's all. So these are some basic pointers which you should know. Apart from that, the power of the lens is 1 by f. F is in meters, power is in diopters. Very good. Yes, there could be different methods, Sriram, but you don't have to use random methods. Use methods which are exactly equal or similar to CBSE methods only. Okay? Okay, can we go ahead? I think you... okay. All right, Harshint Pro. Now, prism derivations. Tomorrow I'm going to give all the important questions from all the chapters in one shot. And prism, what are the important derivations? First, angle of prism, incident angle. Some books use E, some books use I2, but I think I can use I2, that's okay. This is internal refracted angle. This is your internal refracted angle, R1, R2. The dotted lines are the normal, of course. So first thing is finding the relationship between these angles, and the best way to do that is something like this. If this is R1, this is 90 minus R1, because this whole angle is 90 degree. This is also 90 degree. So this angle is 90 minus R2. Now, in order to find the relationship, the first thing you should focus on is this triangle over here. This triangle over here. In this triangle, if you notice, sum of all the angles of a triangle is 180. So sum of all the angles of a triangle is 180. So what do you get? This plus this plus this, 180. Come on, let's do that. So A plus 90 minus R1 plus 90 minus R2 is equal to 180. Okay, so basically what do I get? A plus 90 plus 90, 180 minus R1 minus R2 is 180. So A is equal to, shift these two people there, 180, 180 cancels, is R1 plus R2. This is your first result. Hello, Matesh. Yes, this is not minimum deviation, Sharvana. This is not minimum deviation. Please note that. Yeah. Okay. Next thing. These are generic formulas. This is not for minimum deviation. Wait a minute. We are going to come to that. Now, the next thing is deviation. Now, for deviation, you should know that the initial ray was going like this. So it deviated by delta 1 here, and this ray was going like this, so it deviated by delta 2 here. So if you notice, this whole thing is your final delta. This is your initial delta, this is your final delta. And for refraction, deviation is always I minus R modulus. You should know this formula. It's very obvious because if you draw the normals, it is seen that the deviation always is the bigger angle minus the smaller angle. That's all. Now, thin lens in contact ARGB, that's a very simple derivation. You can just have a look at it on your own. Okay? It's very similar to just like adding the powers using this guy's image is that guy's object, this guy's image is that guy's object. Just do that. It is very similar. So that's not very important, but that is very simple also at the same time. Okay. Now over here, what you can do is the total deviation, this whole deviation is this plus this. So it is delta 1 plus delta 2. Now delta 1, this deviation is this angle minus this angle, big minus small. So it is I1 minus R1. Delta 2 over here is big angle, I2 minus small angle. So it will be I2 minus R2. So I1 comes together, so it will become I1 plus I2 minus R1 and R2 come together, but I already know this is A, so this will be I1 plus I2 minus A, that is your delta in general. That's all. So these are two important derivations based on geometry, you can get it. But probability for this is less, but it's very easy to remember, very easy to do it. Now comes the minimum deviation part. Okay, now for minimum deviation, this diagram is slightly wrong. Let me tell you that. Actual diagram should have been that, the ray is parallel, but ignore that part. So I don't know, I will have to close it, again edit it and all of that. But just please understand that this should be parallel to the base. This is your base. It should be parallel to the base. For minimum deviation, we are talking about minimum delta, minimum deviation. So when minimum deviation happens, what you will see is this angle and this angle are equal, these two angles are also equal. So basically I1 is equal to I2, R1 is equal to R2. Also, what you can do is, since R1 is R2 and we know R1 plus R2 is equal to A, R1 or twice R1 is A, or R1 is just A by 2. This is one thing. Second thing, here you can see delta is I1 plus I2 minus A. So I1 and I2 are equal, so 2I1 minus A. So basically I1 will be A plus delta 2 comes below. These are some tricks which you can use for solving the problems. Now there is one last formula over here which is for refractive index. Refractive index is sin I by sin R. Refractive index is sin of I by sin of R. Now just substitute it. Sin of I means this one. So it will be sin of A plus delta by 2, and this is nothing but sin of R1, which is nothing but just A by 2. So this is that formula again, which you should know, but here the delta is only minimum delta, least deviation. This formula also gets approximated for thin prism. For thin prism, angle A is small, all the angles are small. So when all the angles are very small, what happens? Sine theta becomes theta. So you will see mu will be equal to, numerator will have A plus delta m by 2 divided by A by 2, 2 cancels. So it will be A plus delta m divided by A, cross multiply. So mu A will be equal to A plus delta m. So delta m will be A into mu minus 1. That's the answer. You have to substitute it with the sign convention, Mr. VJ. Is that okay? You cannot substitute it directly. You have to substitute with the signs. You'll get wrong answers, not just wrong in sign, but also wrong in magnitude. Matesh, solve more mock test, see your weak points. Wherever your weak points are there, attend those classes. Watch the recordings of those classes. Okay, cool. How many times I have read NCERT? Many times, yeah, I don't know, lost count now. Okay, now most important derivations. Will I go for the graphs as well? Syed, I have done the graphs, in the one shots just in the last few days for all the chapters of term 2 physics. Please go through the graphs, PDFs you download, whatever graphs I have done over there, whatever graphs I have underlined and I told you please go through it, only those graphs you do. That's all. Formula sheet, whatever I write will be available. Now, what you need to do for simple microscope is that, first of all, remember that the ray diagram is such that you place the object between the focal point and the lens so that the image is enlarged, virtual and erect. So, this is where your object will be and much before the focal point, and what you will notice is that probably your rays go like this. Oops, sorry guys. I'll probably draw the image first, that is always easier. Okay, so one trick of ray diagrams is always show the image first because you know where it is and then draw the ray diagram. Don't show the focal point and all those things. It becomes easier. How many of you do that? Please tell me. Isn't it easier that way? So that you don't have to use too much of your brains now. Okay, now you can show more rays and all of that. That's okay. Alright, so you can show even more like this because it goes like that and all of that. Okay, so this is your ray diagram. This is where your eye is present. You are holding the magnifying glass very close to the eye. That's what it is. And this angle over here, this angle, I will call it theta 1. Theta 1 is the angle subtended by the image. You can see that it is by the image for an aided eye. Aid means help. You are using magnifying glass. With the magnifying glass, you are seeing it big. So that is the angle which the image subtends at your eye. Diffraction syllabus is not there. So guys, remember one thing. If you hold an object close, the angle which it subtends increases. Now, if I observe this pen using a magnifying glass, it will look big. So that's the angle subtended by the image of that object at my eye. Everybody clear about this? Next thing is, if you hold this object at a distance of d, from your eye, which is unaided. This was for an aided eye, in case you are not able to read it clearly. I'll write it over here. Image by aided eye. Aided eye. This, if you notice, this is unaided eye. This will subtend some angle. I'll call it theta naught. So theta naught is basically the angle subtended by object by unaided eye. Now if you take the ratio of these two, that is called as the magnifying power. What is that called? That is called as the magnifying power. Imagine if I hold this pen, it subtends 2 degrees angle. It subtends 2 degrees angle. I put a magnifying glass, suddenly it becomes 10 degrees, huge. So 10 by 2, which is 5. So that is called as the magnifying power. Got it? Everybody? No, Selva, I did not eat dinner. There is nice fish which is cooked at my house, and I'm going to have the fish after the session is over only. Okay? Thalapathy, if you solve the mock test, then see where you went wrong, analyze the mock test. Just see those questions. Write it. Practice those questions 5 times. 5 times. Okay. Now what you need to do is that, the final image is formed at D. Now we are going to talk about the magnifying power formula for these things. Okay? So we are going to just derive the magnifying power formula for these things. So let's try to figure these bits out. First of all, where is it? Yeah, magnifying power is this by this. So therefore, magnifying power, since it is theta 1 by theta naught, can I not say theta 1 is image height, or I can say it is roughly equal to tan theta 1 by tan theta 2, which is roughly equal to opposite by adjacent. Opposite is image height, adjacent is D, and tan theta 2, it was not theta 2, it was tan theta naught. Tan theta naught is object height by adjacent. So object height by adjacent side, which is D, so which is HI by HO, which is just your magnification. So the magnifying power comes out to be magnification of that lens for, least distance of distinct vision. This diagram is enough. If you draw diagrams, you will get half a mark. If you complete the derivation, then you will get all the marks. Now, what you need to do next? Magnification is V by U. So you are trying to find out the magnification power. So V by U, I can write it as V into 1 by U. Now 1 by U, think about it using lens formula. What is lens formula? Come on. 1 by V minus 1 by U is equal to 1 by F. So from here you will get 1 by U is equal to 1 by V minus 1 by F. Rearrange, that's what you get. So you put 1 by V minus 1 by F right over here. Now solve this further. So this will become nothing but 1 minus V by F. Last step. What is V? Image distance. Where is the image? Image is formed at D but negative D. Look at the sign convention. D is distance. D is distance. So 1 minus D by F. So that will give you 1 plus D by F. That's your magnifying power. Got it? Now the last thing over here is, if at all they ask you for magnifying power when the image is at infinity, it becomes very simple. You can read it also, you will understand it very easily. Logic is the same. Angle subtended when you take the help of the glass, magnifying glass, upon angle subtended by without the instrument, without anything, without any help or without any aid. So just do the same thing, you will get the answer. It's very easy. What is D? D is least distance of distinct vision. So this is the formula when you are holding it at the least distance of distinct vision. That formula D by F is when you are using it under normal or basically relaxed condition. The eye is relaxed, then the image is formed at infinity. Image is formed at infinity. Got it, guys? Done, done. Can we move ahead? Important derivation. I hope this is entering your head. Okay, tomorrow at the same time, 7:30, guys. Yep. So correction. Did I not write 1 plus d by f? Oh, sorry, that line looks little bit longer. I meant 1 plus d by f. Yes, thank you. It's only there here, 1 plus d by f. Got it, guys? Alrighty, moving on to the next one, compound microscope. So in compound microscope, what you need to realize is the object is placed near the objective lens. This is called as the objective lens. And you have the second lens which is close to the eye. That's why it's called as the eyepiece. And this is called as the length of the tube. This is called as the length of the tube, meaning distance from one lens to the other lens. Now, in the arrangements that is given in your textbook, the only one arrangement that you have is when you place this object at the focus of the objective, very close to that. So when the object is very close to the focus, image is formed very far away, very far away. In fact, so far that it forms very close to the eyepiece. So you will see that the intermediate image that is formed, is formed almost here. This I will call I1. This is your intermediate image, very close, very, very close to eyepiece. Eyepiece, very, very important. And this becomes the object for the eyepiece lens. Eyepiece lens. That is the first thing you should keep in mind. Accordingly, you draw the ray diagram. Don't draw ray diagram and then figure out where it will land. Draw this and then show the ray diagram. Like this. Okay, like this, and then show. Okay, this way. Show the rays later on. Draw the images, objects first. Now, what you should remember is that the eyepiece actually acts like a magnifying glass. For a magnifying glass, where do you place the object? There is hardly anything left, I'll tell you, Mr. Zerg. After this one, telescope is there and two small things. I'll take maybe 2-3 minutes break and then we'll continue the rest. Yeah, the binding energy calculations, I don't think the quantitative aspect is there. Yes, between focus and object, between focus and pole, not O. Focus and pole. You place the object between focus and pole so that the image is enlarged. Now the exact same thing you do over here. You make sure that this image lies between the focus and the pole of this lens. So this eyepiece actually acts like a magnifying glass. Magnifying glass. So the focal point is somewhere here. So this is the focal point of the eyepiece. What you will see is an extended image right over here maybe. So this is your final image. You can obviously draw the ray diagrams. Like this. This is your ray. That's it. Done. Show more points. Obviously, whatever is there in your NCERT book. I've given you the idea. Now you can complete the ray diagram. Now, here is the final verdict. Observe. This image is formed very close to the eyepiece. So, first time, because of the objective lens, the magnification is given by V by U. V is almost the tube length. It's almost this distance, L. So I can almost put this as L. U is exactly this distance, so it is basically minus FO. Minus FO. Do you guys understand it? Why it is minus FO? Oh, no problem. Optical center. Okay. Fine. Optical center is also okay. Cool. So this is minus FO because this is the object distance. I've just mentioned it over here. Second thing, what I'm going to do is, for the magnifying glass, that is basically for the eyepiece, we know the magnifying power. Magnifying power depends whether it is 1 plus d by f or just d by f. This is Fe, depending on whether it is least distance of distinct vision or whether it is relaxed vision. Your eyes are relaxed. So accordingly, we will use this. So your total magnifying power of your microscope turns out to be just this into this, nothing else. Just this into this. That's all you need to remember. So for example, relaxed condition, it will be nothing but L by F naught, minus sign is there because it is inverted, that's all, otherwise it's fine, into D by Fe. This will be for your relaxed condition. That's what is there in your books. It's a multiplication, magnifying, total magnification is this by this. V is L. Look at this, the image distance. Look at this. What does this mean? When I wrote this statement, what does this mean? The image is formed very close to this. So image distance is roughly equal to L. And when I wrote this object is at F naught, what does this mean? U is roughly minus F naught. That's what I've substituted. In NCERT the minus sign is not indicated, then you also don't indicate. But actually the image is finally inverted. The image is inverted. Is that okay, Prem Kumar Thalapati? Okay. Rahul Krishna, ideally it should not be there, but I am just doing that, mass defect related problems just on the safer side, because they have given just the qualitative aspects of it. I doubt 90% it should not come, 10% we are not taking chances. Yes, so the tube length will be roughly, actually the tube length is image distance of the objective lens plus object distance of the eyepiece, but this is roughly equal to V only because the image is formed very close to the eyepiece. That's the reason for that. Now for astronomical telescope, how you should draw the ray diagram. Starting with object at infinity. Object is very, very far, that's the only difference. So the rays will come from very far away distance like this. If the object is at infinity, where will the image be formed? Obviously the image will be formed at the focal point. So the image, but this is intermediate image, will be formed the focal point of this guy. What is this guy? This is your objective, at objective. Now this part of that lens, which I call it again the eyepiece, eyepiece again acts like your magnifying glass. Keep this in mind, there is no difference. Again this will act like your magnifying glass. Object is placed between focal point and the pole, so the image is enlarged, virtual and erect, but already the image is inverted, so it will become big over here. So you will notice that your final image, will be formed very, very far away. This will be your final image at infinity, very far away. And if it is forming at infinity, that means this object which is there should be very, very close to the focal point of the eyepiece. So FO is also here, FE is also here, very close to each other. Is that understood, guys? What happened? I'll repeat. Object was at infinity. So where will the image form? At focal point. Now, the final image also forms at infinity or very far away. So this point should be the focal point of the other lens. So this is very close to the focal points of both the lenses. Clear, guys? Distance between object and eyepiece lens is called as the tube length. Yes, Sarvana. Now I hope that is clear. Okay, VO plus VE is the exact value, but remember we did an approximation that the image is formed very close, so we've ignored that object distance UE. So U is 0, roughly 0, hence we get it roughly equal to VO. Okay. Now let's have a look at this. So this length of the tube, since this is both the focal length of this guy and this guy, so this will be roughly equal to F naught plus Fe. F naught plus Fe. And the last thing is magnifying power. Magnifying power is F naught by Fe over here. This is something which you should know. This is for normal adjustment. Image is formed at infinity. Keep all these things in mind. In telescope also the length is technically the length, see this is approximate. Length is exactly equal to where the image is formed. Where is the image formed? At V. Image is formed here from the objective lens plus object distance from the eyepiece. This is exact value. But VO is roughly FO, UE is roughly FE. That's why this formula comes. Now this final image is inverted, so you can also put a minus sign because of the inversion. That's all. Now let's go to photons and all of these things. First is the properties of photons. You should know all the properties of photons. Photon is the particle nature of light. Photon carries energy in the form of packets. The packet of energy is given by HF, which is also hc by lambda. After substitution you get it as 1240 electron volt, where lambda is in nanometers. This is the energy of the photon. Second thing, and photon, since it's a particle, it also has momentum, but the momentum formula is obviously not mv, and by the way, the energy formula for a photon is obviously not half mv square. Keep this in mind. And the momentum formula is nothing but h by lambda, which is also energy of that photon divided by lambda. Oh sorry, not lambda, c, divided by c. This is the photon's momentum. Photons, when they hit something, they will transfer momentum. They can also supply energy. So momentum and energy is always conserved. Photons are chargeless particles, so they will not be affected by magnetic or electric fields. Keep this in mind. Bye bye, Miss VG. Okay, now after knowing this, let's move to the next part, which is for particles. See, whatever I am discussing over here in this part, this whole thing is basically the particle nature of light. That particle nature is called as photon. The exact opposite now, the wave nature of particle as in mass m. This wave nature is called as matter wave. And the wavelength of such a particle is given by lambda is equal to h by p, where p is nothing but mass into velocity, your standard momentum. That's all. I hope. No, Zener diode is not there, Thalapati. Why not equal to 0.5 mv square? Why? Because photon does not have mass. Mass of a photon is not defined. That's why you can't write m into v also. That's the reason, Prem Kumar. So these formulas are only applicable in particles. Not many people know that. I think, momentum is h by lambda, momentum is m into v. Then suddenly one day I asked, why you don't use m into v for a photon? And people get confused. Oh, then the correct answer is mass is not defined. That's why the formulas only are different. Keep this in mind. Okay. How does the intensity vary with the width of the slit? Asiya Hajit, it varies proportionally to it. If the width of the slit is more, intensity will be directly proportional. So if it is 2 times, intensity will become 2 times, 4 times, 4 times. That's all. Photons is not massless. Photons mass is not defined. It is not defined because you cannot find a mass at, you cannot find the photon at rest. Yes. Is it square or not? No, it's the amplitude which is the square. Intensity is proportional to the square of the amplitude. Intensity is proportional to the width of the slit. There is complete difference in that. Okay. Now having said this, the energy of a particle, this is half mv square. Keep this in mind. This is half mv square. Lastly, momentum, I just told you. Okay. Now, if you want, you can write also this energy, which is actually kinetic energy. If you think about it, it's also p square by 2m. You can also write p is equal to root of 2 times m times kinetic energy. It's one and the same thing. So you can replace it. You can substitute it here, and you can also write lambda in terms of kinetic energy as well. That is also an option. Many times you might have to substitute. Last thing over here is all about accelerating a charged particle. So if you take a charge and if you accelerate it by voltage difference of delta V, then it acquires kinetic energy. That kinetic energy which it has acquired is the charge into the voltage difference. Keep this in mind. So sometimes you can have questions where voltage difference is given and lambda is asked. Voltage difference is given and lambda is asked. Prem Kumar, P's unit is just like your momentum, kg meter per second, nothing more, nothing less. Okay, and so think about it. If I substitute kinetic energy here and if I substitute momentum over here, then over here what do I get? Observe, lambda in terms of voltage difference. Now best part is many times you don't have to substitute all the values for an electron. So if you substitute Q into delta V here, this value substitute here, you will get some big expression, but there is a very easy way of doing it. 1.227 I guess divided by root of delta V. So this is the formula which you can remember directly. This is the formula which you can remember. Okay, so if it is not visible, if it is not visible, lambda is equal to 1.227 divided by root of delta V. This can be a direct formula. Yeah, this answer is in nanometers. So this substitution which I have done will directly yield this result. Photon is the particle of light. Photon is having a quanta of energy. Quanta is a value whose multiples you will get other quantities. Like money is also in quanta, 1 rupee, 2 rupee. The quanta of money is 1 rupee. It's the smallest quantity, which every other thing is a multiple of. Okay, 1.227 is it 12 point? Sorry guys, just check it in NCERT. Is it 12.27 only? Yeah. Just check this out. 12.27, I think it is for not nanometers, it is for Armstrong, right? Just check it out. Is it for Armstrong or is it for nanometers? Just check it out. So what I had written was correct only, I guess. 1.227 nanometers. It's fine. Yeah, for Armstrong, yes, it will be 12.27. Just like here, it is 12400 when this is in Armstrong. So that zeros get changed. Here also, it is for nanometers. Zenboard, there is a formula, but you don't have to remember that formula. Solve it separately by finding image for the first lens, then the image for this next lens, and then finding the heights. Else you might get a wrong answer because that formula only works when the distance is small and other things. Okay, cool. So this is for your this thing. Now let's go to photoelectric equation. The entire process of photoelectric effect happens via, the energy of a photon getting into removing that electron. So to remove you will need phi, and the remaining is used in kinetic energy of the photoelectron. This is the main equation. Now this energy is obviously HF or HC by lambda. This is nothing but again HF naught or HC by lambda naught, and this over here is just charge into stopping potential. This is your stopping potential. So this becomes your photoelectric equation. Conservation of energy, exactly. Yes, Alpha Press. Okay, is that clear? In some semiconductor, we'll come to semiconductors after a while. 4 graphs which you must know. First graph, intensity and current. That's a straight line. Second graph which you should know is basically your current and voltage. That graph is like this for the same stopping potential. for different intensities, it increases. The next graph which you should know is current versus, okay, wait, I think I need some more space over here. The next graph which you should know is current versus voltage, again, but for different frequencies. So for F1, F2, you will see the Vs values are different. This is another graph. And the last graph is stopping potential versus frequency. And those graphs are straight lines. Slopes are same. Slope are same, which is just h by e. So these are the 4 must-do graphs for your exam. Is it okay if I only learn these derivations, Mariam? Then you'll get partial marks, na? What about other numericals and all those definitions? So make sure you go through everything. Is that okay? Can we go ahead? Alrighty. Now, radius, velocity, energy of hydrogen atom. This is Bohr's theory. Now in Bohr's theory, you should again remember the postulates. There are some 4 or 5 postulates which you should know. And you should also know the disadvantage of Rutherford's theory and what did Rutherford's experiment prove. All these pointers I have given it to you in the previous class. So Rutherford's experiment, told that the mass is concentrated at the center, it is positively charged, electrons revolve in orbits using centripetal force provided by electrostatic force, all of this. Disadvantages, it could not prove hydrogen spectrum, it could not convince on why the electron does not fall inside the nucleus, it did not talk about the energy levels, all these things. Now Bohr overcome all these failures of Rutherford's model and he gave some postulates. First, the electron revolves in circular orbits using the electrostatic force of attraction, and that's how it performs uniform circular motion. The second thing which he told was there are not many orbits in which an electron can revolve. There are some stable orbits. These stable orbits are the only ones where energy is confined, fixed, energy does not increase or decrease. That's why the electron does not fall into the nucleus. They are called as stable orbits. Now these stable orbits, you will notice that the angular momentum is quantized. It's integral multiples of h by 2 pi. That's the next assumption which he made. The next assumption was all about when an electron jumps from lower to higher or higher to lower orbit, then it involves an absorption or emission of a photon. If it jumps up, it absorbs a photon. If it comes down, it releases a photon. This is what it is. Okay, I hope this is clear. So using these theories, let's derive those formulas. It's simple. I will just show you the main steps. Rest all things are very laborious and boring. I'll not go through it. So first is using Newton's laws of motion, UCM and Coulomb's law. Just remember these words. So Coulomb's law, Newton's laws of motion, UCM and Coulomb's law. So according to this, the force of centripetal is mass into centripetal acceleration. That's your Newton's law. And centripetal acceleration is nothing but v square by r. Coulomb's law is over here. That is 1 by 4 pi epsilon naught. The charge at the center, it's a hydrogen atom, it is E. The charge which is revolving is also E, but minus sign. Mass is m. Mass is m. It is moving with a speed of v and the radius of that orbit is r. Radius of the orbit is r. So it will be nothing but force of attraction. What is it? K q1 q2 by r square. Solving this, you shall get r because one of the r goes. So take r on the top. So we'll get E square by 4 pi epsilon naught mv square. I don't know v, we'll can figure it out later on. How? I'll tell you. The next thing you should know is quantization of angular momentum. So quantization of angular momentum. That's all that is needed for the entire derivations of all these things. So we know that L is nh by 2 pi, h is Planck's constant, pi is pi, n is principal quantum number. First orbit n is 1, second orbit L shell n is 2, and so on and so forth. Angular momentum is mvr, this is equal to nh by 2 pi. Now from this r is equal to nh by 2 pi mv. Here also r I am getting, so you can solve them together. That's all. Equate the r's, you will get E square by 4 pi epsilon naught mv square is equal to nh by 2 pi mv. V cancels. From this you will get what is it, 2 pi me square divided by 4 pi epsilon naught m. This v has gone on the top, n and h will come below. This is what you will get. Simplify it. From this you will get velocity is inversely proportional to n. What will you get? Velocity is inversely proportional to n. That's all you should know. Is that okay? What if instead of momentum energy is quantized? Energy is also quantized in a way, but in a very different way in terms of photons, and the world will be a very different place. Okay, in which chapter is it easiest to score according to my view? I feel it is easiest to score in modern physics, right? That's what I feel. And semiconductor is theory, 7 marks. If you know the theory, you will get a lot of marks over there. Alifa, we have doubt sessions on the Vedantu platform on YouTube. It is very difficult to regulate it. So we have systems channels, we have class teachers, assistant teachers, models in which doubts can be solved, for all the students, no matter how big the class is, with the master teacher. So we have that going on right now in the Vedantu platform as we speak. Okay, now once you get this formula for velocity, you can also, what you can do is take this velocity and maybe substitute it over here. From this you will get r proportional to n square. So you will also get the formula for r. Is that okay? Yeah. Okay. Now I left out z, but you can put z also if you want. Yes, that's okay. So this is the derivation for hydrogen. If it is helium, then it will be 2e, and so on and so forth. So you can put a generalized term called as z. In boards there is no z. That's the funny part. That's what it is. Okay, now going to the next part, which is energy. So total energy is the kinetic energy plus potential energy. Kinetic energy is half mv square. Potential energy is minus 1 by 4 pi epsilon naught charge into next charge, which is, why I put minus sign? Because one of the charge is negative. That's why minus sign, divided by r only. Now the catch is that look over here. From the previous slide, you found the value of r, right? So you substitute the value of r, substitute it from before, and look at this. Velocity, do you see it right over here? Velocity, we found it. So substitute the value of velocity. Solve it, you will get some terms, but what is important is that n square will be below. So basically it is inversely proportional to n square. This is what it turns out to be. Very, very important. Bharat, it is called as the Pathfinder series. That is the last year. This year, what we might call it, we have not yet decided. But please start watching the 12th Pathfinder series detailed class. Don't rely on one-shots because you have 1 year. So usually my advice is, please don't watch one-shots. So you will see a lot of YouTube videos with one-shots have very good views. But you see the long-term lectures, less views, relatively. Be it any channel, not just our channel, any channel. That's the reason why many students don't get good marks. I understood. Not many students get very good marks. So that's the problem. Because students want to do everything fast. Instant Maggi 2-minute noodles. Okay. Anyways, the formula which comes out over here, if you find out the value, it's minus 13.6 by n square. This is an electron volt. Also keep this in mind that the potential energy is twice this energy, and the kinetic energy is just the negative of the total energy. This is also very important. So you don't have to remember separate formulas for kinetic and potential. Keep this in mind. Everybody fine? R naught and this value. So see, R naught is nothing but, or rather I will put it like this. One second. R is equal to 0.529 times n square Armstrong. 0.529 into n square, or 0.53 Armstrongs. Similarly for velocity it is 2.2 into 10 to the power 6 divided by n. This is in meters per second. This is what you should remember. Is that okay? I think I had given it before. Okay. How de Broglie explained Bohr's second postulate? So that is not there, Thalapathy. That one last diagram which is there in the NCERT, I think, like this. It is only for JEE advanced level. That is not there. That is not in syllabus. Ignore. Okay. It's got to do with standing waves and how that wave completely fits in that orbit. Can we move ahead? Sir, will we be expected to deduce the formula for U is equal to 2E, or can we just like use these formulas? Ishwar, if it's a question which says what is the kinetic energy of the electron in the second orbit, directly use this. But if it says derive the formula for kinetic energy and potential energy of an electron in Bohr's atom, 3 marks, you will have to substitute. You know, if I was smart, I will not choose that question. Why? So lengthy it is, waste of time. Instead, I will see what the other option is. Now, if I do not know that other option, then I will do it, because I know I will get it. I will waste some time, but I will get it for sure. So, you choose wisely. Don't choose lengthy options. Time. Yes, it is important, Ajay. I mean, what if you are not left with options? Wow, now we just have your mind maps for nuclei. So nuclei, what are the important topics? So guys, I have given everything that you need. You need to know the size of the nucleus, the nuclear parameters, mass defect, the nuclear force, binding energy, nuclear fission and fusion. In each of them, you need to know the following. So, size of the nucleus, you need to know the radius, the density, atomic mass unit, what happens when Z is same, what happens when number of neutrons are same, what happens when number of total nucleons are same, these concepts. Mass defect, you should know how does, so basically the concept of mass being destroyed creating energy or mass being created destroying energy, and the relationship which is E is equal to mc square, and then the concept of nuclear force, which is extremely short range, more powerful than gravity and electromagnetic force, and it acts between any kind of things like proton, proton, neutron, neutron. It does not depend on the charge. Binding energy, which is dependent on the mass defect, and the calculation of binding energy per unit, per nucleon, the Q value for reactions, and the difference between fission, fusion, why fission occurs, why or how does fusion occur, and how is the stability affected by binding energy. So all these are important pointers. You should go through it. So for that, I have put up this chart right before you. Check this out. All the formulas right in front of your eyes. My name is Shreyas. No derivation in nuclei. Yes, Janaya studies no derivation. Now nuclear force says shows saturated property, meaning that, you know, what happens is like if you say electric force or gravitational force, if you separate the distance or separate the masses or charges, the force slowly goes away. In nuclear physics, it's not like that. If there are two particles, proton, proton, neutron, neutron, when you separate them, the force, let's say, it will go off. It's there, it reduces, gone. Suddenly, sudden drop. So that's why it is saturated in a small region. Okay. The map is epic. Now this is going to give you all the concepts. You should know this graph, the binding energy per nucleon. This also tells you this is stable. Binding energy means the energy which is, now this is one common doubt between, for many students, what's the difference between binding energy, what's the difference between Q value? How many of you have that doubt? Or how many of you know the difference? Okay, understand this. See, when I talk about binding energy, think of formation of the nucleus. Formation of the nucleus. When a nucleus is formed, it is made from neutron, proton, neutron, proton. When they collect and form the nucleus, the energy released is called as the binding energy. So it is in the formation of a nucleus from proton and neutron, that there will be some mass difference. That mass difference creates some energy, delta mc square. That is your binding energy. But Q value is not for the formation of nucleus. It can be for fission or for fusion. Two nuclei combine to form another nuclei. A nuclei decomposed into smaller nuclei. There will be some mass difference between the products and the reactants. You take the difference, multiply it with c square. Mass difference into c square. That gives you Q value. So Q value is for fission or fusion. Concept wise it is same. It is energy which comes out of the mass defect. But the mass defect arises because of what process? Formation of nuclei or fusion fission. That decides whether it is Q value or binding energy. Is that clear? Okay, just keep this in mind. Binding energy is okay. Just keep a note of this graph. Also, you should know what is AMU. 1 AMU corresponds to 931 mega electron volt. Just keep a note of this. Know the fission fusion reactions, at least one example, especially for that uranium, hydrogen combining into helium, uranium U-35 making bombarded with a neutron, becoming unstable uranium, and then decomposing into its daughter nuclei. You should know it. Okay. So Selva Karthik, the graph of that potential energy versus distance is like your molecular bonding. You would have learned that in chemistry. When two molecules come very close, then they repel. When the two molecules go very far, they attract. There is an equilibrium distance. That graph which is there is exactly the same. It's exactly the same, but instead it is for two inside the nucleus particles. So if two protons come very close, the potential energy increases. They will not like it, they will repel. If two protons go away, they will again attract and they will again come back. So it's similar to that. Okay, parent and daughter. See, parent means reactant, product means daughter. Be it fission or be it fusion. Two hydrogen combine to form helium. Hydrogen parent, helium daughter. Okay, uranium decomposed into barium, cryptium, whatever. So that initial uranium is parent, the products are the daughters. Okay, all the chapters graphs are important. I don't think there are graphs in your ray optics except for the minimum deviation. Okay, so yes, so Q value decides whether it's endothermic or exothermic reaction. So if Q value is positive, that means energy is coming out. Energy is coming out. And if Q value is negative, that means energy is being sucked in. Keep this in mind. Alright, is this clear? Yeah, you should know this formula for radius also, R0 into A raised to 1 by 3. What's the value of R0, guys? Come on, let's see how many of you, yeah, no sons apparently. Yes, Nikki. So let's give daughters also a chance. Everywhere we talk about sons and guys and men. So yes, I'm so happy that even the daughters have a chance over here. 1.2 femtometers, very good. FM, 10 to the power minus 15. Okay. I'll be taking a session tomorrow, Sayed, definitely. Now, this graph will definitely help you. Now in semiconductor, how are you going to quickly revise? Notice this. You need to know energy bands, PN junction formation, semiconductor as a diode, diode as a rectifier, special applications of diode. This is your mind map, and in each of them you should know these concepts. This is your mind map. Revise in your head. Let's revise together. Come on, guys. Let's do this. We are coming to that, Siddiqui. Okay. So timing for tomorrow is 7:30 only, I think. Just check it out. I think it's 7 or 7:30, one of them. Be there. Just check the schedule. It should be there in the upcoming sessions also. Now, energy bands. Band formation. There are two kinds of bands. One is called conduction band. Second is called valence band. Okay, it's 7 o'clock. Thank God. You guys know it. So two bands, conduction band, valence band. What is the meaning of valence band? Valence band are those bands which are completely filled. Conduction band, they are not filled, empty, okay, or half filled. Like in sodium, it's half filled, right? All the energy bands are drawn at which temperature? Room temperature or 0 Kelvin? Come on, guys. Think. All the energy bands are drawn at room temperature or at 0 Kelvin or some other temperature. 7, the Dhuni number. Atomic spectra, Shravana, just go through it, the spectral lines. It's only there qualitative wise, the formula is not there. Yes, it is always at 0 Kelvin. Correcto. Now, having said that, if the conduction band has some electrons at room temperature, why it has some electrons? Because of the thermal energy, the electrons go up, then the solid becomes conducting. And that band gap difference is called as the band gap. And if this band gap is less than 3 electron volt, it is semiconductor. More than 3 electron volt, insulator. It is very difficult for it to jump. And if they coincide, merge, it is called as a conductor. Yeah, and that gap is also called as the forbidden energy gap. Keep this in mind. Okay, let's revise this quickly. Next thing, when you increase the temperature of a conductor, resistance increases because collisions increase. But for a semiconductor, when you increase the temperature, more electrons enter the conduction band, and that's why the resistance decreases because it becomes more conductive. Okay. Now, semiconductors can be intrinsic or extrinsic. So we are going slowly towards the types of semiconductors. Intrinsic is pure, extrinsic is impure. Like germanium or silicon forming 4 bonds everywhere, that's a pure semiconductor. Conductivity happens because of the formation of holes and electrons. What is hole? I'll come to ripple factor, Prem. Hold on. Yes. Intrinsic semiconductors, what is hole and what is electron? Yes. Electron is that free electron which moves around. Hole is the absence of the electron. And the concentration is same. Ne and NH. Holes and electrons are same in number in pure or intrinsic semiconductor. You add some material like phosphorus, okay, or antimony, that's pentavalent impurity, 5, one extra electron. What will it do? It will create one excess electron, and if you put more pentavalent impurities, it makes it n-type. Correct? Okay. Now, in that same structure, you put trivalent impurity like aluminium. All right. So what happens? One electron is less, it creates a vacancy, it creates a hole. That makes it p-type of semiconductor. That's what it is. When you add pentavalent, make it n-type, pentavalent n-type, you create a donor energy level between the conduction and the valence band. Valence is here, conduction is here. You create a donor level energy in between, which makes it easier for the conduction to happen. But if you make it p-type, you create an acceptor level energy, which makes it easier for the electron to jump to a smaller energy level. Transistor is not there in the syllabus. Very good. Excellent. Now, having said this, the concentration of electron and hole, the product, what is that product? Come on, let me know in the chat box. Ne into NH, the concentration of electrons and holes is equal to, I'll come to that, Ajay, hold on, just give me a second. What is it? Ni square. What is Ni? It's the concentration of holes and electrons in an intrinsic, that I stands for intrinsic, not doped. Very good, it is Ni square. Perfect. That's what you should know. Now let's go to PN junction. Visualize, everything you have to visualize. Don't go through the books. See, I'm making you visualize. Now you're slowly remembering it. You might be keeping your books in front, but that's okay. But try to think, try to analyze. PN junction, P has holes, N has electrons. P has holes, N has electrons. When they combine, when they join, the electrons jump from N to P. When electrons jump from N to P, N will become what charged? P will become what charged? When electrons jump from N to P, because N has electrons, P has holes, need is there, supply is there, demand meets supply. So N will become positively charged, P will become negatively charged. Yes, N becomes positive because electrons leave it, P becomes negatively charged. So what will be created? Field will be created. Between what? p-n junction. This process of the flow of the electrons from n to p, electrons are flowing. This is called as drift or diffusion. This is called as diffusion. Very good. And that current which is created is called as diffusion current. Obviously the flow is opposite because current flows opposite to electrons. Okay, that is called as diffusion current. Because of this electric field, there will be something created. Something is coming. What is this coming, guys? Come on, visualize this. What is coming? Because the electrons are jumping, electric field is created. Something is coming between them. Something is coming between them. What is it? Depletion layer, potential barrier. A potential difference created, barrier is created. Barrier is created. So it will prevent the flow of the electrons. But the electric field which is there, that will apply a force on the electrons in the exact opposite direction. The electric field which is there, it will apply force in the opposite direction. So that will make the electrons flow from p to n, not n to p, p to n. Electrons flow from p to n, p to n. That current is called as drift current. Drift current. Correct? See, mind maps are so important. It's very important you make these kind of notes. Okay, let's go ahead. In an unbiased p-n junction, diffusion and drift are equal or not equal? Diffusion and drift are equal or not equal? They are equal. So the net current is 0. Okay. Now if you bias it, let's say forward bias, you forward bias it, then which current exceeds which current? Equilibrium is established in unbiased, correct? If you forward bias it, then which current is more? Current will flow from p to n, that means electrons will flow from n to p. Electrons flow from n to p, that is diffusion. Yes, diffusion. Think logically. Forward bias, the current flows from p to n. That means electrons flow from n to p. N to p what flows? Diffusion. So diffusion is more. In reverse bias, it's exactly opposite. That's the drift current. But drift is very small because the drift happens only in the depletion layer. Where does drift happen? In the depletion layer. In depletion layer, it's a small region. It's not the major part of the semiconductor. So hence, the current is also very small. Current is also very small in the reverse bias. In the forward bias, the current is very large. Now, a device which conducts electricity only in one direction, not in the opposite direction, such a device is called as an device which conducts electricity only in one direction, not in the other direction, is called as, what is it called? It is called as diode. No, it is not rectified. Diode. Remember, our heart also has a diode. It flows, the blood flows only in one direction in those particular valves. Diode. Current flows in one direction. There is very little current. That current is called as leakage current. Very little current in the reverse direction. In the forward direction, the current flows, but only after a peculiar voltage, unless it's an ideal diode. Ideal diode does not have any kind of barrier. Ideal diode does not have any kind of resistance. It conducts very easily. But no such diode exists. Germanium diode and silicon diode need certain voltage in the forward bias to make it conductive. For germanium, yes, that is called as the knee voltage. For germanium and silicon, the voltages are 0.2 and 0.7. If you get confused which one is for what, I remember it this way. Silicon, 7. Got it? 0.7 is that minimum voltage after which the forward voltage, the diode in the forward bias begins to conduct. Okay, keep this in mind. And for germanium, it is mentioned as 0.2, but in many other books, it is given as 0.3. You will write it as per NCERT, you will put it as 0.2. Understood? Very good. Excellent. Moving on. Now, you should know the IV characteristics. Very important. Okay, that leakage current in the fourth quadrant, and then it goes in the first quadrant. You should know fourth and first. Now, applications of diodes. Half wave, full wave. Now, Rectifier. What is rectifier? Rectification is the process of converting dash into dash. RK Gupta, I didn't reply, is it? Yeah, yesterday I did not reply because I was exhausted, I slept, and that's all. I'll reply today, hopefully. AC to DC, very good. Half wave will rectify half of that wave. Upper half, lower half. Lower half gone, upper half only goes. Positive cycle. How many diodes are used in half wave rectifier? Only one. Only one. Only one. Only one. Only one. Okay? Okay. And if the input frequency is 50 Hertz, output frequency for half wave rectifier will be how many Hertz? Input frequency is 50 Hertz, output frequency will be? Yes. Yeah, the name itself explains it. Yes, surely RK Gupta will explain. 50 only. Full wave means two rectifiers, but there is one common line. Remember, two diodes in the same direction, they come like this, and there is a connection to the central tap transformer. That is a full wave rectification, and in full wave rectification, if you give input signal of 50 Hertz, output frequency will be 100 Hertz, twice the input frequency. But the output which comes is not proper, it is varying. So you collect a capacitor or a filter to make it more smoother. So you reduce the ripple effect, that's all. Now there are three more applications of semiconductor. LED, photodiode, solar cell. LED, light emitting diode. So show a diode, show two arrow marks coming out, that's the symbol. LED, where is it used? Bulbs, TVs, indicators, to show something, warning, whatever, bulb, light. It is very efficient, it is very cheap, very easy to fabricate. Also, it is monochromatic light. LED works in forward or reverse bias? No, burglar alarm wrong, Ajay. No, not in burglar alarm. Burglar alarm, you'll use sound. Burglar alarm is second thing, photodiode. Be careful. It is forward bias. No, not reverse, forward. Guys, made a mistake. Forward bias. It will just conduct normally. Lot of current will flow. More current means more light or less light? More current means more light or less light? Yeah, more light. Yes. Okay, forward bias. LED, it gives light. It gives light. Forward. Forward. Gives forward. Photo takes reverse. Repeat. LED, forward, gives. Photodiode takes light, reverse. Photodiode is conducted in reverse bias. Photodiode absorbs light, conducts in reverse bias. Based on the light, the current changes. Since it's in reverse bias, there will be leakage current, obviously. Leakage current. So, leakage current is small. So, if the light changes, the leakage current will change, and to observe that difference, it will be very easy. That's why, you use photodiode in the reverse bias. There is a give reason passage, go through it. Give reason. This can 90% come in tomorrow's exam or day after tomorrow's exam. Why is it used in reverse bias? Not in forward. Forward bias, it's so high, you will not notice the changes. And uses burglar alarm, motion detection to detect the intensity of light, to turn on and off alarms based on the light. So many applications are there. Last one, solar cell. No bias. No bias. Yes. There is a construction diagram. The layers which are given, go see that diagram, write it as it is, draw it as it is. Uses of solar cell, everybody knows. But making it is very costly, and all about the efficiency, how it is very useful for the environment, all of that you can write. In solar cell, there is no bias, there is no external circuit, keep that in mind. It itself acts like the battery. It itself acts like the source, it produces electricity. More light, more surface, more current. That's another point. Also, the graph of voltage and current is in the this quadrant, this side, below the first quadrant, fourth quadrant. Keep this in mind. Okay. Oh, sorry guys, when I told you about the IV characteristic, I just realized now. I told you it is in the first and the fourth quadrant. My bad. It is in the first and the third quadrant. My bad. Sorry. Saying 1, 2, 3. This is 3, not 4. 4 is for the solar cell. Solar cell IV characteristic is in the fourth quadrant. Be careful. EM wave also I discussed at the beginning only. Okay, keep this in mind. So that's it. That is there. Major revision is done.